Escherichia coli, E. coli, bacteria electron micrograph of E. coli bacteria, credit. Matasaurus, Wikimedia Commons, chapter outline 6 1 exponential functions 6 2 graphs of exponential functions 6 3 logarithmic functions 6 4 graphs of logarithmic functions 6 5 logarithmic properties 6 6 exponential and logarithmic equations 6 7 exponential and logarithmic models 6 8 fitting exponential models to date. A focus in on a square centimeter of your skin. Look closer. Closer still. If you could look closely enough, you would see hundreds of thousands of microscopic organisms. They are bacteria, and they are not only on your skin, but in your mouth, nose, and even your intestines. In fact, the bacterial cells in your body at any given moment outnumber your own cells. But that is no reason to feel bad about yourself. While some bacteria can cause illness, many are healthy and even essential to the body. Bacteria commonly reproduce through a process called binary fission, during which one bacterial cell splits into two. When conditions are right, bacteria can reproduce very quickly. Unlike humans and other complex organisms, the time required to form a new generation of bacteria is often a matter of minutes or hours, as opposed to days or years. For simplicity's sake, suppose we begin with a culture of one bacterial cell that can divide every hour. Table 1 shows the number of bacterial cells at the end of each subsequent hour. We see that the single bacterial cell leads to over 1,000 bacterial cells in just 10 hours. And if we were to extrapolate the table to 24 hours, we would have over 16 million. Hour 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, bacteria 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, Table 1 in this chapter. We will explore exponential functions, which can be used for, among other things, modeling growth patterns such as those found in bacteria. We will also investigate logarithmic functions, which are closely related to exponential functions. Both types of functions have numerous real-world applications when it comes to modeling and interpreting data. Learning objectives in this section, you will evaluate exponential functions. Find the equation of an exponential function. Use compound interest formulas. Evaluate exponential functions with base e. India is the second most populous country in the world, with a population of about 139 billion people in 2021. The population is growing at a rate of about 1–2% each year too. If this rate continues, the population of India will exceed China's population by the year 2027. When populations grow rapidly, we often say that the growth is exponential, meaning that something is growing very rapidly. To a mathematician, however, the term exponential growth has a very specific meaning. In this section, we will take a look at exponential functions, which model this kind of rapid growth. Identifying exponential functions when exploring linear growth, we observed a constant rate of change, a constant number, by which the output increased for each unit increase in input. For example, in the equation letter 1d453, letter 1d465 equals 3 letter 1d465 plus 4, the slope tells us the output increases by 3 each time the input increases by 1. The scenario in the India population example is different because we have a percent change per unit time, rather than a constant change in the number of people. Defining an exponential function, a study found that the percent of the population who are vegans in the United States doubled from 2009 to 2011. In 2011, 25% of the population was vegan, adhering to a diet that does not include any animal products, no meat, poultry, fish, dairy, or eggs. If this rate continues, vegans will make up 10% of the U.S. population in 2015, 40% in 2019, and 80% in 2021. What exactly does it mean to grow exponentially? What does the word double have in common with percent increase? People toss these words around errantly. Are these words used correctly? The words certainly appear frequently in the media. Percent change refers to a change based on a percent of the original amount. Exponential growth refers to an increase based on a constant multiplicative rate of change over equal increments of time. That is, a percent increase of the original amount over time. Exponential decay refers to a decrease based on a constant multiplicative rate of change over equal increments of time. That is, a percent decrease of the original amount over time. For us to gain a clear understanding of exponential growth, let us contrast exponential growth with linear growth. We will construct two functions. The first function is exponential. We will start with an input of 0 and increase each input by 1. We will double the corresponding consecutive outputs. The second function is linear. We will start with an input of 0 and increase each input by 1. We will add 2 to the corresponding consecutive outputs. See Table 1. X letter 1d453, letter 1d465, equals 2 letter 1d465 letter 1d454. Letter 1d465, equals 2 letter 1d4650, 10122244386416853210 Table 1. From Table 1, we can infer that for these two functions, exponential growth dwarfs linear growth. Exponential growth refers to the original value from the range increases by the same percentage over equal increments found in the domain. Linear growth refers to the original value from the range increases by the same amount over equal increments found in the domain. Apparently, the difference between the same percentage and the same amount is quite significant. For exponential growth over equal increments, the constant multiplicative rate of change resulted in doubling the output whenever the input increased by 1. For linear growth, the constant additive rate of change over equal increments resulted in adding 2 to the output whenever the input was increased by 1. The general form of the exponential function is letter 1d453. Letter 1d465 equals letter 1d44 letter 1d44f letter 1d465, where a is any non-zero number, b is a positive real number not equal to 1. If letter 1d44f1, the function grows at a rate proportional to its size. If 0 letter 1d44f1, the function decays at a rate proportional to its size. Let's look at the function letter 1d453, letter 1d465, equals 2 letter 1d465 from our example. We will create a table 2, to determine the corresponding outputs over an interval in the domain from -3 to 3. X minus 3 minus 2 minus 1 0, 1 2 3 letter 1d453, letter 1d465, equals 2 letter 1d465 2 minus 3 equals 18 2 minus 2 equals 14 2 minus 1 equals 12 20 equals 121 equals 222 equals 423 equals 8 Table 2. Let us examine the graph of f by plotting the ordered pairs we observe on the table in Figure 1, and then make a few observations. Graph of companies A and B's functions, which values are found in the previous table. Figure 1 lets define the behavior of the graph of the exponential function letter 1d453, letter 1d465, equals 2 letter 1d465, and highlight some its key characteristics. The domain is -infinity, infinity. The range is 0, infinity, as letter 1d465 right infinity, letter 1d453, letter 1d465, right infinity. As letter 1d465 right -infinity, letter 1d453, letter 1d465 right arrow 0, letter 1d453, letter 1d465 is always increasing. The graph of letter 1d453, letter 1d465 will never touch the x-axis because base 2 raised to any exponent never has the result of 0. Letter 1d466 equals 0 is the horizontal asymptote. The y-intercept is 1. Exponential function for any real number x. An exponential function is a function with the form letter 1d453, letter 1d465, equals letter 1d44 letter 1d44f letter 1d465, where a is a non-zero real number called the initial value, and b is any positive real number such that letter 1d44f not equal to 1. The domain of f is all real numbers. The range of f is all positive real numbers if letter 1d44 is 0. The range of f is all negative real numbers if letter 1d44 is 0. The y-intercept is 0a, and the horizontal asymptote is letter 1d466 equals 0. Example 1, identifying exponential functions. Which of the following equations are not exponential functions? Letter 1d453, letter 1d465 equals 43, letter 1d465 minus 2, letter 1d454. Letter 1d465 equals letter 1d465 3 letter 210e. Letter 1d465 equals 13 letter 1d465 letter 1d457. Letter 1d465 equals minus 2 letter 1d465 solution by definition. An exponential function has a constant as a base and an independent variable as an exponent. Thus, letter 1d454, letter 1d465 equals letter 1d4653 does not represent an exponential function because the base is an independent variable. In fact, letter 1d454, letter 1d465 equals letter 1d4653 is a power function. Recall that the base b of an exponential function is always a positive constant, and letter 1d44f not equal to 1. Thus, letter 1d457, letter 1d465 equals minus 2 letter 1d465 does not represent an exponential function because the base, minus 2, is less than 0. Try at 1 which of the following equations represent exponential functions. Letter 1d453, letter 1d465 equals 2 letter 1d465 2 minus 3 letter 1d465 plus 1 letter 1d454. Letter 1d465 equals 0. 875x letter 210e. Letter 1d465 equals 1. 75x plus 2 letter 1d457. Letter 1d465 equals 1095. 6 minus 2 letter 1d465 evaluating exponential functions. Recall that the base of an exponential function must be a positive real number other than 1. Why do we limit the base b to positive values? To ensure that the outputs will be real numbers. Observe what happens if the base is not positive. Let letter 1d44f equals minus 9 and letter 1d465 equals 12. Then letter 1d453, letter 1d465 equals letter 1d453, 12 equals minus 9 12 equals minus 9 square, which is not a real number. Why do we limit the base to positive values other than 1? Because base 1 results in the constant function. Observe what happens if the base is 1. Let letter 1d44f equals 1. Then letter 1d453, letter 1d465 equals 1 letter 1d465 equals 1 for any value of x. To evaluate an exponential function with the form letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465, we simply substitute x with the given value and calculate the resulting power. For example, let letter 1d453, letter 1d465 equals 2 letter 1d465. What is letter 1d4533? Letter 1d453, letter 1d465 letter 1d453, 3 equals 2 letter 1d465 equals 23 equals 8 substitute letter 1d465 equals 3. Evaluate the power. To evaluate an exponential function with a form other than the basic form, it is important to follow the order of operations. For example, let letter 1d453, letter 1d465 equals 30, 2 letter 1d465. What is letter 1d453? 3. Letter 1d453, letter 1d465, letter 1d453, 3 equals 30, 2 letter 1d465 equals 30, 2 3 equals 30, 8 equals 240 substitute. Simplify the power first. Multiply. Note that if the order of operations were not followed, the result would be incorrect. Letter 1d453, 3 equals 30, 2, 3 not equal to 603 equals 216, 0, 0, 0. Example 2. Evaluating exponential functions, let letter 1d453, letter 1d465 equals 5, 3, letter 1d465 plus 1. Evaluate letter 1d453, 2, without using a calculator. Solution follow the order of operations. Be sure to pay attention to the parentheses. Letter 1d453, letter 1d465, letter 1d453, 2 equals 5, 3, letter 1d465 plus 1 equals 5, 3 2 plus 1 equals 5, 3 3 equals 5, 27 equals 135. Substitute letter 1d465 equals 2. Add the exponents. Simplify the power. Multiply. Try it 2. Let letter 1d453, letter 1d465 equals 8, 1. 2 letter 1d465 minus 5. Evaluate letter 1d453, 3, using a calculator. Round to 4 decimal places. Defining exponential growth because the output of exponential functions increases very rapidly. The term exponential growth is often used in everyday language to describe anything that grows or increases rapidly. However, exponential growth can be defined more precisely in a mathematical sense. If the growth rate is proportional to the amount present, the function models exponential growth. Exponential growth, a function that models exponential growth, grows by a rate proportional to the amount present for any real number x and any positive real numbers a and b, such that letter 1d44f not equal to 1. An exponential growth function has the form letter 1d453. Letter 1d465 equals letter 1d44, letter 1d44f, letter 1d465, where a is the initial or starting value of the function. B is the growth factor or growth multiplier per unit x. In more general terms, we have an exponential function in which a constant base is raised to a variable exponent. To differentiate between linear and exponential functions, let's consider two companies. A and B. Company A has 100 stores and expands by opening 50 new stores a year. So its growth can be represented by the function letter 1d434. Letter 1d465 equals 100 plus 50 letter 1d465. Company B has 100 stores and expands by increasing the number of stores by 50% each year. So its growth can be represented by the function letter 1d435. Letter 1d465 equals 100, 1 plus 0. 5 letter 1d465. A few years of growth for these companies are illustrated in Table 3. Year, X stores, Company A stores, Company B 0, 100 plus 50, 0 equals 100, 100, 1 plus 0. 5 0 equals 100, 100 plus 50, 1 equals 150, 100, 1 plus 0. 5 1 equals 152, 100 plus 50, 2 equals 200, 100, 1 plus 0. 5 2 equals 225, 3 100 plus 50, 3 equals 250, 100, 1 plus 0. 5 3 equals 337. 5x letter 1d434. Letter 1d465 equals 100 plus 50 letter 1d465 letter 1d435. Letter 1d465 equals 100. 1 plus 0. 5 letter 1d465 Table 3, the graphs comparing the number of stores for each company over a 5-year period are shown in Figure 2. We can see that, with exponential growth, the number of stores increases much more rapidly than with linear growth. Graph of companies A and B's functions, which values are found in the previous table. Figure 2, the graph shows the numbers of stores companies A and B opened over a 5-year period. Notice that the domain for both functions is 0, infinity, and the range for both functions is 100, infinity. After year 1, Company B always has more stores than Company A. Now we will turn our attention to the function representing the number of stores for Company B, letter 1d435, letter 1d465, equals 100, 1 plus 0. 5 letter 1d465. In this exponential function, 100 represents the initial number of stores, 0. 50 represents the growth rate, and 1 plus 0. 5 equals 1. 5 represents the growth factor. Generalizing further, we can write this function as letter 1d435. Letter 1d465 equals 100, 1. 5, letter 1d465, where 100 is the initial value, 1. 5 is called the base, and x is called the exponent. Example 3, evaluating a real-world exponential model. At the beginning of this section, we learned that the population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1–2%. This situation is represented by the growth function letter 1d443, letter 1d461 equals 1.25, 1. 0, 12, letter 1d461, where t is the number of years since 2013. To the nearest thousandth, what will the population of India be in 2031? Solution: to estimate the population in 2031, we evaluate the models for letter 1d461 equals 18. because 2031 is 18 years after 2013. Rounding to the nearest thousandth, letter 1d443, 18 equals 1, 25 1, 0 12 18 approximately 1, 549 there will be about 1, 549 billion people in India in the year 2031. Try it 3, the population of China was about 139 billion in the year 2013, with an annual growth rate of about 0.6%. This situation is represented by the growth function letter 1d443, letter 1d461 equals 1, 39, 1, 0, 0, 6, letter 1d461, where t is the number of years since 2013. To the nearest thousandth, what will the population of China be for the year 2031? How does this compare to the population prediction we made for India in example 3? Finding equations of exponential functions in the previous examples, we were given an exponential function, which we then evaluated for a given input. Sometimes, we are given information about an exponential function without knowing the function explicitly. We must use the information to first write the form of the function, then determine the constants a and b, and evaluate the function. How to given two data points, write an exponential model. If one of the data points has the form 0a, then a is the initial value. Using a, substitute the second point into the equation letter 1d453. Letter 1d465 equals letter 1d44e, letter 1d44f, letter 1d465, and solve for b. If neither of the data points have the form 0a, substitute both points into two equations with the form letter 1d453, letter 1d465, equals letter 1d44e, letter 1d44f, letter 1d465. Solve the resulting system of two equations in two unknowns to find a and b using the a and b found in the steps above. Write the exponential function in the form letter 1d453. Letter 1d465 equals letter 1d44e, letter 1d44f, letter 1d465. Example 4, writing an exponential model when the initial value is known in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an exponential function letter 1d441, letter 1d461, representing the population n of deer over time t. Solution, we let our independent variable t be the number of years after 2006. Thus, the information given in the problem can be written as input-output pairs, 0, 80, and 6, 180. Notice that by choosing our input variable to be measured as years after 2006, we have given ourselves the initial value for the function, letter 1d44e equals 80. We can now substitute the second point into the equation, letter 1d441. Letter 1d461 equals 80 letter 1d44f letter 1d461 to find b. Letter 1d441. Letter 1d461 18,094, letter 1d44f letter 1d44f equals 80 letter 1d44f letter 1d461 equals 80 letter 1d44f, 6 equals letter 1d44f, 6 equals 94, 16 approximately 1. 1447 substitute using point 6, 180, divide and write in lowest terms. Isolate busing properties of exponents. Round to 4 decimal places. Note, unless otherwise stated, do not round any intermediate calculations. Then round the final answer to 4 places for the remainder of this section. The exponential model for the population of deer is letter 1d441, letter 1d461 equals 80, 1. 1447, letter 1d461. Note that this exponential function models short-term growth. As the inputs gets large, the output will get increasingly larger, so much so that the model may not be useful in the long term. We can graph our model to observe the population growth of deer in the refuge over time. Notice that the graph in Figure 3 passes through the initial points given in the problem, 80 and 6,180. We can also see that the domain for the function is 0, infinity, and the range for the function is 80, infinity. Graph of the exponential function, nt equals 80, 1. 1447t, with labeled points at 0, 80, and 6, 180. Figure 3 graph showing the population of deer over time, letter 1 D441, letter 1 D461, equals 81. 1,447, letter 1 D461. T years after 2006, try it for a wolf population is growing exponentially. In 2011, 129 wolves were counted. By 2013, the population had reached 236 wolves. What 2 points can be used to derive an exponential equation modeling this situation? Write the equation representing the population n of wolves over time t. Example 5. Writing an exponential model. When the initial value is not known, find an exponential function that passes through the points -2, 6, and 21. Solution: because we don't have the initial value, we substitute both points into an equation of the form letter 1 D453. Letter 1 D465 equals letter 1 D44, letter 1 D44F, letter 1 D465, and then solve the system for A and B. Substituting -2, 6 gives 6 equals letter 1 D44, letter 1 D44F minus 2, substituting. 21 gives 1 equals letter 1 D44, letter 1 D44F2, use the first equation to solve for A in terms of B. Substitute A in the second equation and solve for B. Use the value of B in the first equation to solve for the value of A. Thus, the equation is letter 1 D453, letter 1 D465 equals 2, 4,492, 0. 6,389, letter 1 D465. We can graph our model to check our work. Notice that the graph in figure 4 passes through the initial points given in the problem, -2, 6, and 21. The graph is an example of an exponential decay function. Graph of the exponential function, f(x) equals 2, 4,492, 0. 6,389x, with labeled points at -2, 6, and 2, 1. Figure 4, the graph of letter 1 D453, letter 1 D465, equals 2, 4,492, 0. 6,389, letter 1 D465 models exponential decay. Try it 5 given the 2 points, 13 and 24. 5. Find the equation of the exponential function that passes through these 2 points. Q and A do 2 points always determine a unique exponential function? Yes, provided the 2 points are either both above the x-axis or both below the x-axis and have different x-coordinates. But keep in mind that we also need to know that the graph is, in fact, an exponential function. Not every graph that looks exponential really is exponential. We need to know the graph is based on a model that shows the same % growth with each unit increase in x, which in many real-world cases involves time. How to given the graph of an exponential function, write its equation. First, identify 2 points on the graph. Choose the y-intercept as one of the 2 points whenever possible. Try to choose points that are as far apart as possible to reduce round-off error. If one of the data points is the y-intercept, 0a, then A is the initial value. Using A, substitute the second point into the equation letter 1 D453. Letter 1 D465 equals letter 1 D440, letter 1 D44F, letter 1 D465, and solve for B. If neither of the data points have the form 0a, substitute both points into 2 equations with the form letter 1 D453, letter 1 D465, equals letter 1 D440, letter 1 D44F, letter 1 D465. Solve the resulting system of 2 equations in 2 unknowns to find A and B. Write the exponential function, letter 1 D453, letter 1 D465, equals letter 1 D440, letter 1 D44F, letter 1 D465. Example 6, writing an exponential function given its graph, find an equation for the exponential function graphed in figure 5. Graph of an increasing exponential function with notable points at 0, 3, and 2, 12. Figure 5 solution, we can choose the y-intercept of the graph, 3, as our first point. This gives us the initial value, letter 1 D440 equals 3. Next, choose a point on the curve some distance away from 3 that has integer coordinates. One such point is 212. Letter 1 D466 equals letter 1 D440, letter 1 D44F, letter 1 D465, letter 1 D466 equals 3, letter 1 D44F, letter 1 D465, 12, equals 3, letter 1 D44F. 2, 4 equals letter 1d4 4f. 2 letter 1d4 4f equals plus. 2. Write the general form of an exponential equation. Substitute the initial value 3 for a substitute in 12 for letter 1d466, a nd2 for x divide by 3 take the square root. Because we restrict ourselves to positive values of b, we will use letter 1d4 4f equals 2. Substitute a and b into the standard form to yield the equation letter 1d453. Letter 1d465 equals 3, 2 letter 1d465. Try at 6, find an equation for the exponential function graphed in figure 6. Graph of an increasing function with a labeled point at 0, sqrt, 2. Figure 6, how to given 2 points on the curve of an exponential function, use a graphing calculator to find the equation. Press Stat. Clear any existing entries in columns L1 or L2. In L1, enter the x-coordinates given. In L2, enter the corresponding y-coordinates. Press Stat again. Cursor right to CALC, scroll down to XBREG, exponential regression, and press Enter. The screen displays the values of a and b in the exponential equation letter 1d466 equals letter 1d44e, letter 1d44f, letter 1d465. Example 7, using a graphing calculator to find an exponential function, use a graphing calculator to find the exponential equation that includes the points 224, 8 and 5198 4. Solution, follow the guidelines above. First press Stat, Edit 1, Edit, and clear the lists L1 and L2. Next, in the L1 column, enter the x-coordinates 2 and 5. Do the same in the L2 column for the y-coordinates 24, 8 and 198. 4 now press Stat, Calc, 0, XBREG, and press Enter. The values letter 1d44e equals 6, 2, and letter 1d44f equals 2 will be displayed. The exponential equation is letter 1d466 equals 6, 2, 2 letter 1d465. Try at 7, use a graphing calculator to find the exponential equation that includes the points 3, 75, 98, and 6, 480, 17. Applying the compound interest formula savings instruments in which earnings are continually reinvested, such as mutual funds and retirement accounts, use compound interest. The term compounding refers to interest earned not only on the original value, but on the accumulated value of the account. The annual percentage rate, APR, of an account, also called the nominal rate, is the yearly interest rate earned by an investment account. The term nominal is used when the compounding occurs a number of times other than once per year. In fact, when interest is compounded more than once a year, the effective interest rate ends up being greater than the nominal rate. This is a powerful tool for investing. We can calculate the compound interest using the compound interest formula, which is an exponential function of the variables time t, principal p, APRR, and number of compounding periods in a year n. Letter 1d434, letter 1d461 equals letter 1d443. 1 plus letter 1d45f, letter 1d45b, letter 1d45b, letter 1d461, for example, observe Table 4, which shows the result of investing $1,000 at 10% for 1 year. Notice how the value of the account increases as the compounding frequency increases. Frequency value, after 1 year, annually $1,100, semi-annually $1,102. $50 quarterly $1,103. 80 1 monthly $1,104. $71 daily $1,105. 16 Table 4, the compound interest formula. Compound interest can be calculated using the formula letter 1d434. Letter 1d461 equals letter 1d443. 1 plus letter 1d45f, letter 1d45b, letter 1d45b, letter 1d461, where letter 1d434, letter 1d461, is the account value. T is measured in years, P is the starting amount of the account, often called the principal, or more generally present value. R is the annual percentage rate, APR, expressed as a decimal, and N is the number of compounding periods in 1 year. Example 8, calculating compound interest. If we invest $3,000 in an investment account paying 3% interest compounded quarterly, how much will the account be worth in 10 years? Solution: because we are starting with $3,000, letter 1D443 equals 3,000. Our interest rate is 3%, so letter 1D45F equals 0. 3. Because we are compounding quarterly, we are compounding 4 times per year, so letter 1D45B equals 4. We want to know the value of the account in 10 years, so we are looking for letter 1D434, 10, the value when letter 1D461 equals 10. Letter 1D434, letter 1D461, letter 1D434, 10 equals letter 1D443. 1 plus letter 1D45F, letter 1D45B, letter 1D45B, letter 1D461 equals 3,000. 1 plus 0. 0, 34, 410, approximately $4,045. 5. Use the compound interest formula. Substitute using given values. Round to 2 decimal places. The account will be worth about $4,045. $5 in 10 years. Try at 8. An initial investment of $100,000 at 12% interest is compounded weekly. Use 52 weeks in a year. What will the investment be worth in 30 years? Example 9. Using the compound interest formula to solve for the principal, a 529 plan is a college savings plan that allows relatives to invest money to pay for a child's future college tuition. The account grows tax-free. Lily wants to set up a 529 account for her new granddaughter and wants the account to grow to $40,000 over 18 years. She believes the account will earn 6% compounded semi-annually, twice a year. To the nearest dollar, how much will Lily need to invest in the account now? Solution: the nominal interest rate is 6%, so letter 1D45F equals 0. 6. Interest is compounded twice a year, so letter 1D45B equals 2. We want to find the initial investment, P, needed so that the value of the account will be worth $40,000 in 18 years. Substitute the given values into the compound interest formula and solve for P. Letter 1D434, letter 1D461 40, 00040, 00040, 0001, 03, 36. Letter 1D443 equals letter 1D443. 1 plus letter 1D45F, letter 1D45B, letter 1D45B, letter 1D461 equals letter 1D443. 1 plus 0. 0, 62, 2, 18 equals letter 1D4431. Use the compound interest formula. Substitute using given values A, R, N, and T. Simplify. Isolate P, divide and round to the nearest dollar. Lily will need to invest $13,801 to have $40,000 in 18 years. Try at 9, refer to example 9. To the nearest dollar, how much would Lily need to invest if the account is compounded quarterly? Evaluating functions with base E, as we saw earlier, the amount earned on an account increases as the compounding frequency increases. Table 5 shows that the increase from annual to semi-annual compounding is larger than the increase from monthly to daily compounding. This might lead us to ask whether this pattern will continue. Examine the value of $1 invested at 100% interest for 1 year, compounded at various frequencies, listed in Table 5. Frequency: letter 1D434, letter 1D45B equals 1 plus 1 letter 1D45B, letter 1D45B value annually, 1 plus 11, $2 semi-annually, 1 plus 12, $2. 25 quarterly, 1 plus 14, $2. $441,406 monthly, 1 plus 112, $2. 613,035 daily, 1 plus 1,365, $2. $714,567 hourly, 1 plus 18,760, $8,762. 718,127 once per minute, 1 plus 1,525,600, $525,600, $2. 718,279 once per second, 1 plus 130, 1,530,6,000, 30, 1,536,000, $2. 718,282. Table 5. these values appear to be approaching a limit as n increases without bound. In fact, as n gets larger and larger, the expression 1 plus 1 letter 1d45b, letter 1d45b approaches a number used so frequently in mathematics that it has its own name. The letter, this value is an irrational number, which means that its decimal expansion goes on forever without repeating. Its approximation to 6 decimal places is shown below. The number e, the letter e, represents the irrational number, 1 plus 1 letter 1d45b, letter 1d45b, a s letter 1d45b, INCRE a SES. Without bound, the letter e is used as a base for many real-world exponential models. To work with base e, we use the approximation, letter 1d452 approximately 2, 718,282. The constant was named by the Swiss mathematician Leonhard Euler, 1707-1783, who first investigated and discovered many of its properties. Example 10, using a calculator to find powers of e. Calculate E3. 14. Round to 5 decimal places. Solution on a calculator, press the button labeled letter 1d452 letter 1d465. The window shows letter 1d452. Type 314 and then close parenthesis. Press enter. Rounding to 5 decimal places, E3, 14 approximately 23, 10,387. Caution, many scientific calculators have an exp button, which is used to enter numbers in scientific notation. It is not used to find powers of e. Try it 10, use a calculator to find letter 1d452 minus 0. 5 round to 5 decimal places. Investigating continuous growth, so far we have worked with rational bases for exponential functions. For most real-world phenomena, however, e is used as the base for exponential functions. Exponential models that use e as the base are called continuous growth or decay models. We see these models in finance, computer science, and most of the sciences, such as physics, toxicology, and fluid dynamics. The continuous growth decay formula for all real numbers t and all positive numbers a and r. Continuous growth or decay is represented by the formula letter 1d434. Letter 1d461 equals letter 1d44, letter 1d452, letter 1d45f, letter 1d461, where a is the initial value. R is the continuous growth rate per unit time, and t is the elapsed time. If letter 1d45f 0, then the formula represents continuous growth. If letter 1d45f 0, then the formula represents continuous decay. For business applications, the continuous growth formula is called the continuous compounding formula and takes the form letter 1d434. Letter 1d461 equals letter 1d443, letter 1d452, letter 1d45f, letter 1d461, where p is the principal or the initial invested. R is the growth or interest rate per unit time, and t is the period or term of the investment. How to, given the initial value, rate of growth or decay, and time t, solve a continuous growth or decay function. Use the information in the problem to determine a, the initial value of the function. Use the information in the problem to determine the growth rate r if the problem refers to continuous growth, then letter 1d45f 0. If the problem refers to continuous decay, then letter 1d45f 0. Use the information in the problem to determine the time t. Substitute the given information into the continuous growth formula and solve for letter 1d434, letter 1d461. Example 11. Calculating continuous growth. A person invested $1,000 in an account earning a nominal 10% per year, compounded continuously. How much was in the account at the end of 1 year? Solution: since the account is growing in value, this is a continuous compounding problem with growth rate letter 1d45f equals 0. 10. The initial investment was $1,000, so letter 1d443 equals 1,000. We use the continuous compounding formula to find the value after letter 1d461 equals 1 year. Letter 1d434. Letter 1d461 equals letter 1d443, letter 1d452, letter 1d45f, letter 1d461 equals 1,000, letter 1d452 0. 1 approximately 1,105, 17. Use the continuous compounding formula. Substitute known values for P, R, and T. Use a calculator to approximate. The account is worth $1,105, $17 after 1 year. Try it 11. A person invests $100,000 at a nominal 12% interest per year, compounded continuously. What will be the value of the investment in 30 years? Example 12. Calculating continuous decay radon, decays at a continuous rate of 3% per day. How much will 100 mg of radon decay to in 3 days? Solution: since the substance is decaying, the rate, 3%, is negative. So, letter 1d45f equals minus 0. 173. The initial amount of radon-222 was 100 mg, so letter 1d44e equals 100. We use the continuous decay formula to find the value after letter 1d461 equals 3 days. Letter 1d434. Letter 1d461 equals letter 1d44, letter 1d45 to letter 1d45f, letter 1d461 equals 100, letter 1d452 minus 0. 173, 3 approximately 59. 5115. Use the continuous growth formula. Substitute known values for A, R, and T. Use a calculator to approximate. So 59. 5115 mg of radon-222 will remain. Try it 12 using the data in example 12. How much radon-222 will remain after 1 year? Media access: these online resources for additional instruction and practice with exponential functions. Exponential growth function, compound interest, 6.1 section, exercises verbal 1. Explain why the values of an increasing exponential function will eventually overtake the values of an increasing linear function. 2. Given a formula for an exponential function, is it possible to determine whether the function grows or decays exponentially just by looking at the formula? Explain. 3. The Oxford Dictionary defines the word nominal as a value that is stated or expressed, but not necessarily corresponding exactly to the real value. 3. Develop a reasonable argument for why the term nominal rate is used to describe the annual percentage rate of an investment account that compounds interest. Algebraic for the following exercises, identify whether the statement represents an exponential function. Explain. For the average annual population increase of a pack of wolves is 25. 5. A population of bacteria decreases by a factor of 18 every 24 hours. 6. The value of a coin collection has increased by 325% annually over the last 20 years. 7. For each training session, a personal trainer charges his clients $5 less than the previous training session. 8. The height of a projectile at time t is represented by the function letter 210e, letter 1d461, equals minus 4. 9t2 plus 18t plus 40. For the following exercises, consider this scenario. For each year t, the population of a forest of trees is represented by the function letter 1d434, letter 1d461 equals 115, 1, 0, 25, letter 1d461. In a neighboring forest, the population of the same type of tree is represented by the function letter 1d435, letter 1d461 equals 82, 1, 0, 29, letter 1d461. Round answers to the nearest whole number. 9. Which forest population is growing at a faster rate? 10. Which forest had a greater number of trees initially? By how many? 11. Assuming the population growth models continue to represent the growth of the forests, which forest will have a greater number of trees after 20 years? By how many? 12. Assuming the population growth models continue to represent the growth of the forests, which forest will have a greater number of trees after 100 years? By how many? 13. Discuss the above results from the previous 4 exercises. Assuming the population growth models continue to represent the growth of the forests, which forest will have the greater number of trees in the long run? Why? What are some factors that might influence the long-term validity of the exponential growth model? For the following exercises, determine whether the equation represents exponential growth, exponential decay, or neither. Explain. 14. Letter 1d466 equals 300, 1 minus letter 1 d461, 515. Letter 1 d466 equals 221. 0, 6. Letter 1 d465, 16. Letter 1 d466 equals 16. 5, 1. 0, 25. 1 letter 1 d465, 17. Letter 1 d466 equals 11, 701, 0. 97. Letter 1 d461 for the following exercises, find the formula for an exponential function that passes through the 2 points given. 18. 6 and 3750, 19. 2000 and 220, 20. Minus 1, 32 and 324, 21. Minus 2, 6 and 31, 22. 31 and 54, for the following exercises, determine whether the table could represent a function that is linear, exponential, or neither. If it appears to be exponential, find a function that passes through the points. 23. x1, 2, 3, 4, letter 1 d4, 5, 3, letter 1 d4, 6, 5, 70, 40, 10 minus 20, 24. x1, 2, 3, 4, letter 2, 1, 0, e, letter 1 d4, 6, 5, 70, 49, 34. 324, 125. x1, 2, 3, 4, letter 1 d4, 5a, letter 1 d4, 6, 5, 80, 61, 42. 925. 61, 26. x1, 2, 3, 4, letter 1 d4, 5, 3, letter 1 d4, 6, 5, 10, 20, 40, 80, 27. x1, 2, 3, 4, letter 1 d4, 5, 4, letter 1 d4, 6, 5, 25, 2, 7, 25, 12. 5. For the following exercises, use the compound interest formula, letter 1 d434, letter 1 d461 equals letter 1 d443, 1 plus letter 1 d45f, letter 1 d45b, letter 1 d45b, letter 1 d461. 28. After a certain number of years, the value of an investment account is represented by the equation letter 1 d434 equals 10,250, 1 plus 0, 0412, 120. What is the value of the account? 29. What was the initial deposit made to the account in the previous exercise? 30. How many years had the account from the previous exercise been accumulating interest? 31. An account is opened with an initial deposit of $6,500 and earns 3.6% interest compounded semi-annually. What will the account be worth in 20 years? 32. How much more would the account in the previous exercise have been worth if the interest were compounding weekly? 33. Solve the compound interest formula for the principal, P34. Use the formula found in the previous exercise to calculate the initial deposit of an account that is worth $14,472. $74 after earning 5% interest compounded monthly for 5 years. Round to the nearest dollar. 35. How much more would the account in the previous 2 exercises be worth if it were earning interest for 5 more years? 36. Use properties of rational exponents to solve the compound interest formula for the interest rate, R37. Use the formula found in the previous exercise to calculate the interest rate for an account that was compounded semi-annually, had an initial deposit of $9,000, and was worth $13,373. 53 after 10 years. 38. Use the formula found in the previous exercise to calculate the interest rate for an account that was compounded monthly, had an initial deposit of $5,500, and was worth $38,455 after 30 years. For the following exercises, determine whether the equation represents continuous growth, continuous decay, or neither. Explain. 39. Letter 1 d466 equals 3,742, letter 1 d452, 0. 75 t40. Letter 1 d466 equals 150, letter 1 d452, 3. 25 t41. Letter 1 d466 equals 2. 25, letter 1 d452, minus 2, letter 1 d461, 42. Suppose an investment account is opened with an initial deposit of $12,000 earning 7.2% interest compounded continuously. How much will the account be worth after 30 years? 43. How much less would the account from exercise 42 be worth after 30 years if it were compounded monthly instead? Numeric for the following exercises, evaluate each function. Round answers to 4 decimal places if necessary. 44. Letter 1 D453, letter 1 D465 equals 2, 5 letter 1 D465, for letter 1 D453, minus 3, 45. Letter 1 D453, letter 1 D465, equals minus 42 letter 1 D465 plus 3, for letter 1 D453, minus 1, 46. Letter 1 D453, letter 1 D465 equals letter 1 D45 to letter 1 D465, for letter 1 D453, 3, 47. Letter 1 D453, letter 1 D465, equals minus 2 letter 1 D45 to letter 1 D465 minus 1, for letter 1 D453, minus 1, 48. Letter 1 D453, letter 1 D465 equals 2, 7, 4 minus letter 1 D465 plus 1 plus 1. 5, for letter 1 D453, minus 2, 49. Letter 1 D453, letter 1 D465 equals 1, 2 e to letter 1 D465 minus 0. 3, for letter 1 D453, 3, 50. Letter 1 D453, letter 1 D465, equals minus 32, 3 minus letter 1 D465 plus 32, for letter 1 D453, 2. Technology for the following exercises. Use a graphing calculator to find the equation of an exponential function given the points on the curve. 51, 3 and 3,375, 52, 3,222, 62, and 1,077, 456, 53, 2,029, 495, and 150,730, 89, 54, 52, 909, and 130, 555, 11,310, 35, and 25,356,365. 2. Extensions 56. The annual percentage yield, APY, of an investment account is a representation of the actual interest rate earned on a compounding account. It is based on a compounding period of 1 year. Show that the APY of an account that compounds monthly can be found with the formula APY equals 1 plus letter 1 D45F 12, 12 minus 1, 57. Repeat the previous exercise to find the formula for the APY of an account that compounds daily. Use the results from this and the previous exercise to develop a function letter 1 D43C, letter 1 D45B, for the APY of any account that compounds n times per year. 58. Recall that an exponential function is any equation written in the form letter 1 D453, letter 1 D465, equals letter 1 D44E, letter 1 D44F, letter 1 D465, such that a and b are positive numbers and letter 1 D44F not equal to 1. Any positive number b can be written as letter 1 D44F equals letter 1 D45 to letter 1 D45B for some value of n. Use this fact to rewrite the formula for an exponential function that uses the number e as a base. 59. In an exponential decay function, the base of the exponent is a value between 0 and 1. Thus, for some number letter 1 D44F1, the exponential decay function can be written as letter 1 D453. Letter 1 D465 equals letter 1 D44E, 1 letter 1 D44F, letter 1 D465. Use this formula, along with the fact that letter 1 D44F equals letter 1 D45 to letter 1 D45B, to show that an exponential decay function takes the form letter 1 D453. Letter 1 D465 equals letter 1 D44E, letter 1 D452, minus letter 1 D45B, letter 1 D465 for some positive number n. 60. The formula for the amount A in an investment account with a nominal interest rate R at any time t is given by letter 1 D434. Letter 1 D461 equals letter 1 D44E, letter 1 D452, letter 1 D45F, letter 1 D461, where A is the amount of principal initially deposited into an account that compounds continuously. Prove that the percentage of interest earned to principal at any time t can be calculated with the formula letter 1 D43C. Letter 1 D461 equals letter 1 D45 letter 1 D45F, letter 1 D461 minus 1. Real-world applications 61. The fox population in a certain region has an annual growth rate of 9% per year. In the year 2012, there were 23,900 fox counted in the area. What is the fox population predicted to be in the year 2020? 62. A scientist begins with 100 milligrams of a radioactive substance that decays exponentially. After 35 hours, 50 mg of the substance remains. How many milligrams will remain after 54 hours? 63. In the year 1985, a house was valued at $110,000. By the year 2005, the value had appreciated to $145,000. What was the annual growth rate between 1985 and 2005? Assume that the value continued to grow by the same percentage. What was the value of the house in the year 2010? 64. A car was valued at $38,000 in the year 2007. By 2013, the value had depreciated to $11,000. If the car's value continues to drop by the same percentage, what will it be worth by 2017? 65. Jalen wants to save $54,000 for a down payment on a home. How much will he need to invest in an account with 8.2% APR, compounding daily, in order to reach his goal in 5 years? 66. Kyoko has $10,000 that she wants to invest. Her bank has several investment accounts to choose from, all compounding daily. Her goal is to have $15,000 by the time she finishes graduate school in 6 years. To the nearest hundredth of a percent, what should her minimum annual interest rate be in order to reach her goal? Hint: solve the compound interest formula for the interest rate. 67. Alyssa opened a retirement account with 7.25% APR in the year 2000. Her initial deposit was $13,500. How much will the account be worth in 2025 if interest compounds monthly? How much more would she make if interest compounded continuously? 68. An investment account with an annual interest rate of 7% was opened with an initial deposit of $4,000. Compare the values of the account after 9 years when the interest is compounded annually, quarterly, monthly, and continuously. Learning objectives: graph exponential functions. Graph exponential functions using transformations. As we discussed in the previous section, exponential functions are used for many real-world applications such as finance, forensics, computer science, and most of the life sciences. Working with an equation that describes a real-world situation gives us a method for making predictions. Most of the time, however, the equation itself is not enough. We learn a lot about things by seeing their pictorial representations, and that is exactly why graphing exponential equations is a powerful tool. It gives us another layer of insight for predicting future events. Graphing exponential functions. Before we begin graphing, it is helpful to review the behavior of exponential growth. Recall the table of values for a function of the form letter 1 d453, letter 1 d465, equals letter 1 d44f letter 1 d465, whose base is greater than 1. We'll use the function letter 1 d453, letter 1 d465, equals 2 letter 1 d465. Observe how the output values in table 1 change as the input increases by 1. X minus 3 minus 2 minus 1 0 1 2 3 letter 1 d453, letter 1 d465, equals 2 letter 1 d465 18 14 12 1 2 4 8 table 1. Each output value is the product of the previous output and the base, 2. We call the base 2 the constant ratio. In fact, for any exponential function with the form letter 1 d453, letter 1 d465, equals letter 1 d44 letter 1 d44f letter 1 d465, b is the constant ratio of the function. This means that as the input increases by 1, the output value will be the product of the base and the previous output, regardless of the value of a. Notice from the table that the output values are positive for all values of x. As x increases, the output values increase without bound, and as x decreases, the output values grow smaller, approaching 0. Figure 1 shows the exponential growth function letter 1 d453, letter 1 d465, equals 2 letter 1 d465. Graph of the exponential function 2x with labeled points at -3, 1 8, -2 a quarter, -1 a half, 0 1, 1, 2, 2, 4, and 3, 8. The graph notes that the x-axis is an asymptote. Figure 1 notice that the graph gets close to the x-axis, but never touches it. The domain of letter 1D453, letter 1D465, equals 2 letter 1D465 is all real numbers. The range is 0, infinity, and the horizontal asymptote is letter 1D466 equals 0. To get a sense of the behavior of exponential decay, we can create a table of values for a function of the form letter 1D453. Letter 1D465 equals letter 1D44f letter 1D465, whose base is between 0 and 1. We'll use the function letter 1D454, letter 1D465 equals 12, letter 1D465. Observe how the output values in Table 2 change as the input increases by 1. X minus 3 minus 2 minus 1 0 1 2 3 letter 1D454, letter 1D465 equals 12, letter 1D465 8 4 2 1 12 14 18 Table 2 again. Because the input is increasing by 1, each output value is the product of the previous output and the base or constant ratio 12. Notice from the table that the output values are positive for all values of x. As x increases, the output values grow smaller, approaching 0. And as x decreases, the output values grow without bound. Figure 2 shows the exponential decay function letter 1D454, letter 1D465 equals 12, letter 1D465. Graph of decreasing exponential function, 1/2x with labeled points at minus 3, 8, minus 2, 4, minus 1, 2, 0, 1, 1, 1, 2, 2, 1, 4, and 3, 1, 8. The graph notes that the x-axis is an asymptote. Figure 2, the domain of letter 1D454, letter 1D465 equals 12, letter 1D465 is all real numbers. The range is 0, infinity, and the horizontal asymptote is letter 1D466 equals 0. Characteristics of the graph of the parent function, letter 1D453. Letter 1D465 equals letter 1D44f letter 1D465, an exponential function with the form letter 1D453, letter 1D465, equals letter 1D44f letter 1D465, letter 1D44f 0, letter 1D44f not equal to 1, has these characteristics. 1-to-1 function horizontal asymptote, letter 1D466 equals 0 domain, infinity infinity range, 0 infinity x-intercept, none y-intercept. 1, increasing if letter 1D44f 1, decreasing if letter 1D44f 1. Figure 3 compares the graphs of exponential growth and decay functions. Graph of two functions where the first graph is of a function of f, x, bx when b1, and the second graph is of the same function when b is 0, b1. Both graphs have the points 0, 1, and 1 be labeled. Figure 3 how to given an exponential function of the form letter 1D453, letter 1D465, equals letter 1D44f letter 1D465, graph the function. Create a table of points. Plot at least 3 points from the table, including the y-intercept 1. Draw a smooth curve through the points. State the domain, minus infinity, infinity, the range, 0, infinity, and the horizontal asymptote, letter 1D466 equals 0. Example 1, sketching the graph of an exponential function of the form fx equals bx. Sketch a graph of letter 1D453, letter 1D465 equals 0. 25x. State the domain, range, and asymptote. Solution before graphing, identify the behavior and create a table of points for the graph. Since letter 1D44f equals 0, 25 is between 0 and 1, we know the function is decreasing. The left tail of the graph will increase without bound, and the right tail will approach the asymptote letter 1D466 equals 0. Create a table of points as in Table 3. X minus 3 minus 2 minus 1 0, 1 2 3 letter 1D453, letter 1D465, equals 0. 25x 64 16 4 1 0, 25 0. 6 25 0 15,625 Table 3, plot the y-intercept, 1, along with 2 other points. We can use minus 1 4 and 10, 25. Draw a smooth curve connecting the points as in Figure 4. Graph of the decaying exponential function f(x) equals 0. 25x with labeled points at -1, 4, 0, 1, and 1, 0, 25. Figure 4. The domain is -infinity, infinity. The range is 0, infinity. The horizontal asymptote is letter 1d466 equals 0. Try it 1. Sketch the graph of letter 1d453, letter 1d465 equals 4 letter 1d465. State the domain, range, and asymptote. Graphing transformations of exponential functions, transformations of exponential graphs behave similarly to those of other functions. Just as with other parent functions, we can apply the 4 types of transformations: shifts, reflections, stretches, and compressions to the parent function letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 without loss of shape. For instance, just as the quadratic function maintains its parabolic shape when shifted, reflected, stretched, or compressed, the exponential function also maintains its general shape regardless of the transformations applied. Graphing a vertical shift, the first transformation occurs when we add a constant d to the parent function letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465, giving us a vertical shift d units in the same direction as the sign. For example, if we begin by graphing a parent function, letter 1d453, letter 1d465 equals 2 letter 1d465, we can then graph 2 vertical shifts alongside it, using letter 1d451 equals 3. The upward shift, letter 1d454, letter 1d465 equals 2 letter 1d465 plus 3, and the downward shift, letter 210e, letter 1d465 equals 2 letter 1d465 minus 3. Both vertical shifts are shown in figure 5. Graph of 3 functions, g, x, equals 2x plus 3 in blue with an asymptote at y equals 3, f, x, equals x in orange with an asymptote at y equals 0, and h, x, equals 2x3 with an asymptote at y equals 3. Note that each function's transformations are described in the text. Figure 5, observe the results of shifting letter 1d453, letter 1d465, equals 2 letter 1d465 vertically. The domain, -infinity, infinity, remains unchanged. When the function is shifted up 3 units to letter 1d454, letter 1d465 equals 2 letter 1d465 plus 3. The y-intercept shifts up 3 units to 4. The asymptote shifts up 3 units to letter 1d466 equals 3. The range becomes 3, infinity. When the function is shifted down 3 units to letter 210e, letter 1d465 equals 2 letter 1d465 minus 3. The y-intercept shifts down 3 units to 0, minus 2. The asymptote also shifts down 3 units to letter 1d466 equals minus 3. The range becomes minus 3, infinity. Graphing a horizontal shift, the next transformation occurs when we add a constant c to the input of the parent function letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465, giving us a horizontal shift c units in the opposite direction of the sign. For example, if we begin by graphing the parent function letter 1d453, letter 1d465 equals 2 letter 1d465, we can then graph 2 horizontal shifts alongside it, using letter 1d450 equals 3. The shift left, letter 1d454, letter 1d465 equals 2 letter 1d465 plus 3, and the shift right, letter 210e, letter 1d465 equals 2 letter 1d465 minus 3. Both horizontal shifts are shown in figure 6. Graph of 3 functions, g, x equals 2, x plus 3 in blue, fx equals x in orange, and hx equals 2, x3. Each function's asymptotes are at y equals 0. Note that each function's transformations are described in the text. Figure 6, observe the results of shifting letter 1d453, letter 1d465, equals 2 letter 1d465 horizontally. The domain, -infinity, infinity, remains unchanged. The asymptote, letter 1d466 equals 0, remains unchanged. The y-intercept shifts such that, when the function is shifted left 3 units to letter 1d454, letter 1d465 equals 2 letter 1d465 plus 3, the y-intercept becomes 8. This is because 2 letter 1d465 plus 3 equals 8 2 letter 1d465, so the initial value of the function is 8. When the function is shifted right 3 units to letter 210e, letter 1d465 equals 2 letter 1d465 minus 3, the y-intercept becomes 18. Again, see that 2 letter 1d465 minus 3 equals 18 2 letter 1d465, so the initial value of the function is 18. Shifts of the parent function f, x, equals bx for any constant c and d. The function letter 1d453, letter 1d465, equals letter 1d44f letter 1d465 plus letter 1d450 plus letter 1d451 shifts the parent function letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 vertically d units, in the same direction of the sign of d, horizontally c units. In the opposite direction of the sign of c, the y-intercept becomes 0. Letter 1d44f letter 1d450 plus letter 1d451. The horizontal asymptote becomes letter 1d466 equals letter 1d451. The range becomes letter 1d451 infinity. The domain minus infinity infinity remains unchanged. How to given an exponential function with the form letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 plus letter 1d450 plus letter 1d451. Graph the translation. Draw the horizontal asymptote letter 1d466 equals letter 1d451. Identify the shift as minus letter 1d450, letter 1d451. Shift the graph of letter 1d453, letter 1d465, equals letter 1d44f letter 1d465, left c units if c is positive, and right c units if c is negative. Shift the graph of letter 1d453, letter 1d465, equals letter 1d44f letter 1d465 up d units if d is positive, and down d units if d is negative. State the domain, minus infinity, infinity, the range, letter 1d451, infinity, and the horizontal asymptote letter 1d466 equals letter 1d451. Example 2, graphing a shift of an exponential function graph, letter 1d453, letter 1d465, equals 2 letter 1d465 plus 1 minus 3. State the domain, range, and asymptote. Try it 2 graph letter 1d453, letter 1d465, equals 2 letter 1d465 minus 1 plus 3. State domain, range, and asymptote. How to given an equation of the form letter 1d453, letter 1d465, equals letter 1d44f letter 1d465 plus letter 1d450 plus letter 1d451 for x. Use a graphing calculator to approximate the solution. Press y equals. Enter the given exponential equation in the line headed y1 equals. Enter the given value for letter 1d453, letter 1d465 in the line headed y2 equals. Press window. Adjust the y-axis so that it includes the value entered for y2 equals. Press graph to observe the graph of the exponential function along with the line for the specified value of letter 1d453, letter 1d465. To find the value of x, we compute the point of intersection. Press second, then calc. Select intersect and press enter 3 times. The point of intersection gives the value of x for the indicated value of the function. Example 3, approximating the solution of an exponential equation, solve 42 equals 1. 2 5-letter 1d465 plus 2. 8 graphically. Round to the nearest thousandth. Try it 3 solve 4 equals 7. 85 1. 15 letter 1d465 minus 2. 27 graphically. Round to the nearest thousandth. Graphing a stretch or compression, while horizontal and vertical shifts involve adding constants to the input or to the function itself. A stretch or compression occurs when we multiply the parent function letter 1d453, letter 1d465, equals letter 1d44f letter 1d465 by a constant letter 1d44e0. For example, if we begin by graphing the parent function letter 1d453, letter 1d465, equals 2 letter 1d465, We can then graph the stretch, using letter 1d44e equals 3. To get letter 1d454, letter 1d465 equals 3, 2 letter 1d465 as shown on the left in figure 8, and the compression, using letter 1d44e equals 13. To get letter 210e, letter 1d465 equals 13, 2 letter 1d465 as shown on the right in figure 8. Two graphs where graph A is an example of vertical stretch and graph B is an example of vertical compression. Figure 8a, letter 1d454, letter 1d465 equals 3, 2 letter 1d465 stretches the graph of letter 1d453, letter 1d465, equals 2 letter 1d465 vertically by a factor of 3. B, letter 210e, letter 1d465, equals 13, 2 letter 1d465 compresses the graph of letter 1d453, letter 1d465, equals 2 letter 1d465 vertically by a factor of 13. Stretches and compressions of the parent function, letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 for any factor letter 1d44e 0. The function letter 1d453, letter 1d465, equals letter 1d44e letter 1d44f. Letter 1d465 is stretched vertically by a factor of a if letter 1d44e1, is compressed vertically by a factor of a if letter 1d44e1, has a y-intercept of 0a, has a horizontal asymptote at letter 1d466 equals 0, a range of 0, infinity, and a domain of -infinity, infinity, which are unchanged from the parent function. Example 4, graphing the stretch of an exponential function, sketch a graph of letter 1d453, letter 1d465, equals 4, 12, letter 1d465. State the domain, range, and asymptote. Solution before graphing, identify the behavior and key points on the graph. Since letter 1d44f equals 12 is between 0 and 1, the left tail of the graph will increase without bound as x decreases, and the right tail will approach the x-axis as x increases. Since letter 1d44e equals 4, the graph of letter 1d453, letter 1d465 equals 12, letter 1d465 will be stretched by a factor of 4. Create a table of points as shown in table 4. x minus 3 minus 2 minus 1 0, 1 2 3 letter 1d453, letter 1d465 equals 4, 12 letter 1d465 32 16 8 4 2 1 0. 5 table 4 plot the y-intercept 4 along with two other points. We can use -1 8 and 12. Draw a smooth curve connecting the points as shown in figure 9. Graph of the function fx equals 4 1/2 x with an asymptote at y equals 0. Labeled points in the graph are -1 8 0 4 and 1 2. Figure 9, the domain is -infinity, infinity. The range is 0, infinity. The horizontal asymptote is letter 1d466 equals 0. Try at 4 sketch the graph of letter 1d453, letter 1d465, equals 12 4 letter 1d465. State the domain, range, and asymptote. Graphing reflections in addition to shifting, compressing, and stretching a graph, we can also reflect it about the x-axis or the y-axis. When we multiply the parent function, letter 1d453, letter 1d465 equals letter 1d44f letter 1d465 by -1, we get a reflection about the x-axis. When we multiply the input by -1, we get a reflection about the y-axis. For example, if we begin by graphing the parent function letter 1d453, letter 1d465, equals 2 letter 1d465, we can then graph the two reflections alongside it. The reflection about the x-axis, letter 1d454, letter 1d465, equals -2 letter 1d465, is shown on the left side of figure 10, and the reflection about the y-axis, letter 210e, letter 1d465 equals 2 minus letter 1d465, is shown on the right side of figure 10. Two graphs where graph A is an example of a reflection about the x-axis, and graph B is an example of a reflection about the y-axis. Figure 10, A, letter 1d454, letter 1d465, equals -2 letter 1d465 reflects the graph of letter 1d453, letter 1d465 equals 2 letter 1d465 about the x-axis. B, letter 1d454, letter 1d465 equals 2 minus letter 1d465 reflects the graph of letter 1d453, letter 1d465 equals 2 letter 1d465 about the y-axis. Reflections of the parent function, letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465, the function letter 1d453. Letter 1d465 equals minus letter 1d44f letter 1d465 reflects the parent function letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 about the x-axis. Has a y-intercept of 0, minus 1. Has a range of minus infinity, 0. Has a horizontal asymptote at letter 1d466 equals 0 and domain of minus infinity, infinity, which are unchanged from the parent function. The function letter 1d453, letter 1d465, equals letter 1d44f minus letter 1d465 reflects the parent function letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 about the y-axis. Has a y-intercept of 1, a horizontal asymptote at letter 1d466 equals 0, a range of 0, infinity, and a domain of minus infinity, infinity, which are unchanged from the parent function. Example 5. Writing and graphing the reflection of an exponential function. Find and graph the equation for a function, letter 1d454, letter 1d465, that reflects letter 1d453, letter 1d465 equals 14, letter 1d465 about the x-axis. State its domain, range, and asymptote. Solution: since we want to reflect the parent function letter 1d453, letter 1d465 equals 14, letter 1d465 about the x-axis, we multiply letter 1d453, letter 1d465 by minus 1 to get letter 1d454, letter 1d465 equals minus 14 letter 1d465. Next, we create a table of points as in table 5. X minus 3 minus 2 minus 1 0, 1 2 3, letter 1d454, letter 1d465 equals minus 14 letter 1d465 minus 64 minus 16 minus 4 minus 0, 25 minus 0, 6 25 minus 0, 156. Table 5. Plot the y-intercept 0, minus 1, along with two other points. We can use minus 1 minus 4 and 1 minus 0, 25. Draw a smooth curve connecting the points. Graph of the function gx equals 0, 25, x, with an asymptote at y equals 0. Labeled points in the graph are minus 1, minus 4, 0, minus 1, and 1. 25. Figure 11. The domain is minus infinity, infinity. The range is minus infinity, 0. The horizontal asymptote is letter 1d466 equals 0. Try it 5. Find and graph the equation for a function, letter 1d454, letter 1d465. That reflects letter 1d453, letter 1d465 equals 1. 25x, about the y-axis. State its domain, range, and asymptote, summarizing translations of the exponential function. Now that we have worked with each type of translation for the exponential function, we can summarize them in Table 6 to arrive at the general equation for translating exponential functions. Transformations of the parent function, letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465. Transformation form. Shift. Horizontally, letter 1d450. Units to the left. Vertically, letter 1d451. Units up. Letter 1d453. Letter 1d465 equals letter 1d44f letter 1d465 plus letter 1d450 plus letter 1d451. Stretch and compress. Stretch if letter 1d44e1. Compression if 0 letter 1d44e1. Letter 1d453. Letter 1d465 equals letter 1d44 letter 1d44f letter 1d465. Reflect about the x-axis. Letter 1d453. Letter 1d465 equals minus letter 1d44f letter 1d465. Reflect about the y-axis. Letter 1d453. Letter 1d465 equals letter 1d44f minus letter 1d465 equals 1 letter 1d44f, letter 1d465. General equation for all transformations. Letter 1 D453. Letter 1 D465 equals letter 1 D44 letter 1 D44F letter 1 D465 plus letter 1 D450 plus letter 1 D451. Table 6. Translations of exponential functions. A translation of an exponential function has the form letter 1 D453. Letter 1 D465 equals letter 1 D44 letter 1 D44F letter 1 D465 plus letter 1 D450 plus letter 1 D451. 6. 1. Where the parent function, letter 1 D466 equals letter 1 D44F letter 1 D465, letter 1 D44F1, is shifted horizontally, letter 1 D450, units to the left, stretched vertically by a factor of letter 1 D44E, if letter 1 D44E 0, compressed vertically by a factor of letter 1 D44E, if 0, letter 1 D44E 1, shifted vertically, letter 1 D451, units, reflected about the x-axis when letter 1 D44E 0. Note the order of the shifts, transformations, and reflections follow the order of operations. Example 6. Writing a function from a description. Write the equation for the function described below. Give the horizontal asymptote, the domain, and the range. Letter 1 D453, letter 1 D465 equals letter 1 D452 letter 1 D465, is vertically stretched by a factor of 2, reflected across the y-axis, and then shifted up 4 units. Solution. We want to find an equation of the general form letter 1 D453. Letter 1 D465 equals letter 1 D44 letter 1 D44F letter 1 D465 plus letter 1 D450 plus letter 1 D451. We use the description provided to find letter 1 D44E, B, C, and letter 1 D451. We are given the parent function letter 1 D453, letter 1 D465 equals letter 1 D452 letter 1 D465, so letter 1 D44F equals letter 1 D452. The function is stretched by a factor of 2, so letter 1 D44E equals 2. The function is reflected about the y-axis. We replace letter 1 D465 with minus letter 1 D465 to get letter 1 D452 minus letter 1 D465. The graph is shifted vertically 4 units, so letter 1 D451 equals 4. Substituting in the general form we get letter 1 D453. Letter 1 D465 equals letter 1 D44 letter 1 D44F letter 1 D465 plus letter 1 D450 plus letter 1 D451 equals 2 letter 1 D452 minus letter 1 D465 plus 0 plus 4 equals 2 letter 1 D452 minus letter 1 D465 plus 4. The domain is minus infinity. Infinity. The range is 4 infinity. The horizontal asymptote is letter 1 D466 equals 4. Try it 6. Write the equation for function described below. Give the horizontal asymptote, the domain, and the range. Letter 1 D453. Letter 1 D465 equals letter 1 D45 to letter 1 D465 is compressed vertically by a factor of 13, reflected across the x-axis, and then shifted down 2 units. Media. Access this online resource for additional instruction and practice with graphing exponential functions. Graph exponential functions. 6-2 section exercises. Verbal. 1. What role does the horizontal asymptote of an exponential function play in telling us about the end behavior of the graph? 2. What is the advantage of knowing how to recognize transformations of the graph of a parent function algebraically? Algebraic. 3. The graph of letter 1 D453, letter 1 D465 equals 3 letter 1 D465 is reflected about the y-axis and stretched vertically by a factor of 4. What is the equation of the new function, letter 1 D454, letter 1 D465? State its y-intercept, domain, and range. For the graph of letter 1 D453, letter 1 D465 equals 12 minus letter 1 D465 is reflected about the y-axis and compressed vertically by a factor of 15. What is the equation of the new function, letter 1 D454, letter 1 D465? State its y-intercept, domain, and range. 5. The graph of letter 1 D453, letter 1 D465 equals 10 letter 1 D465 is reflected about the x-axis and shifted upward 7 units. What is the equation of the new function, letter 1d454, letter 1d465? State its y-intercept, domain, and range. 6. The graph of letter 1d453, letter 1d465 equals 1. 68, letter 1d465, is shifted right 3 units, stretched vertically by a factor of 2, reflected about the x-axis, and then shifted downward 3 units. What is the equation of the new function, letter 1d454, letter 1d465? State its y-intercept to the nearest thousandth, domain, and range. 7. The graph of plus 4 is shifted downward 4 units and then shifted left 2 units, stretched vertically by a factor of 4, and reflected about the x-axis. What is the equation of the new function, letter 1d454, letter 1d465? State its y-intercept, domain, and range. Graphic. For the following exercises, graph the function and its reflection about the y-axis on the same axes and give the y-intercept. 8. Letter 1d453, letter 1d465 equals 3. 12. Letter 1d465. 9. Letter 1d454, letter 1d465 equals -2, 0. 25. Letter 1d465. 10. Letter 210e, letter 1d465 equals 6, 1. 75 minus letter 1d465. For the following exercises, graph each set of functions on the same axes. 11. Letter 1d453, letter 1d465 equals 3, 14. Letter 1d465. Letter 1d454, letter 1d465 equals 3, 2. Letter 1d465. And letter 210e, letter 1d465 equals 3, 4. Letter 1d465. 12. Letter 1d453, letter 1d465 equals 14, 3. Letter 1d465. Letter 1d454, letter 1d465 equals 2, 3. Letter 1d465. And letter 210e, letter 1d465 equals 4, 3. Letter 1d465. For the following exercises, match each function with one of the graphs in Figure 12. Graph of 6 exponential functions, Figure 12. 13. Letter 1d453, letter 1d465 equals 2, 0. 69. Letter 1d465. 14. Letter 1d453, letter 1d465 equals 2, 1. 28. Letter 1d465. 15. Letter 1d453, letter 1d465 equals 2, 0. 81. Letter 1d465. 16. Letter 1d453, letter 1d465 equals 4, 1. 28. Letter 1d465. 17. Letter 1d453, letter 1d465 equals 2, 1. 59. Letter 1d465. 18. Letter 1d453, letter 1d465 equals 4, 0. 69. Letter 1d465. For the following exercises, use the graphs shown in Figure 13. All have the form letter 1d453, letter 1d465 equals letter 1d44, letter 1d44f, letter 1d465. Graph of 6 exponential functions, Figure 13. 19. Which graph has the largest value for letter 1d44f? 20. Which graph has the smallest value for letter 1d44f? 21. Which graph has the largest value for letter 1d44e? 22. Which graph has the smallest value for letter 1d44e? For the following exercises, graph the function and its reflection about the x-axis on the same axes. 23. Letter 1d453, letter 1d465 equals 12, 4. Letter 1d465. 24. Letter 1d453, letter 1d465 equals 3, 0. 75. Letter 1d465 minus 1. 25. Letter 1d453, letter 1d465 equals -4, 2. Letter 1d465 plus 2. For the following exercises, graph the transformation of letter 1d453. Letter 1d465 equals 2. Letter 1d465. Give the horizontal asymptote, the domain, and the range. 26. Letter 1d453, letter 1d465 equals 2 minus letter 1d465. 27. Letter 210e, letter 1d465 equals 2. Letter 1d465 plus 3. 28. Letter 1d453, letter 1d465 equals 2. Letter 1d465 minus 2. For the following exercises, describe the end behavior of the graphs of the functions. 29. Letter 1d453, letter 1d465 equals -5, 4 letter 1 d465 -1. 30, letter 1 d453, letter 1 d465, equals 3, 12 letter 1 d465 -2. 31, letter 1 d453, letter 1 d465, equals 3, 4 minus letter 1 d465 plus 2. For the following exercises, start with the graph of letter 1 d453, letter 1 d465, equals 4 letter 1 d465. Then write a function that results from the given transformation. 32. Shift letter 1 d453, letter 1 d465, 4 units upward. 33. Shift letter 1 d453, letter 1 d465, 3 units downward. 34. Shift letter 1 d453, letter 1 d465, 2 units left. 35. Shift letter 1 d453, letter 1 d465, 5 units right. 36. Reflect letter 1 d453, letter 1 d465. About the x-axis. 37. Reflect letter 1 d453, letter 1 d465. About the y-axis. For the following exercises, each graph is a transformation of letter 1 d466 equals 2 letter 1 d465. Write an equation describing the transformation. 38. Graph of f, x equals 2x with the following translations: vertical stretch of 4, a reflection about the x-axis, and a shift up by 139. Graph of f, x equals 2x with the following translations: a reflection about the x-axis and a shift up by 340. Graph of f, x equals 2x with the following translations: vertical stretch of 2, a reflection about the x-axis and y-axis, and a shift up by 3. For the following exercises, find an exponential equation for the graph. 41. Graph of f, x equals 3x with the following translations: vertical stretch of 2, a reflection about the x-axis, and a shift up by 742. Graph of f, x equals 1/2x with the following translations: vertical stretch of 2 and a shift down by 4. Numeric. For the following exercises, evaluate the exponential functions for the indicated value of letter 1 d465. 43. Letter 1 d454, letter 1 d465, equals 13, 7 letter 1 d465 minus 2. For letter 1 d4546, 44. Letter 1 d453, letter 1 d465, equals 4, 2 letter 1 d465 minus 1 minus 2. For letter 1 d4535, 45. Letter 210e, letter 1 d465, equals minus 12, 12 letter 1 d465 plus 6. For letter 210e minus 7. Technology. For the following exercises, use a graphing calculator to approximate the solutions of the equation. Round to the nearest thousandth. 46. Minus 50 equals minus 12 minus letter 1 d465. 47. 116 equals 14, 18 letter 1 d465. 48. 12 equals 2, 3 letter 1 d465 plus 1. 49. 5 equals 3, 12 letter 1 d465 minus 1 minus 2. 50. Minus 30 equals minus 4, 2 letter 1 d465 plus 2 plus 2. Extensions. 51. Explore and discuss the graphs of letter 1 d439, letter 1 d465 equals, letter 1 d44f letter 1 d465, and letter 1 d43a, letter 1 d465 equals, 1 letter 1 d44f letter 1 d465. Then make a conjecture about the relationship between the graphs of the functions letter 1 d44f letter 1 d465 and 1 letter 1 d44f letter 1 d465 for any real number letter 1 d44f0. 52. Prove the conjecture made in the previous exercise. 53. Explore and discuss the graphs of letter 1 d453, letter 1 d465 equals 4 letter 1 d465, letter 1 d454, letter 1 d465 equals 4 letter 1 d465 minus 2. And then make a conjecture about the relationship between the graphs of the functions letter 1 d44f letter 1 d465 and 1 letter 1 d44f letter 1 d45b, letter 1 d44f letter 1 d465 for any real number n and real number letter 1 d44f0. 54. Prove the conjecture made in the previous exercise. Learning objectives. In this section, you will convert from logarithmic to exponential form, convert from exponential to logarithmic form, evaluate logarithms, Use common logarithms. Use natural logarithms. Photo of the aftermath of the earthquake in Japan with a focus on the Japanese flag. Figure 1 devastation of March 11, 2011 earthquake in Honshu, Japan. Credit: Daniel Pierce. In 2010, a major earthquake struck Haiti, destroying or damaging over 285,000 homes. 1 year later, another, stronger earthquake devastated Honshu, Japan, destroying or damaging over 332,000 buildings, 5 like those shown in Figure 1. Even though both caused substantial damage, the earthquake in 2011 was 100 times stronger than the earthquake in Haiti. How do we know? The magnitudes of earthquakes are measured on a scale known as the Richter scale. The Haitian earthquake registered a 7.0 on the Richter scale 6, whereas the Japanese earthquake registered a 9.07. The Richter scale is a base 10 logarithmic scale. In other words, an earthquake of magnitude 8 is not twice as great as an earthquake of magnitude 4. It is 108 minus 4 equals 104 equals 10, 0, 0, 0 times as great. In this lesson, we will investigate the nature of the Richter scale and the base 10 function upon which it depends. Converting from logarithmic to exponential form. In order to analyze the magnitude of earthquakes or compare the magnitudes of two different earthquakes, we need to be able to convert between logarithmic and exponential form. For example, suppose the amount of energy released from one earthquake were 500 times greater than the amount of energy released from another. We want to calculate the difference in magnitude. The equation that represents this problem is 10 letter 1d465 equals 500, where letter 1d465 represents the difference in magnitudes on the Richter scale. How would we solve for letter 1d465? We have not yet learned a method for solving exponential equations. None of the algebraic tools discussed so far is sufficient to solve 10 letter 1d465 equals 500. We know that 102 equals 100, and 103 equals 1000, so it is clear that letter 1d465 must be some value between 2 and 3. Since letter 1d466 equals 10 letter 1d465 is increasing, we can examine a graph, as in Figure 2, to better estimate the solution. Graph of the intersections of the equations y equals 10x and y equals 500. Figure 2. Estimating from a graph, however, is imprecise. To find an algebraic solution, we must introduce a new function. Observe that the graph in Figure 2 passes the horizontal line test. The exponential function letter 1d466 equals letter 1d44f letter 1d465 is 1 to 1, so its inverse, letter 1d465 equals letter 1d44f letter 1d466, is also a function. As is the case with all inverse functions, we simply interchange letter 1d465 and letter 1d466 and solve for letter 1d466 to find the inverse function. To represent letter 1d466 as a function of letter 1d465, we use a logarithmic function of the form letter 1d466 equals log letter 1d44f, letter 1d465. The base letter 1d44f, logarithm of a number, is the exponent by which we must raise letter 1d44f. To get that number, we read a logarithmic expression as the logarithm with base letter 1d44f of letter 1d465 is equal to letter 1d466, or, simplified, log base letter 1d44f of letter 1d465 is letter 1d466. We can also say letter 1d44f raised to the power of letter 1d466 is letter 1d465, because logs are exponents. For example, the base 2 logarithm of 32 is 5, because 5 is the exponent we must apply to 2 to get 32. Since 25 equals 32, we can write log 232 equals 5. We read this as log base 2 of 32 is 5. We can express the relationship between logarithmic form and its corresponding exponential form as follows. Log letter 1d44f. Letter 1d465 equals letter 1d466, letter 1d44f letter 1d466 equals letter 1d465, letter 1d44f 0. Letter 1d44f not equal to 1. Note that the base letter 1d44f is always positive. Because logarithm is a function, it is most correctly written as log letter 1d44f, letter 1d465. using parentheses to denote function evaluation, just as we would with letter 1D453, letter 1D465. However, when the input is a single variable or number, it is common to see the parentheses dropped and the expression written without parentheses, as log letter 1D44f, letter 1D465. Note that many calculators require parentheses around the letter 1D465. We can illustrate the notation of logarithms as follows. Notice that, comparing the logarithm function and the exponential function, the input and the output are switched. This means letter 1D466 equals log letter 1D44f, letter 1D465, and letter 1D466 equals letter 1D44f, letter 1D465. Are inverse functions. Definition of the logarithmic function. A logarithm base, letter 1D44f, of a positive number, letter 1D465, satisfies the following definition. For letter 1D4650, letter 1D44f0, letter 1D44f not equal to 1. Letter 1D466 equals log letter 1D44f. Letter 1D465 is equivalent to letter 1D44f, letter 1D466 equals letter 1D465, where we read log letter 1D44f, letter 1D465, as the logarithm with base letter 1D44f of letter 1D465, or the log base letter 1D44f of letter 1D465. The logarithm letter 1D466 is the exponent to which letter 1D44f must be raised to get letter 1D465. Also, since the logarithmic and exponential functions switch the letter 1D465 and letter 1D466, values, the domain and range of the exponential function, are interchanged for the logarithmic function. Therefore, the domain of the logarithm function with base letter 1D44f is 0, infinity. The range of the logarithm function with base letter 1D44f is -infinity, infinity. Q&A. Can we take the logarithm of a negative number? No, because the base of an exponential function is always positive. No power of that base can ever be negative. We can never take the logarithm of a negative number. Also, we cannot take the logarithm of 0. Calculators may output a log of a negative number when in complex mode, but the log of a negative number is not a real number. How to? Given an equation in logarithmic form, log letter 1D44f, letter 1D465 equals letter 1D466. Convert it to exponential form. Examine the equation letter 1D466 equals log letter 1D44f, letter 1D465, and identify letter 1D44f, letter 1D466, nd letter 1D465. Rewrite log letter 1D44f, letter 1D465 equals letter 1D466 as example 1. Converting from logarithmic form to exponential form. Write the following logarithmic equations in exponential form. A log 6, 6 square equals 12. B log 3, 9 equals 2. Solution. First, identify the values of letter 1D44f, letter 1D466, and nd letter 1D465. Then, write the equation in the form letter 1D44f, letter 1D466 equals letter 1D465. A log 6, 6 square equals 12. Here, letter 1D44f equals 6, letter 1D466 equals 12, and letter 1D465 equals 6. Square. Therefore, the equation log 6, 6 square equals 12, is equivalent to 612 equals 6 square. B log 3, 9 equals 2. Here, letter 1D44f equals 3, letter 1D466 equals 2, and letter 1D465 equals 9. Therefore, the equation log is equivalent to 32 equals 9. Try it 1. Write the following logarithmic equations in exponential form. A log 10, 1 0 0 0, 0 0 0 equals 6. B log 5, 25 equals 2. Converting from exponential to logarithmic form. To convert from exponents to logarithms, we follow the same steps in reverse. We identify the base letter 1D44f, exponent letter 1D465, and output letter 1D466. Then we write letter 1D465 equals log letter 1D44f, letter 1D466. Example 2. Converting from exponential form to logarithmic form. Write the following exponential equations in logarithmic form. 23 equals 8, 52 equals 25. 10 minus 4 equals 110. 0, 0, 0. Solution. First, identify the values of letter 1D44F, letter 1D466, and letter 1D465. Then, write the equation in the form letter 1D465 equals log letter 1D44F, letter 1D466. 23 equals 8. Here, letter 1D44F equals 2. And letter 1D466 equals 8. Therefore, the equation 23 equals 8 is equivalent to log 2, 8 equals 3. 52 equals 25. Here, letter 1D44F equals 5. Letter 1D465 equals 2. And letter 1D466 equals 25. Therefore, the equation 52 equals 25 is equivalent to log 5, 25 equals 2. 10 minus 4 equals 110, 0, 0, 0. Here, letter 1D44F equals 10. And letter 1D466 equals 110, 0, 0, 0. Therefore, the equation 10 minus 4 equals 110, 0, 0, 0 is equivalent to log 10, 110, 0, 0, 0 equals minus 4. Try it too. Write the following exponential equations in logarithmic form. A32 equals 9. B53 equals 125. C2 minus 1 equals 12. Evaluating logarithms. Knowing the squares, cubes, and roots of numbers allows us to evaluate many logarithms mentally. For example, consider log 28. We ask, to what exponent must 2 be raised in order to get 8? Because we already know 23 equals 8. It follows that log 28 equals 3. Now consider solving log 749 and log 327. Mentally, we ask, to what exponent must 7 be raised in order to get 49? We know 72 equals 49. Therefore, log 749 equals 2. We ask, to what exponent must 3 be raised in order to get 27? We know 33 equals 27. Therefore, log 327 equals 3. Even some seemingly more complicated logarithms can be evaluated without a calculator. For example, let's evaluate log 2349. Mentally, we ask, to what exponent must 23 be raised in order to get 49? We know 22 equals 4, and 32 equals 9. So 23, 2 equals 49. Therefore, log 23, 49 equals 2. How to? Given a logarithm of the form letter 1D466 equals log letter 1D44F, letter 1D465. Evaluate it mentally. Rewrite the argument letter 1D465 as a power of letter 1D44F. Use previous knowledge of powers of letter 1D44F. Identify letter 1D466 by asking, to what exponent should letter 1D44F be raised in order to get letter 1D465? Example 3. Solving logarithms mentally. Solve letter 1D466 equals log 4, 64. Without using a calculator. Solution. First, we rewrite the logarithm in exponential form. 4 letter 1D466 equals 64. Next, we ask, to what exponent must 4 be raised in order to get 64? We know 43 equals 64. Therefore, log 64 4 equals 3. Try it 3. Solve letter 1D466 equals log 121, 11. Without using a calculator. Example 4. Evaluating the logarithm of a reciprocal. Evaluate letter 1D466 equals log 3, 127. Without using a calculator. Solution. First, we rewrite the logarithm in exponential form. 3 letter 1D466 equals 127. Next, we ask, to what exponent must 3 be raised in order to get 127? We know 33 equals 27, but what must we do to get the reciprocal, 127? Recall from working with exponents that letter 1D44F minus letter 1D44E equals 1 letter 1D44F letter 1D44E. We use this information to write 3 minus 3 equals 133 equals 127. Therefore, log 3, 127 equals minus 3. Try it 4. Evaluate letter 1D466 equals log 2, 132. Without using a calculator, using common logarithms. Sometimes you may see a logarithm writ without a base. When you see one written this way, you need to look at the expression before evaluating it. It may be that the base you use doesn't matter. If you find it in computer science, it often means log 2, letter 1d465. However, in mathematics it almost always means the common logarithm of 10. In other words, the expression log, letter 1d465, often means log 10, letter 1d465. Definition of the common logarithm. A common logarithm is a logarithm with base 10. We can also write log 10, letter 1d465, simply as log, letter 1d465. The common logarithm of a positive number, letter 1d465, satisfies the following definition. For letter 1d4650, letter 1d466 equals log. Letter 1d465 is equivalent to 10 letter 1d466 equals letter 1d465. We read log, letter 1d465, as the logarithm with base 10 of letter 1d465, or log base 10 of letter 1d465. The logarithm, letter 1d466, is the exponent to which 10 must be raised to get letter 1d465. Currently, we use log letter 1d44f letter 1d465, lg letter 1d465 as the common logarithm, lb, as the binary logarithm, and ln letter 1d465 as the natural logarithm. Writing lg letter 1d465 without specifying a base is now considered bad form, despite being frequently found in older materials. How to? Given a common logarithm of the form letter 1d466 equals log letter 1d465, evaluate it mentally. Rewrite the argument letter 1d465 as a power of 10, 10 letter 1d466 equals letter 1d465. Use previous knowledge of powers of 10 to identify letter 1d466 by asking to what exponent must 10 be raised in order to get letter 1d465. Example 5. Finding the value of a common logarithm mentally. Evaluate letter 1d466 equals log 1000 without using a calculator. Solution. First, we rewrite the logarithm in exponential form. 10 letter 1d466 equals 1000. Next, we ask, to what exponent must 10 be raised in order to get 1000? We know 103 equals 1000. Therefore, log 1000 equals 3. Try it 5. Evaluate letter 1d466 equals log 1,000,000. How to? Given a common logarithm with the form letter 1d466 equals log letter 1d465, evaluate it using a calculator. Press log, enter the value given for letter 1d465, followed by press enter. Finding the value of a common logarithm using a calculator. Evaluate letter 1d466 equals log 321 to 4 decimal places using a calculator. Solution. Press log, enter 321, followed by press enter. Rounding to 4 decimal places, log 321 approximately 2, 5065. Analysis. Note that 102 equals 100, and that 103 equals 1000. Since 321 is between 100 and 1000, we know that log 321 must be between log 100 and log 1000. This gives us the following: 1002, 3212, 5065, 10003. Try it 6. Evaluate letter 1d466 equals log 123 to 4 decimal places using a calculator. Example 7. Rewriting and solving a real-world exponential model. The amount of energy released from one earthquake was 500 times greater than the amount of energy released from another. The equation 10 letter 1d465 equals 500 represents this situation, where letter 1d465 is the difference in magnitudes on the Richter scale. To the nearest thousandth, what was the difference in magnitudes? Solution. We begin by rewriting the exponential equation in logarithmic form. 10 letter 1d465 log 500 equals 500 equals letter 1d465. Use the definition of the common log. Next, we evaluate the logarithm using a calculator. Press log, enter 500, followed by press enter. To the nearest thousandth, log 500 approximately 2, 699. The difference in magnitudes was about 2, 699. Try it 7. The amount of energy released from one earthquake was 8, 500 times greater than the amount of energy released from another. The equation 10 letter 1d465 equals 8500 represents this situation, where letter 1d465 is the difference in magnitudes on the Richter scale. To the nearest thousandth, what was the difference in magnitudes? Using natural logarithms, the most frequently used base for logarithms is letter 1d452, the value of which is approximately 271,828. Base letter 1d452. Logarithms are important in calculus and some scientific applications. They are called natural logarithms. The base letter 1d452. Logarithm, log letter 1d452, letter 1d465, has its own notation, ln, letter 1d465. Most values of ln, letter 1d465, can be found only using a calculator. The major exception is that, because the logarithm of 1 is always 0 in any base, ln 1 equals 0. For other natural logarithms, we can use the ln key that can be found on most scientific calculators. We can also find the natural logarithm of any power of letter 1d452. Using the inverse property of logarithms. Definition of the natural logarithm. A natural logarithm is a logarithm with base. We write log letter 1d452, letter 1d465, simply as ln, letter 1d465. The natural logarithm of a positive number, letter 1d465, satisfies the following definition. For letter 1d4650, ln is equivalent to letter 1d452 letter 1d466 equals letter 1d465. We read ln, letter 1d465, as the logarithm with base letter 1d452 of letter 1d465, or the natural logarithm of letter 1d465. The logarithm letter 1d466 is the exponent to which letter 1d452 must be raised to get letter 1d465. Since the functions letter 1d466 equals letter 1d452 letter 1d465, and letter 1d466 equals ln, letter 1d465, are inverse functions, ln, letter 1d452 letter 1d465 equals letter 1d465 for all letter 1d465, and letter 1d452 equals ln, letter 1d465 letter 1d465 for letter 1d4650. How to? Given a natural logarithm with the form letter 1d466 equals ln, letter 1d465, evaluate it using a calculator, press ln, enter the value given for letter 1d465, followed by a press enter, example 8, evaluating a natural logarithm using a calculator. Evaluate letter 1d466 equals ln, 500, to 4 decimal places using a calculator. Solution. Press ln, enter 500, followed by a press enter, rounding to 4 decimal places, ln, 500 approximately 6, 2146. Try at 8. Evaluate ln, minus 500. Media. Access this online resource for additional instruction and practice with logarithms. Introduction to Logarithms. 6.3 Section Exercises. Verbal. 1. What is a base letter 1d44f? Logarithm. Discuss the meaning by interpreting each part of the equivalent equations letter 1d44f letter 1d466 equals letter 1d465, and log letter 1d44f letter 1d465 equals letter 1d466. For letter 1d44f 0, letter 1d44f not equal to 1. 2. How is the logarithmic function letter 1d453, letter 1d465 equals log letter 1d44f letter 1d465 related to the exponential function letter 1d454, letter 1d465 equals letter 1d44f letter 1d465? What is the result of composing these two functions? 3. How can the logarithmic equation log letter 1d44f letter 1d465 equals letter 1d466 be solved for letter 1d465 using the properties of exponents? 4. Discuss the meaning of the common logarithm. What is its relationship to a logarithm with base letter 1d44f, and how does the notation differ? 5. Discuss the meaning of the natural logarithm. What is its relationship to a logarithm with base letter 1d44f, and how does the notation differ? Algebraic. For the following exercises, rewrite each equation in exponential form. 6. Log 4, letter 1d45e, equals letter 1d45a. 7. Log letter 1d44e, letter 1d44f equals letter 1d450. 8. Log 16, letter 1d466, equals letter 1d465. 9. Log letter 1d465, 64 equals letter 1d466. 10. Log letter 1d466, letter 1d465 equals minus 11. 11. Log 15, letter 1d44e equals letter 1d44f. 12. Log letter 1d466, 137 equals letter 1d465. 13. Log 13, 142 equals letter 1d44e. 14. Log letter 1d463 equals letter 1d461. 15. Ln letter 1d464 equals letter 1d45b. For the following exercises, rewrite each equation in logarithmic form. 16. 4 letter 1d465 equals letter 1d466. 17. Letter 1d450 letter 1d451 equals letter 1d458. 18. Letter 1d45a minus 7 equals letter 1d45b. 19. 19 letter 1d465 equals letter 1d466. 20. Letter 1d465 minus 1013 equals letter 1d466. 21. Letter 1d45b, 4 equals 103. 22. 75. Letter 1d45a equals letter 1d45b. 23. Letter 1d466 letter 1d465 equals 39,100. 24. 10 letter 1d44e equals letter 1d44f. 25. Letter 1d45 to letter 1d458 equals letter 210e. For the following exercises, solve for letter 1d465 by converting the logarithmic equation to exponential form. 26. Log 3, letter 1d465 equals 2. 27. Log 2, letter 1d465 equals minus 3. 28. Log 5, letter 1d465 equals 2. 29. Log 3, letter 1d465 equals 3. 30. Log 2, letter 1d465 equals 6. 31. Log 9, letter 1d465 equals 12. 32. Log 18, letter 1d465 equals 2. 33. Log 6, letter 1d465 equals minus 3. 34. Log letter 1d465 equals 3. 35. Ln letter 1d465 equals 2. For the following exercises, use the definition of common and natural logarithms to simplify. 36. Log. 37. 10 log 32. 38. 2 log. 1. 39. Letter 1d452 ln 1. 6. 40. Ln letter 1d452 minus 5. 3. 41. Letter 1d452 ln 10. 125 plus 4. Numeric. For the following exercises, evaluate the base letter 1d44f. Logarithmic expression without using a calculator. 42. Log 3, 127. 43. Log 6, 6 square. 44. Log 2, 18 plus 4. 45. 6 log 8, 4. For the following exercises, evaluate the common logarithmic expression without using a calculator. 46. Log 10, 0, 0, 0. 47. Log 0, 1. 48. Log 1 plus 7. 49. 2 log 100 minus 3. For the following exercises, evaluate the natural logarithmic expression without using a calculator. 50. Ln, letter 1d452 13. 51. Ln. 52. Ln, letter 1d452 minus 0. 225 minus 3. 53. 25. Ln, letter 1d452 25. Technology. For the following exercises, evaluate each expression using a calculator. Round to the nearest thousandth. 54. Log 0. 4. 55. Ln 15. 56. Ln 45. 57. Log. 58. Ln 2 square. Extensions. 59 is, in the domain of the function letter 1d453, letter 1d465 equals log letter 1d465. If so, what is the value of the function when? Verify the result. 60 is letter 1d453, letter 1d465 equals 0. In the range of the function letter 1d453, letter 1d465 equals log letter 1d465. If so, for what value of letter 1d465? Verify the result. 61. Is there a number letter 1d465 such that ln letter 1d465 equals 2? If so, what is that number? Verify the result. 62. Is the following true? Log 327, log 4, 164 equals -1? Verify the result. 63. Is the following true? ln, letter 1d4521. 725, ln 1 equals 1. 725, verify the result. Real-world applications. 64. The exposure index letter 1d438 letter 1d43c for a camera is a measurement of the amount of light that hits the image receptor. It is determined by the equation letter 1d438 letter 1d43c equals log 2 letter 1d453 to t, where letter 1d453 is the f-stop setting on the camera and letter 1d461 is the exposure time in seconds. Suppose the f-stop setting is 8 and the desired exposure time is 2 seconds. What will the resulting exposure index be? 65. Refer to the previous exercise. Suppose the light meter on a camera indicates in letter 1d438 letter 1d43c of -2, and the desired exposure time is 16 seconds. What should the f-stop setting be? 66. The intensity levels I of two earthquakes measured on a seismograph can be compared by the formula log letter 1d43c, 1 letter 1d43c, 2 equals letter 1d440, 1 minus letter 1d440, 2, where letter 1d440 is the magnitude given by the Richter scale. In August 2009, an earthquake of magnitude 6.1 hit Honshu, Japan. In March 2011, that same region experienced yet another, more devastating earthquake, this time with a magnitude of 9.08. How many times greater was the intensity of the 2011 earthquake? Round to the nearest whole number. Learning objectives in this section, you will identify the domain of a logarithmic function. Graph logarithmic functions. In graphs of exponential functions, we saw how creating a graphical representation of an exponential model gives us another layer of insight for predicting future events. How do logarithmic graphs give us insight into situations? Because every logarithmic function is the inverse function of an exponential function, we can think of every output on a logarithmic graph as the input for the corresponding inverse exponential equation. In other words, logarithms give the cause for an effect. To illustrate, suppose we invest $2,500 in an account that offers an annual interest rate of 5%, compounded continuously. We already know that the balance in our account for any year t can be found with the equation letter 1d434 equals 2,500 letter 1d4520. 5t, but what if we wanted to know the year for any balance? We would need to create a corresponding new function by interchanging the input and the output. Thus, we would need to create a logarithmic model for this situation. By graphing the model, we can see the output year for any input account balance. For instance, what if we wanted to know how many years it would take for our initial investment to double? Figure 1 shows this point on the logarithmic graph, a graph titled Logarithmic Model Showing Years as a Function of the Balance in the Account. The x-axis is labeled account balance and the y-axis is labeled years. The line starts at $25,000 on the first year. The graph also notes that the balance reaches $5,000 near year 14. Figure 1 in this section, we will discuss the values for which a logarithmic function is defined and then turn our attention to graphing the family of logarithmic functions. Finding the domain of a logarithmic function before working with graphs, we will take a look at the domain, the set of input values, for which the logarithmic function is defined. Recall that the exponential function is defined as letter 1d466 equals letter 1d44f letter 1d465 for any real number x and constant letter 1d44f 0. Letter 1d44f not equal to 1, where the domain of y is -infinity, infinity. The range of y is 0, infinity. In the last section, we learned that the logarithmic function letter 1d466 equals log letter 1d44f, letter 1d465, is the inverse of the exponential function letter 1d466 equals letter 1d44f letter 1d465. So, as inverse functions, the domain of letter 1d466 equals log letter 1d44f, letter 1d465, is the range of letter 1d466 equals letter 1d44f letter 1d465, 0, infinity. The range of letter 1d466 equals log letter 1d44f, letter 1d465, is the domain of letter 1d466 equals letter 1d44f, letter 1d465, minus infinity, infinity. Transformations of the parent function letter 1d466 equals log letter 1d44f, letter 1d465, behave similarly to those of other functions. Just as with other parent functions, we can apply the four types of transformations: shifts, stretches, compressions, and reflections. In graphs of exponential functions, we saw that certain transformations can change the range of letter 1d466 equals letter 1d44f, letter 1d465. Similarly, applying transformations to the parent function letter 1d466 equals log letter 1d44f, letter 1d465, can change the domain. When finding the domain of a logarithmic function, therefore, it is important to remember that the domain consists only of positive real numbers. That is, the argument of the logarithmic function must be greater than 0. For example, consider letter 1d453, letter 1d465, equals log 4, 2 letter 1d465 minus 3. This function is defined for any values of x such that the argument, in this case 2 letter 1d465 minus 3, is greater than 0. To find the domain, we set up an inequality and solve for x. 2 letter 1d465 minus 3 0 2 letter 1d465 3 letter 1d465 1. 5 show the argument greater than 0. Add 3. Divide by 2. In interval notation, the domain of letter 1d453, letter 1d465 equals log 4, 2 letter 1d465 minus 3 is 1. 5. Infinity. How to given a logarithmic function, identify the domain. Set up an inequality showing the argument greater than 0. Solve for x, write the domain in interval notation. Example 1, identifying the domain of a logarithmic shift. What is the domain of letter 1d453? Letter 1d465 equals log 2, letter 1d465 plus 3. Solution: the logarithmic function is defined only when the input is positive. So this function is defined when letter 1d465 plus 3 0. Solving this inequality, letter 1d465 plus 3 0, letter 1d465 minus 3, the input must be positive. Subtract 3. The domain of letter 1d453, letter 1d465, equals log 2 letter 1d465 plus 3, is minus 3 infinity. Try it 1. What is the domain of letter 1d453, letter 1d465, equals log 5 letter 1d465 minus 2, plus 1? Example 2, identifying the domain of a logarithmic shift and reflection. What is the domain of letter 1d453, letter 1d465, equals log 5 minus 2 letter 1d465? Solution: the logarithmic function is defined only when the input is positive. So this function is defined when 5 2 letter 1d465 0. Solving this inequality, 5 minus 2 letter 1d465 0 minus 2 letter 1d465 minus 5 letter 1d465 52, the input must be positive. Subtract 5. Divide by minus 2 and switch the inequality. The domain of letter 1d453, letter 1d465, equals log 5 minus 2 letter 1d465 is infinity 52. Try it 2. What is the domain of letter 1d453, letter 1d465, equals log letter 1d465 minus 5, plus 2? Graphing logarithmic functions. Now that we have a feel for the set of values for which a logarithmic function is defined, we move on to graphing logarithmic functions. The family of logarithmic functions includes the parent function letter 1d466 equals log letter 1d44f, letter 1d465, along with all its transformations: shifts, stretches, compressions, and reflections. We begin with the parent function letter 1d466 equals log letter 1d44f, letter 1d465, because every logarithmic function of this form is the inverse of an exponential function with the form letter 1d466 equals letter 1d44f, letter 1d465. Their graphs will be reflections of each other across the line letter 1d466 equals letter 1d465. To illustrate this, we can observe the relationship between the input and output values of letter 1D466 equals 2 letter 1D465, and its equivalent letter 1D465 equals log 2 letter 1D466 in Table 1. X minus 3 minus 2 minus 1 0 1 2 3 2 letter 1D465 equals letter 1D466 18 14 12 1 2 4 8 log 2 letter 1D466 equals letter 1D465 minus 3 minus 2 minus 1 0 1 2 3 Table 1. Using the inputs and outputs from Table 1, we can build another table to observe the relationship between points on the graphs of the inverse functions letter 1D453, letter 1D465 equals 2 letter 1D465 and letter 1D454, letter 1D465 equals log 2 letter 1D465. See Table 2. Letter 1D453, letter 1D465 equals 2 letter 1D465 minus 3, 18, minus 2, 14, minus 1, 12, 0, 1, 1, 2, 2, 4, 3. 8 letter 1D454, letter 1D465 equals log 2 letter 1D465. 18 minus 3, 14 minus 2, 12 minus 1, 1, 0, 2, 1, 4, 2, 8. 3. Table 2, as we'd expect, the x and y coordinates are reversed for the inverse functions. Figure 2 shows the graph of f and g graph of two functions. F, x, equals 2x and g, x equals log 2x, with the line y equals x denoting the axis of symmetry. Figure 2 notice that the graphs of letter 1D453, letter 1D465, equals 2 letter 1D465 and letter 1D454. Letter 1D465 equals log 2 letter 1D465 are reflections about the line letter 1D466 equals letter 1D465. Observe the following from the graph. Letter 1D453, letter 1D465 equals 2 letter 1D465 has a y-intercept at 1, and letter 1D454, letter 1D465 equals log 2 letter 1D465 has an x-intercept at 10. The domain of letter 1D453, letter 1D465 equals 2 letter 1D465 minus infinity infinity is the same as the range of letter 1D454. Letter 1D465 equals log 2 letter 1D465. The range of letter 1D453, letter 1D465 equals 2 letter 1D465. 0, infinity, is the same as the domain of letter 1D454. Letter 1D465 equals log 2 letter 1D465. Characteristics of the graph of the parent function, letter 1D453. Letter 1D465 equals log letter 1D44f, letter 1D465. For any real number x and constant letter 1D44f 0, letter 1D44f not equal to 1, we can see the following characteristics in the graph of letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465. 1-to-1 function vertical asymptote, letter 1D465 equals 0 domain, 0 infinity range, minus infinity infinity x intercept, 10 and key point B1 y-intercept. None increasing if letter 1D44f1 decreasing if 0 letter 1D44f1 see Figure 3. Two graphs of the function f, x equals log b, x, with points 10 and b1. The first graph shows the line when b1, and the second graph shows the line when 0 b1. Figure 3 Figure 4 shows how changing the base b in letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465 can affect the graphs. Observe that the graphs compress vertically as the value of the base increases. Note, recall that the function ln, letter 1D465, has base letter 1D452 approximately 2, 718. Graph of three equations, y equals log 2 x in blue, y equals ln x in orange, and y equals log x in red. The y-axis is the asymptote. Figure 4 the graphs of three logarithmic functions with different bases, all greater than 1. How to given a logarithmic function with the form letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465, graph the function. Draw and label the vertical asymptote, letter 1D465 equals 0. Plot the x-intercept, 10, plot the key point B1. Draw a smooth curve through the points. State the domain, 0, infinity, the range, minus infinity, infinity, and the vertical asymptote, letter 1D465 equals 0. Example 3, graphing a logarithmic function with the form fx equals log x. Graph letter 1D453, letter 1D465 equals log 5, letter 1D465. State the domain, range, and asymptote. Solution before graphing, identify the behavior and key points for the graph. Since letter 1D44f equals 5 is greater than 1, we know the function is increasing. The left tail of the graph will approach the vertical asymptote letter 1D465 equals 0, and the right tail will increase slowly without bound. The x-intercept is 10. The key point, 51, is on the graph. We draw and label the asymptote, plot and label the points, and draw a smooth curve through the points, see figure 5. Graph of fx equals log 5, x with labeled points at 1, 0, and 5, 1. The y-axis is the asymptote. Figure 5, the domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1D465 equals 0. Try it 3, graph letter 1D453, letter 1D465 equals log 15, letter 1D465. State the domain, range, and asymptote. Graphing transformations of logarithmic functions, as we mentioned in the beginning of the section. Transformations of logarithmic graphs behave similarly to those of other parent functions. We can shift, stretch, compress, and reflect the parent function letter 1D466 equals log letter 1D44f, letter 1D465, without loss of shape. Graphing a horizontal shift of f, x equals log x. When a constant c is added to the input of the parent function letter 1D453, letter 1D465 equals letter 1D459, letter 1D45c, letter 1D454, letter 1D44f, letter 1D465. The result is a horizontal shift, c, units in the opposite direction of the sign on c. To visualize horizontal shifts, we can observe the general graph of the parent function letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465, and for letter 1D4500 alongside the shift left, letter 1D454, letter 1D465 equals log letter 1D44f, letter 1D465 plus letter 1D450, and the shift right, letter 210e, letter 1D465 equals log letter 1D44f, letter 1D465 minus letter 1D450. See figure 6. Graph of two functions. The parent function is fx equals log b x, with an asymptote at x equals 0, and g, x equals log b, x plus c, is the translation function with an asymptote at x equals c. This shows the translation of shifting left. Figure 6, horizontal shifts of the parent function letter 1D453, letter 1D465, equals log letter 1D44f, letter 1D465, for any constant c. The function letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465 plus letter 1D450. Shifts the parent function letter 1D466 equals log letter 1D44f, letter 1D465, left c units if letter 1D4500. Shifts the parent function letter 1D466 equals log letter 1D44f, letter 1D465. Right c units if letter 1D4500. Has the vertical asymptote. Has domain minus letter 1D450, infinity. Has range minus infinity, infinity. How to given a logarithmic function with the form letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465 plus letter 1D450. Graph the translation. Identify the horizontal shift. If letter 1D4500, shift the graph of letter 1D453, letter 1D465 equals log letter 1D44f, letter 1D465, left c units. If letter 1D4500, shift the graph of letter 1D453, letter 1D465 equals log letter 1D44f, letter 1d465, write C units. Draw the vertical asymptote letter 1d465 equals minus letter 1d450. Identify 3 key points from the parent function. Find new coordinates for the shifted functions by subtracting c from the x-coordinate. Label the 3 points. The domain is minus letter 1d450, infinity. The range is minus infinity, infinity. And the vertical asymptote is letter 1d465 equals minus letter 1d450. Example 4, graphing a horizontal shift of the parent function, y equals log x. Sketch the horizontal shift letter 1d453. Letter 1d465 equals log 3 letter 1d465 minus 2 alongside its parent function. Include the key points and asymptotes on the graph. State the domain, range, and asymptote. Solution since the function is letter 1d453, letter 1d465 equals log 3, letter 1d465 minus 2, we notice letter 1d465 plus minus 2 equals letter 1d465 2. Thus letter 1d450 equals minus 2, so letter 1d450 0. This means we will shift the function letter 1d453, letter 1d465 equals log 3, letter 1d465, write 2 units. The vertical asymptote is letter 1d465 equals minus 2, or letter 1d465 equals 2. Consider the 3 key points from the parent function, 13 minus 1, 10, and 31. The new coordinates are found by adding 2 to the x-coordinates. Label the points 73 minus 1, 30, and 51. The domain is 2, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 2. Graph of 2 functions. The parent function is y equals log 3, x, with an asymptote at x equals 0 and labeled points at 1, 3, minus 1, 1, 0, and 3, 1. The translation function f(x) equals log 3, x2 has an asymptote at x equals 2 and labeled points at 3, 0, and 5, 1. Figure 7 try it 4 sketch a graph of letter 1d453, letter 1d465, equals log 3, letter 1d465 plus 4, alongside its parent function. Include the key points and asymptotes on the graph. State the domain, range, and asymptote. Graphing a vertical shift of y equals log x when a constant d is added to the parent function letter 1d453, letter 1d465, equals log letter 1d44f, letter 1d465. The result is a vertical shift d units in the direction of the sign on d. To visualize vertical shifts, we can observe the general graph of the parent function letter 1d453, letter 1d465, equals log letter 1d44f, letter 1d465, alongside the shift up. Letter 1d454, letter 1d465, equals log letter 1d44f, letter 1d465, plus letter 1d451 and the shift down. Letter 210e, letter 1d465 equals log letter 1d44f, letter 1d465 minus letter 1d451. See Figure 8. Graph of 2 functions. The parent function is f(x) equals log b x, with an asymptote at x equals 0 and g, x equals log b, x plus d is the translation function with an asymptote at x equals 0. This shows the translation of shifting up. Graph of 2 functions. The parent function is f(x) equals log bx, with an asymptote at x equals 0 and g, x equals log b, x and d is the translation function with an asymptote at x equals 0. This shows the translation of shifting down. Figure 8 vertical shifts of the parent function, letter 1d466 equals log letter 1d44f, letter 1d465, for any constant d. The function letter 1d453, letter 1d465, equals log letter 1d44f, letter 1d465, plus letter 1d451 shifts the parent function letter 1d466 equals log letter 1d44f, letter 1d465, up d units if letter 1d4510. Shifts the parent function letter 1d466 equals log letter 1d44f, letter 1d465, down d units if letter 1d4510. Has the vertical asymptote letter 1d465 equals 0. has domain 0, infinity, has range minus infinity, infinity. How to give a logarithmic function with the form letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465 plus letter 1d451, graph the translation. Identify the vertical shift. If letter 1d4510, shift the graph of letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465, up d units. If letter 1d4510, shift the graph of letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465, down d units. Draw the vertical asymptote letter 1d465 equals 0. Identify 3 key points from the parent function. Find new coordinates for the shifted functions by adding d to the y-coordinate. Label the 3 points. The domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. Example 5, graphing a vertical shift of the parent function y equals log x. Sketch a graph of letter 1d453, letter 1d465 equals log 3, letter 1d465, minus 2 alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. Solution: since the function is letter 1d453, letter 1d465 equals log 3, letter 1d465, minus 2, we will notice letter 1d451 equals 2. Thus letter 1d4510. This means we will shift the function letter 1d453, letter 1d465, equals log 3, letter 1d465, down 2 units. The vertical asymptote is letter 1d465 equals 0. Consider the 3 key points from the parent function, 13 minus 1, 10, and 31. The new coordinates are found by subtracting 2 from the y-coordinates. Label the points 13 minus 3, 1 minus 2, and 3 minus 1. The domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. Graph of 2 functions. The parent function is y equals log 3 x, with an asymptote at x equals 0 and labeled points at 1, 3, minus 1, 1, 0, and 3, 1. The translation function f, x equals log 3. X minus 2 has an asymptote at x equals 0 and labeled points at 1, 0, and 3, 1. Figure 9, the domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. Try it 5, sketch a graph of letter 1d453, letter 1d465 equals log 2, letter 1d465, plus 2 alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. Graphing stretches and compressions of y equals log x when the parent function letter 1d453, letter 1d465, equals log letter 1d44f, letter 1d465, is multiplied by a constant letter 1d440. The result is a vertical stretch or compression of the original graph. To visualize stretches and compressions, we set letter 1d440 1 and observe the general graph of the parent function letter 1d453, letter 1d465, equals log letter 1d44f, letter 1d465, alongside the vertical stretch. Letter 1d454, letter 1d465 equals letter 1d440, log letter 1d44f, letter 1d465, and the vertical compression. Letter 210e. Letter 1d465 equals 1 letter 1d440, log letter 1d44f, letter 1d465. See Figure 10. Graph of 2 functions. The parent function is f x equals log b x, with an asymptote at x equals 0 and g, x equals a log b x, when a 1 is the translation function with an asymptote at x equals 0. The graph note the intersection of the 2 lines at 1, 0. This shows the translation of a vertical stretch. Figure 10, vertical stretches and compressions of the parent function letter 1d466 equals log letter 1d44f, letter 1d465. For any constant letter 1d441, the function letter 1d453, letter 1d465 equals letter 1d44e, log letter 1d44f. Letter 1d465 stretches the parent function letter 1d466 equals log letter 1d44f, letter 1d465, vertically by a factor of a if letter 1d44e1. Compresses the parent function letter 1d466 equals log letter 1d44f, letter 1d465, vertically by a factor of a if 0 letter 1d44e1. Has the vertical asymptote letter 1d465 equals 0. Has the x-intercept 10. Has domain 0 infinity. Has range minus infinity infinity. How to given a logarithmic function with the form letter 1d453. Letter 1d465 equals letter 1d44e, log letter 1d44f, letter 1d465. Letter 1d44e 0, graph the translation. Identify the vertical stretch or compressions. If letter 1d44e 1, the graph of letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465 is stretched by a factor of a units. If letter 1d44e1, the graph of letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465, is compressed by a factor of a units. Draw the vertical asymptote letter 1d465 equals 0. Identify 3 key points from the parent function. Find new coordinates for the shifted functions by multiplying the y-coordinates by a. Label the 3 points. The domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. Example 6, graphing a stretch or compression of the parent function y equals log x. Sketch a graph of letter 1d453, letter 1d465 equals 2 log 4, letter 1d465, alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. Solution since the function is letter 1d453, letter 1d465 equals 2 log 4 letter 1d465, we will notice letter 1d44e equals 2. This means we will stretch the function letter 1d453, letter 1d465 equals log 4 letter 1d465 by a factor of 2. The vertical asymptote is letter 1d465 equals 0. Consider the 3 key points from the parent function, 14 minus 1, 10, and 41. The new coordinates are found by multiplying the y-coordinates by 2. Label the points 14 minus 2, 10, and 42. The domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. See Figure 11. Graph of 2 functions. The parent function is y equals log 4, x, with an asymptote at x equals 0 and labeled points at 1, 0, and 4, 1. The translation function f, x equals 2 log 4, x has an asymptote at x equals 0 and labeled points at 1, 0, and 2, 1. Figure 11. The domain is 0, infinity, the range is minus infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. Try at 6. Sketch a graph of letter 1d453, letter 1d465 equals 12 log 4, letter 1d465, alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. Example 7. Combining a shift and a stretch. Sketch a graph of letter 1d453, letter 1d465 equals 5 log, letter 1d465 plus 2. State the domain, range, and asymptote. Solution. Remember, what happens inside parentheses happens first. First, we move the graph left 2 units, then stretch the function vertically by a factor of 5, as in Figure 12. The vertical asymptote will be shifted to letter 1d465 equals minus 2. The x-intercept will be minus 1, 0. The domain will be minus 2, infinity. 2 points will help give the shape of the graph. Minus 1, 0, and 85. We chose letter 1d465 equals 8 as the x-coordinate of 1 point to graph, because when letter 1d465 equals 8, letter 1d465 plus 2 equals 10, the base of the common logarithm. Graph of 3 functions. The parent function is y equals log x, with an asymptote at x equals 0. The first translation function y equals 5 log x plus 2 has an asymptote at x equals 2. The second translation function y equals log x plus 2 has an asymptote at x equals 2. Figure 12, the domain is -2 infinity, the range is -infinity, infinity, and the vertical asymptote is letter 1d465 equals -2. Try it 7. Sketch a graph of the function letter 1d453, letter 1d465 equals 3 log letter 1d465 minus 2 plus 1. State the domain, range, and asymptote. Graphing reflections of f x equals log x when the parent function letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465 is multiplied by -1. The result is a reflection about the x-axis. When the input is multiplied by -1, the result is a reflection about the y-axis. To visualize reflections, we restrict letter 1d44f1 and observe the general graph of the parent function letter 1d453. Letter 1d465 equals log letter 1d44f, letter 1d465, alongside the reflection about the x-axis. Letter 1d454, letter 1d465, equals minus log letter 1d44f, letter 1d465, and the reflection about the y-axis. Graph of two functions. The parent function is f x equals log b x, with an asymptote at x equals 0 and g x equals log b x, when b1 is the translation function with an asymptote at x equals 0. The graph note the intersection of the two lines at 1, 0. This shows the translation of a reflection about the x-axis. Figure 13, reflections of the parent function letter 1d466 equals log letter 1d44f, letter 1d465. The function letter 1d453, letter 1d465, equals minus log letter 1d44f, letter 1d465, reflects the parent function letter 1d466 equals log letter 1d44f, letter 1d465, about the x-axis, has domain 0, infinity, range -infinity, infinity, and vertical asymptote letter 1d465 equals 0, which are unchanged from the parent function. The function reflects the parent function letter 1d466 equals log letter 1d44f, letter 1d465, about the y-axis, has domain -infinity, 0, has range -infinity, infinity, and vertical asymptote letter 1d465 equals 0, which are unchanged from the parent function. How to given a logarithmic function with the parent function letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465. Graph a translation. If letter 1d453, letter 1d465 equals minus log letter 1d44f, letter 1d465. If letter 1d453, letter 1d465 equals log letter 1d44f, minus letter 1d465, 1. Draw the vertical asymptote, letter 1d465 equals 0. 1. Draw the vertical asymptote, letter 1d465 equals 0. 2. Plot the x-intercept, 10. 2. Plot the x-intercept, 10, 3. Reflect the graph of the parent function letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465, about the x-axis. 3. Reflect the graph of the parent function letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465, about the y-axis. 4. Draw a smooth curve through the points. 4. Draw a smooth curve through the points. 5. State the domain, 0, infinity, the range, -infinity, infinity, and the vertical asymptote letter 1d465 equals 0. 5. State the domain, -infinity, 0, the range, -infinity, infinity, and the vertical asymptote letter 1d465 equals 0. Table 3, Example 8, graphing a reflection of a logarithmic function. Sketch a graph of letter 1d453, letter 1d465, equals log minus letter 1d465, alongside its parent function. Include the key points and asymptote on the graph. State the domain, range, and asymptote. Solution before graphing letter 1d453, letter 1d465, equals log minus letter 1d465, identify the behavior and key points for the graph. Since letter 1d44f equals 10 is greater than 1, we know that the parent function is increasing. Since the input value is multiplied by -1, f is a reflection of the parent graph about the y-axis. Thus, letter 1d453, letter 1d465 equals log minus letter 1d465 will be decreasing as x moves from negative infinity to 0. And the right tail of the graph will approach the vertical asymptote. The x-intercept is -1, 0. We draw and label the asymptote, plot and label the points, and draw a smooth curve through the points. Graph of two functions. The parent function is y equals log x, with an asymptote at x equals 0 and labeled points at 1, 0, and 10, 1. The translation function f(x equals log x) has an asymptote at x equals 0 and labeled points at -1, 0, and -10, 1. Figure 14, the domain is -infinity, 0. The range is -infinity, infinity, and the vertical asymptote is letter 1d465 equals 0. Try it 8 graph letter 1d453, letter 1d465 equals minus log minus letter 1d465. State the domain, range, and asymptote. How to given a logarithmic equation, use a graphing calculator to approximate solutions. Press y equals. Enter the given logarithm equation or equations as y1 equals and, if needed, y2 equals. Press graph to observe the graphs of the curves and use window to find an appropriate view of the graphs, including their point S of intersection. To find the value of x, we compute the point of intersection. Press second, then calc. Select intersect and press enter 3 times. The point of intersection gives the value of x for the point S of intersection. Example 9, approximating the solution of a logarithmic equation, solve 4 ln letter 1d465 plus 1 equals -2 ln letter 1d465 minus 1 graphically. Round to the nearest thousandth. Solution, press y equals and enter 4 ln letter 1d465 plus 1 next to y1 equals. Then enter -2 ln letter 1d465 minus 1 next to y2 equals. For a window, use the values 0 to 5 for x and 10 to 10 for y. Press graph. The graph should intersect somewhere a little to right of letter 1d465 equals 1. For a better approximation, press second, then calc. Select 5, intersect, and press enter 3 times. The x-coordinate of the point of intersection is displayed as 1. 3,380,5,297. Your answer may be different if you use a different window or use a different value for guess. So, to the nearest thousandth, letter 1d465 approximately 1. 339. Try at 9, solve 5 log, letter 1d465 plus 2 equals 4 minus log, letter 1d465, graphically. Round to the nearest thousandth. Summarizing translations of the logarithmic function. Now that we have worked with each type of translation for the logarithmic function, we can summarize each in Table 4 to arrive at the general equation for translating exponential functions. Transformations of the parent function, letter 1d466 equals log letter 1d44f, letter 1d465. Transformation form shift horizontally c units to the left vertically d, units up letter 1d466 equals log letter 1d44f, letter 1d465 plus letter 1d450, plus letter 1d451 stretch, and compress stretch, if letter 1d44e1 compression, if letter 1d44e1. Letter 1d466 equals letter 1d44e, log letter 1d44f, letter 1d465. Reflect about the x-axis, letter 1d466 equals minus log letter 1d44f, letter 1d465. Reflect about the y-axis, letter 1d466 equals log letter 1d44f, minus letter 1d465. General equation for all translations. Letter 1d466 equals letter 1d44e, log letter 1d44f, letter 1d465 plus letter 1d450, plus letter 1d451, Table 4 transformations of logarithmic functions, all transformations of the parent logarithmic function. Letter 1d466 equals log letter 1d44f, letter 1d465. Have the form letter 1d453, letter 1d465 equals letter 1d44e, log letter 1d44f, letter 1d465 plus letter 1d450, plus letter 1d451, where the parent function. Letter 1d466 equals log letter 1d44f, letter 1d465, letter 1d44f1 is shifted vertically up d units, shifted horizontally to the left c units, stretched vertically by a factor of letter 1d44e if letter 1d44e 0, compressed vertically by a factor of letter 1d44e if 0 letter 1d44e 1. Reflected about the x-axis when letter 1d44e 0. For letter 1d453, letter 1d465 equals log minus letter 1d465. The graph of the parent function is reflected about the y-axis. Example 10, finding the vertical asymptote of a logarithm graph. What is the vertical asymptote of letter 1d453, letter 1d465, equals minus 2 log 3, letter 1d465 plus 4, plus 5. Solution: the vertical asymptote is at letter 1d465 equals minus 4. Analysis: the coefficient, the base, and the upward translation do not affect the asymptote. The shift of the curve 4 units to the left shifts the vertical asymptote to letter 1d465 equals minus 4. Try it 10. What is the vertical asymptote of letter 1d453, letter 1d465, equals 3 plus ln, letter 1d465 minus 1. Example 11, finding the equation from a graph, find a possible equation for the common logarithmic function graphed in figure 15. Graph of a logarithmic function with a vertical asymptote at x equals 2 has been vertically reflected and passes through the points minus 1, 1, and 2, minus 1. Figure 15 analysis, we can verify this answer by comparing the function values in Table 5 with the points on the graph in Figure 15. X minus 1, 0, 1, 2, 3, letter 1d453, letter 1d465, 1, 0 minus 0. 58,496 minus 1 minus 1. 3219 x 4, 5, 6, 7, 8, letter 1d453, letter 1d465, minus 1. 5850 minus 1. 80, 74 minus 2 minus 2. 1699 minus 2. 3219 Table 5 try, it 11 give the equation of the natural logarithm graphed in Figure 16. Graph of a logarithmic function with a vertical asymptote at x equals 3 has been vertically stretched by 2 and passes through the points minus 1, minus 1. Figure 16 Q&A, is it possible to tell the domain and range and describe the end behavior of a function just by looking at the graph? Yes, if we know the function is a general logarithmic function. For example, look at the graph in Figure 16. The graph approaches letter 1d465 equals minus 3, or thereabouts, more and more closely, so letter 1d465 equals minus 3 is, or is very close to, the vertical asymptote. It approaches from the right, so the domain is all points to the right, letter 1d465, letter 1d465 minus 3. The range, as with all general logarithmic functions, is all real numbers. And we can see the end behavior because the graph goes down as it goes left and up as it goes right. The end behavior is that as letter 1d465 right minus 3 plus, letter 1d453, letter 1d465 right minus infinity, and as letter 1d465 right infinity, letter 1d453, letter 1d465 right infinity. Media access, these online resources for additional instruction and practice with graphing logarithms. Graph an exponential function and logarithmic function, match graphs with exponential and logarithmic functions, find the domain of logarithmic functions 6. 4 section exercises verbal 1. The inverse of every logarithmic function is an exponential function and vice versa. What does this tell us about the relationship between the coordinates of the points on the graphs of each? 2. What type S of translation S, if any, affect the range of a logarithmic function? 3. What type S of translation S, if any, affect the domain of a logarithmic function? 4. Consider the general logarithmic function letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465. Why can't x be 0? 5. Does the graph of a general logarithmic function have a horizontal asymptote? Explain. Algebraic for the following exercises, state the domain and range of the function. 6. Letter 1d453, letter 1d465 equals log 3, letter 1d465 plus 4, 7. Letter 210e, letter 1d465 equals ln 12 minus letter 1d465, 8. Letter 1d454, letter 1d465 equals log 5, 2 letter 1d465 plus 9 minus 2, 9. Letter 210e, letter 1d465 equals ln 4 letter 1d465 plus 17 minus 5, 10. Letter 1d453, letter 1d465 equals log 212 minus 3 letter 1d465 minus 3 for the following exercises, state the domain and the vertical asymptote of the function. 11. Letter 1d453, letter 1d465 equals log letter 1d44f, letter 1d465 minus 5, 12. Letter 1d454, letter 1d465 equals ln 3 minus letter 1d465, 13. Letter 1d453, letter 1d465 equals log 3 letter 1d465 plus 1, 14. Letter 1d453, letter 1d465 equals 3 log minus letter 1d465 plus 2, 15. Letter 1d454, letter 1d465 equals minus ln 3 letter 1d465 plus 9 minus 7 for the following exercises. State the domain, vertical asymptote, and end behavior of the function. 16. Letter 1d453, letter 1d465 equals ln 2 minus letter 1d465. 17. Letter 1d453, letter 1d465 equals log letter 1d465 minus 37, 18. Letter 210e, letter 1d465 equals minus log 3 letter 1d465 minus 4 plus 319. Letter 1d454, letter 1d465 equals ln 2 letter 1d465 plus 6 minus 520. Letter 1d453, letter 1d465 equals log 3, 15 minus 5 letter 1d465 plus 6 for the following exercises. State the domain, range, and x and y intercepts if they exist. If they do not exist, write DNE. 21. Letter 210e, letter 1d465 equals log 4, letter 1d465 minus 1 plus 122. Letter 1d453, letter 1d465 equals log 5 letter 1d465 plus 10 plus 323. Letter 1d454, letter 1d465 equals ln minus letter 1d465 minus 224. Letter 1d453, letter 1d465 equals log 2 letter 1d465 plus 2 minus 525. Letter 210e, letter 1d465 equals 3 ln letter 1d465 minus 9 graphical for the following exercises. Match each function in figure 17 with the letter corresponding to its graph. Graph of 5 logarithmic functions. Figure 1726. Letter 1d451, letter 1d465 equals log letter 1d465, 27. Letter 1d453, letter 1d465 equals ln letter 1d465, 28. Letter 1d454, letter 1d465 equals log 2 letter 1d465, 29. Letter 210e, letter 1d465 equals log 5, letter 1d465, 30. Log, for the following exercises, match each function in figure 18 with the letter corresponding to its graph. Graph of 3 logarithmic functions. Figure 1831. Letter 1d453, letter 1d465 equals log 13, letter 1d465, 32. Letter 1d454, letter 1d465 equals log 2 letter 1d465, 33. Letter 210e, letter 1d465 equals log 34, letter 1d465. For the following exercises, sketch the graphs of each pair of functions on the same axis. 34. Letter 1d453, letter 1d465 equals log, letter 1d465, and letter 1d454, letter 1d465 equals 10 letter 1d465, 35. Letter 1d453, letter 1d465 equals log letter 1d465, and letter 1d454, letter 1d465 equals log 12, letter 1d465, 36. Letter 1d453, letter 1d465 equals log 4, letter 1d465, and letter 1d454, letter 1d465 equals ln, letter 1d465, 37. Letter 1d453, letter 1d465 equals letter 1d45 to letter 1d465 and letter 1d454. Letter 1d465 equals ln, letter 1d465 for the following exercises. Match each function in Figure 19 with the letter corresponding to its graph. Graph of three logarithmic functions. Figure 1938. Letter 1d453, letter 1d465 equals log 4 minus letter 1d465 plus 2, 39. Letter 1d454, letter 1d465 equals minus log 4, letter 1d465 plus 2, 40. Letter 210e, letter 1d465 equals log 4 letter 1d465 plus 2. For the following exercises, sketch the graph of the indicated function. 41. Letter 1d453, letter 1d465 equals log 2 letter 1d465 plus 2, 42. Letter 1d453, letter 1d465 equals 2 log letter 1d465, 43. Letter 1d453, letter 1d465 equals ln minus letter 1d465, 44. Letter 1d454, letter 1d465 equals log 4 letter 1d465 plus 16 plus 445. Letter 1d454, letter 1d465 equals log 6 minus 3 letter 1d465 plus 146. Letter 210e, letter 1d465 equals minus 12 ln, letter 1d465 plus 1 minus 3 for the following exercises. Write a logarithmic equation corresponding to the graph shown. 47. Use letter 1d466 equals log 2 letter 1d465 as the parent function. The graph y equals log 2, x, has been reflected over the y-axis and shifted to the right by 148. Use letter 1d453, letter 1d465 equals log 3, letter 1d465 as the parent function. The graph y equals log 3, x has been reflected over the x-axis, vertically stretched by 3 and shifted to the left by 4. 49. Use letter 1d453, letter 1d465 equals log 4, letter 1d465 as the parent function. The graph y equals log 4, x, has been vertically stretched by 3 and shifted to the left by 2. 50. Use letter 1d453, letter 1d465 equals log 5, letter 1d465 as the parent function. The graph y equals log 3, x, has been reflected over the x-axis and y-axis, vertically stretched by 2 and shifted to the right by 5. Technology for the following exercises. Use a graphing calculator to find approximate solutions to each equation. 51. Log letter 1d465 minus 1 plus 2 equals ln letter 1d465 minus 1 plus 252. Log 2 letter 1d465 minus 3 plus 2 equals minus log 2 letter 1d465 minus 3 plus 553 ln letter 1d465 minus 2 equals minus ln letter 1d465 plus 1, 54. 2 ln 5 letter 1d465 plus 1 equals 12 ln minus 5 letter 1d465 plus 155. 13 log 1 minus letter 1d465 equals log letter 1d465 plus 1 plus 13 extensions 56. Let b be any positive real number such that letter 1d44f not equal to 1. What must log letter 1d44f1 be equal to? Verify the result. 57. Explore and discuss the graphs of letter 1d453, letter 1d465 equals log 12, letter 1d465, and letter 1d454, letter 1d465, equals minus log 2 letter 1d465. Make a conjecture based on the result. 58. Prove the conjecture made in the previous exercise. 59. What is the domain of the function letter 1d453, letter 1d465 equals ln, letter 1d465 plus 2 letter 1d465 minus 4. Discuss the result. 60. Use properties of exponents to find the x-intercepts of the function letter 1d453, letter 1d465 equals log letter 1d465 plus 4 letter 1d465 plus 4 algebraically. Show the steps for solving, and then verify the result by graphing the function. Learning objectives. In this section, you will use the product rule for logarithms, use the quotient rule for logarithms, use the power rule for logarithms, expand logarithmic expressions, condense logarithmic expressions, use the change of base formula for logarithms, testing of the pH of hydrochloric acid. Figure 1, the pH of hydrochloric acid is tested with litmus paper. Credit. David Berardin. In chemistry, pH is used as a measure of the acidity or alkalinity of a substance. The pH scale runs from 0 to 14. Substances with a pH less than 7 are considered acidic, and substances with a pH greater than 7 are said to be basic. Our bodies, for instance, must maintain a pH close to 735 in order for enzymes to work properly. To get a feel for what is acidic and what is basic, consider the following pH levels of some common substances. Battery acid, 0.8. Stomach acid, 2.7. Orange juice, 3.3. Pure water, 7 at 25 degrees C. Human blood, 735. Fresh coconut, 7.8. Sodium hydroxide, Li. 14. To determine whether a solution is acidic or basic, we find its pH, which is a measure of the number of active positive hydrogen ions in the solution. The pH is defined by the following formula, where H+ is the concentration of hydrogen ion in the solution. pH equals minus log. Letter 1d43b plus equals log 1 letter 1d43b plus. The equivalence of minus log, letter 1d43b plus, and log 1 letter 1d43b plus is one of the logarithm properties we will examine in this section. Using the product rule for logarithms, recall that the logarithmic and exponential functions undo each other. This means that logarithms have similar properties to exponents. Some important properties of logarithms are given here. First, the following properties are easy to prove. For example, log 51 equals 0, since 50 equals 1, and log 55 equals 1, since 51 equals 5. Next, we have the inverse property. Log letter 1d44f. Letter 1d44f letter 1d465 equals letter 1d465 letter 1d44f. Log letter 1d44f letter 1d465 equals letter 1d465. Letter 1d465 0. For example, to evaluate log 100, we can rewrite the logarithm as log 10, 102, and then apply the inverse property log letter 1d44f. Letter 1d44f letter 1d465 equals letter 1d465. To get log 10, 102 equals 2. To evaluate letter 1d452 ln, 7, we can rewrite the logarithm as letter 1d452, log letter 1d4527, and then apply the inverse property letter 1d44f, log letter 1d44f, letter 1d465 equals letter 1d465. To get letter 1d452, log letter 1d452, 7 equals 7. Finally, we have the one-to-one property. Log letter 1d44f, letter 1d440 equals log letter 1d44f, letter 1d441 if, and only if letter 1d440 equals letter 1d441. We can use the one-to-one property to solve the equation log 3. 3 letter 1d465 equals log 3, 2 letter 1d465 plus 5. For x, since the bases are the same, we can apply the one-to-one property by setting the arguments equal and solving for x. 3 letter 1d465 equals 2 letter 1d465 plus 5 letter 1d465 equals 5. Set the arguments equal. Subtract 2x, but what about the equation log 3? 3 letter 1d465 plus log 3, 2 letter 1d465 plus 5 equals 2. The one-to-one property does not help us in this instance. Before we can solve an equation like this, we need a method for combining terms on the left side of the equation. Recall that we use the product rule of exponents to combine the product of powers by adding exponents. Letter 1d465 letter 1d44 letter 1d465 letter 1d44f equals letter 1d465 letter 1d44e plus letter 1d44f. We have a similar property for logarithms, called the product rule for logarithms, which says that the logarithm of a product is equal to a sum of logarithms. Because logs are exponents and we multiply like bases, we can add the exponents. We will use the inverse property to derive the product rule below. Given any real number x, and positive real numbers m, n, and b, where letter 1d44f not equal to 1, we will show log letter 1d44f, letter 1d440 letter 1d441 equals log letter 1d44f, letter 1d440, plus log letter 1d44f, letter 1d441. Let letter 1d45a equals log letter 1d44f, letter 1d440. And letter 1d45b equals log letter 1d44f, letter 1d441. In exponential form, these equations are letter 1d44f letter 1d45a equals letter 1d440, and letter 1d44f letter 1d45b equals letter 1d441. It follows that log letter 1d44f, letter 1d440 letter 1d441 equals log letter 1d44f. Letter 1d44f, letter 1d45a, letter 1d44f, letter 1d45b equals log letter 1d44f. Letter 1d44f, letter 1d45a, plus letter 1d45b equals letter 1d45a, plus letter 1d45b equals log letter 1d44f. Letter 1d440 plus log letter. For and n, apply the product rule for exponents. Apply the inverse property of logs. Substitute for and n. Note that repeated applications of the product rule for logarithms allow us to simplify the logarithm of the product of any number of factors. For example, consider log letter 1d44f, letter 1d464, letter 1d465, letter 1d466, letter 1d467. Using the product rule for logarithms, we can rewrite this logarithm of a product as the sum of logarithms of its factors. Log letter 1d44f. Letter 1d464, letter 1d465, letter 1d466, letter 1d467 equals log letter 1d44f, letter 1d464 plus log letter 1d44f, letter 1d465 plus log letter 1d44f, letter 1d466 plus log letter 1d44f, letter 1d467. The product rule for logarithms. The product rule for logarithms can be used to simplify a logarithm of a product by rewriting it as a sum of individual logarithms. Log letter 1d44f, letter 1d440, letter 1d441 equals log letter 1d44f, letter 1d440, plus log letter 1d44f, letter 1d4414, letter 1d44f0. How to? Given the logarithm of a product, use the product rule of logarithms to write an equivalent sum of logarithms. Factor the argument completely, expressing each whole number factor as a product of primes. Write the equivalent expression by summing the logarithms of each factor. Example 1. Using the product rule for logarithms, expand log 3, 30 letter 1d465, 3 letter 1d465 plus 4. Solution. We begin by factoring the argument completely, expressing 30 as a product of primes. Log 3, 30 letter 1d465, 3 letter 1d465 plus 4 equals log 3, 235 letter 1d465, 3 letter 1d465 plus 4. Next, we write the equivalent equation by summing the logarithms of each factor. Log 3, 30 letter 1d465, 3 letter 1d465 plus 4 equals log 3, 2 plus log 3, 3, plus log 3, 5, plus log 3, letter 1d465, plus log 3, 3 letter 1d465 plus 4. Try it 1. Expand log letter 1d44f, 8 letter 1d458. Using the quotient rule for logarithms. For quotients, we have a similar rule for logarithms. Recall that we use the quotient rule of exponents to combine the quotient of exponents by subtracting. Letter 1d465, letter 1d44, letter 1d465, letter 1d44f equals letter 1d465, letter 1d44 minus letter 1d44f. The quotient rule for logarithms says that the logarithm of a quotient is equal to a difference of logarithms. Just as with the product rule, we can use the inverse property to derive the quotient rule. Given any real number x, and positive real numbers m, n, and b, where letter 1d44f not equal to 1. We will show log letter 1d44f, letter 1d440 letter 1d441 equals log letter 1d44f, letter 1d440, minus log letter 1d44f, letter 1d441. Let letter 1d45a equals log letter 1d44f, letter 1d440, and letter 1d45b equals log letter 1d44f, letter 1d441. In exponential form, these equations are letter 1d44f, letter 1d45a equals letter 1d440, and letter 1d44f, letter 1d45b equals letter 1d441. It follows that log letter 1d44f, letter 1d440, letter 1d441 equals log letter 1d44f. Letter 1d44f, letter 1d45a, letter 1d44f, letter 1d45b equals log letter 1d44f. Letter 1d44f, letter 1d45a, minus letter 1d45b equals letter 1d45a, minus letter 1d45b equals log letter 1d44f. Letter 1d440 minus log. For mand n, apply the quotient rule for exponents. Apply the inverse property of logs. Substitute for mand n, for example, to expand log 2 letter 1d4652 plus 6 letter 1d465 3 letter 1d465 plus 9. We must first express the quotient in lowest terms. Factoring and canceling, we get log 2 letter 1d4652 plus 6 letter 1d465 3 letter 1d465 plus 9 equals log 2 letter 1d465. Letter 1d465 plus 3 letter 1d465 plus 3 equals log 2 letter 1d465 3 factor the numerator and denominator. Cancel the common factors. Next, we apply the quotient rule by subtracting the logarithm of the denominator from the logarithm of the numerator. Then, we apply the product rule. Log 2 letter 1d465 3 equals log 2 letter 1d465 minus log 3 equals log 2 plus log letter 1d465 minus log 3. The quotient rule for logarithms. The quotient rule for logarithms can be used to simplify a logarithm or a quotient by rewriting it as the difference of individual logarithms. Log letter 1d44f, letter 1d440, letter 1d441 equals log letter 1d44f, letter 1d440 minus log letter 1d44f, letter 1d441. How to? Given the logarithm of a quotient, use the quotient rule of logarithms to write an equivalent difference of logarithms. Express the argument in lowest terms by factoring the numerator and denominator and canceling common terms. Write the equivalent expression by subtracting the logarithm of the denominator from the logarithm of the numerator. Check to see that each term is fully expanded. If not, apply the product rule for logarithms to expand completely. Example 2. Using the quotient rule for logarithms, expand log 2, 15 letter 1d465, letter 1d465 minus 1, 3 letter 1d465 plus 4, 2 minus letter 1d465. Solution. First, we note that the quotient is factored and in lowest terms, so we apply the quotient rule. Log 2, 15 letter 1d465, letter 1d465 minus 1, 3 letter 1d465 plus 4, 2 minus letter 1d465, equals log 2, 15 letter 1d465, letter 1d465 minus 1, minus log 2, 3 letter 1d465 plus 4, 2 minus letter 1d465. Notice that the resulting terms are logarithms of products. To expand completely, we apply the product rule, noting that the prime factors of the factor 15 are 3 and 5. Log 2, 15 letter 1d465, letter 1d465 minus 1, minus log 2. 3 letter 1d465 plus 4, 2 minus letter 1d465, equals log 2 3, plus log 2 5, plus log 2 letter 1d465, plus log 2, letter 1d465 minus 1 minus log 2, 3 letter 1d465 plus 4, plus log 2, 2 minus letter 1d465, equals log 2 3, plus log 2 5, plus log 2, letter 1d465, plus log 2 letter 1d465 minus 1, minus log 2 3 letter 1d465 plus 4 minus log 2 2 minus letter 1d465. Analysis. There are exceptions to consider in this and later examples. First, because denominators must never be 0, This expression is not defined for letter 1d465 equals minus 43, and letter 1d465 equals 2. Also, since the argument of a logarithm must be positive, we note as we observe the expanded logarithm that letter 1d465 0, letter 1d465 1, letter 1d465 minus 43, and letter 1d465 2. Combining these conditions is beyond the scope of this section, and we will not consider them here or in subsequent exercises. Try it too. Expand log 3, 7 letter 1d465 2 plus 21 letter 1d465 7 letter 1d465, letter 1d465 minus 1, letter 1d465 minus 2. Using the power rule for logarithms, we've explored the product rule and the quotient rule, but how can we take the logarithm of a power, such as x2? One method is as follows. Log letter 1d44f. Letter 1d4652 equals log letter 1d44f. Letter 1d465 letter 1d465 equals log letter 1d44f, letter 1d465 plus log letter 1d44f, letter 1d465 equals 2 log letter 1d44f, letter 1d465. Notice that we used the product rule for logarithms to find a solution for the example above. By doing so, we have derived the power rule for logarithms, which says that the log of a power is equal to the exponent times the log of the base. Keep in mind that, although the input to a logarithm may not be written as a power, we may be able to change it to a power. For example, 100 equals 1023 square equals 3121, letter 1d452 equals letter 1d452 minus 1. The power rule for logarithms. The power rule for logarithms can be used to simplify the logarithm of a power by rewriting it as the product of the exponent times the logarithm of the base. Log letter 1d44f. Letter 1d440 letter 1d45b equals letter 1d45b, log letter 1d44f, letter 1d440. How to? Given the logarithm of a power, use the power rule of logarithms to write an equivalent product of a factor and a logarithm. Express the argument as a power, if needed. Write the equivalent expression by multiplying the exponent times the logarithm of the base. Example 3. Expanding a logarithm with powers. Expand log to x5. Solution. The argument is already written as a power, so we identify the exponent, 5, and the base, x, and rewrite the equivalent expression by multiplying the exponent times the logarithm of the base. Log 2, letter 1d4655, equals 5 log to x. Try it 3. Expand ln letter 1d4652. Example 4. Rewriting an expression as a power before using the power rule. Expand log 3, 25. Using the power rule for logs. Try it 4. Expand ln 1 letter 1d4652. Example 5. Using the power rule in reverse. Rewrite 4 ln letter 1d465. Using the power rule for logs to a single logarithm with a leading coefficient of 1. Solution. Because the logarithm of a power is the product of the exponent times the logarithm of the base, it follows that the product of a number and a logarithm can be written as a power. For the expression 4 ln, letter 1d465, we identify the factor 4 as the exponent and the argument x as the base and rewrite the product as a logarithm of a power. 4 ln letter 1d465 equals ln letter 1d4654. Try it 5. Rewrite 2 log 34. Using the power rule for logs to a single logarithm with a leading coefficient of 1. Expanding logarithmic expressions. Taken together, the product rule, quotient rule, and power rule are often called laws of logs. Sometimes we apply more than one rule in order to simplify an expression. For example, log letter 1d44f. 6 letter 1d465 letter 1d466 equals log letter 1d44f. 6 letter 1d465 minus log letter 1d44f, letter 1d466 equals log letter 1d44f. 6 plus log letter 1d44f, letter 1d465 minus log letter 1d44f, letter 1d466. We can use the power rule to expand logarithmic expressions involving negative and fractional exponents. Here is an alternate proof of the quotient rule for logarithms using the fact that a reciprocal is a negative power. Log letter 1d44f, letter 1d434 letter 1d436 equals log letter 1d44f. letter 1 d4 3 4 letter 1 d4 3 6 minus 1 equals log letter 1 d4 4f, letter 1 d4 3 4 plus log letter 1 d4 4f, letter 1 d4 3 6 minus 1 equals log letter 1 d4 4f, letter 1 d4 3 4 plus minus 1 log letter 1 d4 4f, letter 1 d4 3 6 equals L. We can also apply the product rule to express a sum or difference of logarithms as the logarithm of a product. With practice, we can look at a logarithmic expression and expand it mentally, writing the final answer. Remember, however, that we can only do this with products, quotients, powers, and roots, never with addition or subtraction inside the argument of the logarithm. Example 6. Expanding logarithms using product, quotient, and power rules. Rewrite ln, letter 1 d4 6 5 4 letter 1 d4 6 6 7, as a sum or difference of logs. Solution. First, because we have a quotient of two expressions, we can use the quotient rule. ln, letter 1 d4 6 5 4 letter 1 d4 6 6 7 equals ln, letter 1 d4 6 5 4 letter 1 d4 6 6 minus ln 7. Then seeing the product in the first term, we use the product rule. ln, letter 1 d4 6 5 4 letter 1 d4 6 6 minus ln 7 equals ln letter 1 d4 6 5 4 plus ln letter 1 d4 6 6 minus ln 7. Finally, we use the power rule on the first term. ln letter 1 d4 6 5 4 plus ln letter 1 d4 6 6 minus ln 7 equals 4 ln letter 1 d4 6 5 plus ln letter 1 d4 6 6 minus ln 7. Try it 6. Expand log, letter 1 d4 6 5 to y3 z4. Example 7. Using the power rule for logarithms to simplify the logarithm of a radical expression. Expand log, letter 1 d4 6 5 square. Solution. Log, letter 1 d4 6 5 square equals log letter 1 d4 6 5. 12 equals 12 log letter 1 d4 6 5. Try it 7. Expand ln, letter 1 d4 6 5 2 square 3. Q&A. Can we expand ln, letter 1 d4 6 5 2 plus letter 1 d4 6 6 2? No, there is no way to expand the logarithm of a sum or difference inside the argument of the logarithm. Expanding complex logarithmic expressions. Expand log 6, 64 letter 1 d4 6 5 3, 4 letter 1 d4 6 5 plus 1, 2 letter 1 d4 6 5 minus 1. Solution. We can expand by applying the product and quotient rules. Log 6, 64 letter 1 d4 6 5 3, 4 letter 1 d4 6 5 plus 1, 2 letter 1 d4 6 5 minus 1 equals log 664 plus log 6 letter 1 d4 6 5 3 plus log 6, 4 letter 1 d4 6 5 plus 1 minus log 6, 2 letter 1 d4 6 5 minus 1 equals log 626 plus log 6 letter 1 d4 6 5 3 plus log 6, 4 letter 1 d4 6 5 plus 1 minus. The quotient rule. Simplify by writing 64 as 26. Apply the power rule. Try it 8. Expand ln. Letter 1 d4 6 5 minus 1, 2 letter 1 d4 6 5 plus 1 2 square root, letter 1 d4 6 5 2 minus 9. Condensing logarithmic expressions. We can use the rules of logarithms we just learned to condense sums, differences, and products with the same base as a single logarithm. It is important to remember that the logarithms must have the same base to be combined. We will learn later how to change the base of any logarithm before condensing. How to. Given a sum, difference, or product of logarithms with the same base, write an equivalent expression as a single logarithm. Apply the power property first. Identify terms that are products of factors and a logarithm and rewrite each as the logarithm of a power. Next, apply the product property. Rewrite sums of logarithms as the logarithm of a product. Apply the quotient property last. Rewrite differences of logarithms as the logarithm of a quotient. Example 9. Using the product and quotient rules to combine logarithms. Write log 3, 5 plus log 3, 8 minus log 3, 2, as a single logarithm. Solution. Using the product and quotient rules. Log 3, 5 plus log 3, 8 equals log 3, 5, 8 equals log 3, 40. This reduces our original expression to log 3, 40 minus log 3, 2. Then, using the quotient rule, log 3, 40 minus log 3, 2 equals log 3, 402 equals log 3, 20. Try it 9. Condense log 3 minus log 4 plus log 5 minus log 6. Example 10. Condensing complex logarithmic expressions. Condense log 2, letter 1d4652, plus 12 log 2, letter 1d465 minus 1 minus 3 log 2, letter 1d465 plus 3, 2. Solution. We apply the power rule first. Log 2, letter 1d4652, plus 12 log 2, letter 1d465 minus 1 minus 3 log 2. Letter 1d465 plus 3 2 equals log 2 letter 1d465 2 plus log 2 letter 1d465 minus 1 square minus log 2. Letter 1d465 plus 3 6. Next, we apply the product rule to the sum. Log 2 letter 1d465 2 plus log 2 letter 1d465 minus 1 square minus log 2. Letter 1d465 plus 3 6 equals log 2 letter 1d465 to letter 1d465 minus 1 square minus log 2. Letter 1d465 plus 3, 6. Finally, we apply the quotient rule to the difference. Log 2, letter 1d465 to letter 1d465 minus 1 square minus log 2. Letter 1d465 plus 3, 6 equals log 2x to letter 1d465 minus 1 square letter 1d465 plus 3, 6. Try it 10. Rewrite log 5 plus 0. 5 log, letter 1d465, minus log, 7 letter 1d465 minus 1, plus 3 log letter 1d465 minus 1, as a single logarithm. Example 11. Rewriting as a single logarithm. Rewrite 2 log letter 1d465 minus 4 log, letter 1d465 plus 5, plus 1 letter 1d465 log, 3 letter 1d465 plus 5. As a single logarithm. Solution. We apply the power rule first. 2 log letter 1d465 4 log letter 1d465 plus 5, plus 1 letter 1d465 log, 3 letter 1d465 plus 5 equals log, letter 1d465 2, minus log letter 1d465 plus 5, 4 plus log, 3 letter 1d465 plus 5 letter 1d465 minus 1. Next, we rearrange and apply the product rule to the sum. Log letter 1d465 2 minus log letter 1d465 plus 5, 4 plus log. 3 letter 1d465 plus 5 letter 1d465 minus 1. Log equals log letter 1d465 2, 3 letter 1d465 plus 5 letter 1d465 minus 1 minus log letter 1d465 plus 5, 4. Finally, we apply the quotient rule to the difference. Equals log, letter 1d465 2, 3 letter 1d465, plus 5 letter 1d465 minus 1 minus log. Letter 1d465 plus 5, 4 equals log letter 1d465 2, 3 letter 1d465, plus 5 letter 1d465, minus 1 letter 1d465 plus 5, 4. Try it 11. Condense 4, 3 log, letter 1d465, plus log, letter 1d465 plus 5 minus log 2 letter 1d465 plus 3. Example 12. Applying of the laws of logs. Recall that, in chemistry, pH equals minus log letter 1d43b plus. If the concentration of hydrogen ions in a liquid is doubled, what is the effect on pH? Solution. Suppose letter 1d436 is the original concentration of hydrogen ions, and letter 1d443 is the original pH of the liquid. Then letter 1d443 equals log letter 1d436. If the concentration is doubled, the new concentration is 2 letter 1d436. Then the pH of the new liquid is pH equals minus log 2 letter 1d436. Using the product rule of logs, pH equals minus log 2 letter 1d436 equals minus log 2 plus log letter 1d436 equals minus log 2 minus log letter 1d436. Since letter 1d443 equals log letter 1d436, the new pH is pH equals letter 1d443 minus log 2 approximately letter 1d443 minus 0. 301. When the concentration of hydrogen ions is doubled, the pH decreases by about 0. 301. Try it 12. How does the pH change when the concentration of positive hydrogen ions is decreased by half? Using the change of base formula for logarithms, most calculators can evaluate only common and natural logs. In order to evaluate logarithms with a base other than 10 or letter 1d452, we use the change of base formula to rewrite the logarithm as the quotient of logarithms of any other base. When using a calculator, we would change them to common or natural logs. To derive the change of base formula, we use the one-to-one property and power rule for logarithms. Given any positive real numbers letter 1d440, b, and letter 1d45b, where letter 1d45b not equal to 1, and letter 1d44f not equal to 1, we show log letter 1d44f, letter 1d440 equals log letter 1d45b, letter 1d440, log letter 1d45b, letter 1d44f. Let letter 1d466 equals log letter 1d44f, letter 1d440. By exponentiating both sides with base b, we arrive at an exponential form, namely letter 1d44f, letter 1d466 equals letter 1d440. It follows that log letter 1d45b, letter 1d44f, letter 1d466, letter 1d466, log letter 1d45b, letter 1d44f, letter 1d466, log letter 1d44f, letter 1d440 equals log letter 1d45b, letter 1d440 equals log letter 1d45b, letter 1d440 equals log letter 1d45b, letter 1d440, log letter 1d45b, letter 1d44f equals log letter 1d45b, letter 1d440, log letter 1d45b, letter 1d44f. Apply the one-to-one property. Apply the power rule for logarithms. Isolate y substitute for y, for example, to evaluate log 536. Using a calculator, we must first rewrite the expression as a quotient of common or natural logs. We will use the common log. Log 536 equals log 36 log 5, approximately 2. 2266. Apply the change of base formula using base 10. Use a calculator to evaluate to 4 decimal places. The change of base formula. The change of base formula can be used to evaluate a logarithm with any base. For any positive real numbers letter 1d440, b, and letter 1d45b, where letter 1d45b not equal to 1, and letter 1d44f not equal to 1, log letter 1d44f, letter 1d440 equals log letter 1d45b, letter 1d440, log letter 1d45b, letter 1d44f. It follows that the change of base formula can be used to rewrite a logarithm with any base as the quotient of common or natural logs. Log letter 1d44f, letter 1d440 equals ln letter 1d440 ln letter 1d44f, and log letter 1d44f, letter 1d440 equals log letter 1d440, log letter 1d44f. How to? Given a logarithm with the form log letter 1d44f, letter 1d440, use the change of base formula to rewrite it as a quotient of logs with any positive base letter 1d45b, where letter 1d45b not equal to 1. Determine the new base, letter 1d45b, remembering that the common log, letter 1d465, has base 10, and the natural log, ln, letter 1d465, has base letter 1d452. Rewrite the log as a quotient using the change of base formula. The numerator of the quotient will be a logarithm with base letter 1d45b, and argument letter 1d440. The denominator of the quotient will be a logarithm with base letter 1d45b, and argument letter 1d44f. Example 13. Changing logarithmic expressions to expressions involving only natural logs. Change log 53 to a quotient of natural logarithms. Solution. Because we will be expressing log 53 as a quotient of natural logarithms, the new base, letter 1d45b, equals letter 1d452. We rewrite the log as a quotient using the change of base formula. The numerator of the quotient will be the natural log with argument 3. The denominator of the quotient will be the natural log with argument 5. Log letter 1d44f, letter 1d440 log 53 equals ln letter 1d440 ln letter 1d44f equals ln 3 ln 5. Try at 13. Change log 0, 58 to a quotient of natural logarithms, q and a. Can we change common logarithms to natural logarithms? Yes, remember that log 9 means log 109. So log 9 equals ln 9 ln 10. Example 14. Using the change of base formula with a calculator. Evaluate log 2, 10. Using the change of base formula with a calculator. Solution. According to the change of base formula, we can rewrite the log base 2 as a logarithm of any other base. Since our calculators can evaluate the natural log, we might choose to use the natural logarithm, which is the log base letter 1 d452. Log 210 equals ln 10 ln 2 approximately 3. 3219. Apply the change of base formula using base e. Use a calculator to evaluate to 4 decimal places. Try at 14. Evaluate log 5, 100. Using the change of base formula. Media. Access these online resources for additional instruction and practice with laws of logarithms, the properties of logarithms, expand logarithmic expressions, evaluate a natural logarithmic expression. 6-5 section exercises. Verbal. 1. How does the power rule for logarithms help when solving logarithms with the form log letter 1 d44f, letter 1 d465 square letter 1 d45b? 2. What does the change of base formula do? Why is it useful when using a calculator? Algebraic. For the following exercises, expand each logarithm as much as possible. Rewrite each expression as a sum, difference, or product of logs. 3 log letter 1 d44f, 7 letter 1 d465, 2 letter 1 d466. 4. ln 3 letter 1 d44 letter 1 d44f, 5 letter 1 d450. 5 log letter 1 d44f, 1317. 6. Log 4 letter 1 d465 letter 1 d467 letter 1 d464. 7 ln 14 letter 1 d458. 8 log 2 letter 1 d466 letter 1 d465. For the following exercises, condense to a single logarithm if possible. 9 ln 7 plus ln letter 1 d465 plus ln letter 1 d466. 10 log 3 2 plus log 3 letter 1 d44e plus log 3. 11 plus log 3 letter 1 d44f. 11 log letter 1 d44f. 28 minus log letter 1 d44f. 7. 12 ln letter 1 d44e minus ln letter 1 d451 minus ln letter 1 d450. 13 minus log letter 1 d44f. 17. 14 13 ln 8. For the following exercises, use the properties of logarithms to expand each logarithm as much as possible. Rewrite each expression as a sum, difference, or product of logs. 15. Log letter 1 d465, 15 letter 1 d466, 13 letter 1 d467, 19. 16. ln letter 1 d44e minus 2 letter 1 d44f minus 4 letter 1 d4505. 17. Log letter 1 d465, 3 letter 1 d466 minus 4 square. 18. ln letter 1 d466 letter 1 d466, 1 minus letter 1 d466 square. 19. Log letter 1 d465 to y 3 x to letter 1 d466, 5 square 3. For the following exercises, condense each expression to a single logarithm using the properties of logarithms. 20 log 2 letter 1 d4654 plus log 3 letter 1 d4655. 21 ln 6 letter 1 d4659 minus ln 3 letter 1 d4652. 22 2 log letter 1 d465 plus 3 log letter 1 d465 plus 1. 23 log letter 1 d465 minus 12 log letter 1 d466 plus 3 log letter 1 d467. 24 4 log 7 letter 1 d450 plus log 7 letter 1 d44e3 plus log 7 letter 1 d44f3. For the following exercises, rewrite each expression as an equivalent ratio of logs using the indicated base. 25 log to base letter 1 d452. 26 log 1455 875 to base 10. For the following exercises, suppose log 5 6 equals letter 1 d44e and log 5 11 equals letter 1 d44f. Use the change of base formula along with properties of logarithms to rewrite each expression in terms of letter 1 d44e and letter 1 d44f Show the steps for solving. 27. Log 11 5. 28. Log 6 55. 29. Log 11 611. Numeric. For the following exercises, use properties of logarithms to evaluate without using a calculator. 30. Log 3 19 minus 3 log 3 3. 31. 6 log 8 2 plus log 8 64 3 log 8 4. 32. 2 log 9 3 minus 4 log 9 3 plus log 9 1729. For the following exercises, use the change of base formula to evaluate each expression as a quotient of natural logs. Use a calculator to approximate each to 5 decimal places. 33. Log 3 22. 34. Log 8 65. 35. Log 6 5 38. 36. Log 4 152. 37. Log 12 4 7. Extensions. 38. Use the product rule for logarithms to find all letter 1d465 values such that log 12, 2 letter 1d465 plus 6, plus log 12, letter 1d465 plus 2 equals 2. Show the steps for solving. 39. Use the quotient rule for logarithms to find all letter 1d465 values such that log 6, letter 1d465 plus 2 minus log 6, letter 1d465 minus 3 equals 1. Show the steps for solving. 40. Can the power property of logarithms be derived from the power property of exponents using the equation letter 1d44f letter 1d465 equals letter 1d45a? If not, explain why. If so, show the derivation. 41. Prove that log letter 1d44f letter 1d45b equals 1 log letter 1d45b letter 1d44f for any positive integers letter 1d44f 1 and letter 1d45b 1. 42. Does log 81 2401 equals log 3 7? Verify the claim algebraically. Learning objectives. In this section, you will use like bases to solve exponential equations. Use logarithms to solve exponential equations. Use the definition of a logarithm to solve logarithmic equations. Use the one-to-one property of logarithms to solve logarithmic equations. Solve applied problems involving exponential and logarithmic equations. 7 rabbits in front of a brick building. Figure 1 wild rabbits in Australia. The rabbit population grew so quickly in Australia that the event became known as the rabbit plague. Credit Richard Taylor Flicker. In 1859, an Australian landowner named Thomas Austin released 24 rabbits into the wild for hunting. Because Australia had few predators and ample food, the rabbit population exploded. In fewer than 10 years, the rabbit population numbered in the millions. Uncontrolled population growth, as in the wild rabbits in Australia, can be modeled with exponential functions. Equations resulting from those exponential functions can be solved to analyze and make predictions about exponential growth. In this section, we will learn techniques for solving exponential functions, using like bases to solve exponential equations. The first technique involves 2 functions with like bases. Recall that the one-to-one property of exponential functions tells us that, for any real numbers letter 1d44f, s, and letter 1d447, where letter 1d44f 0, letter 1d44f not equal to 1, letter 1d44f, letter 1d446 equals letter 1d44f, letter 1d447. If and only if letter 1d446 equals letter 1d447. In other words, when an exponential equation has the same base on each side, the exponents must be equal. This also applies when the exponents are algebraic expressions. Therefore, we can solve many exponential equations by using the rules of exponents to rewrite each side as a power with the same base. Then, we use the fact that exponential functions are one-to-one to set the exponents equal to one another and solve for the unknown. For example, consider the equation 34 letter 1d465 minus 7 equals 32 letter 1d465 3. To solve for letter 1d465, we use the division property of exponents to rewrite the right side so that both sides have the common base, 3. Then we apply the one-to-one property of exponents by setting the exponents equal to one another and solving for letter 1d465. 34 letter 1d465 minus 734 letter 1d465 minus 734 letter 1d465 minus 74 letter 1d465 minus 72 letter 1d465 letter 1d465 equals 32 letter 1d465 3 equals 32 letter 1d465 31 equals 32 letter 1d465 minus 1 equals 2 letter 1d465 minus 1 equal 3 as 31. Use the division property of exponents. Apply the one-to-one property of exponents. Subtract 2 letter 1d465 ND adds 7 to both sides. Divide by 2. Using the one-to-one property of exponential functions to solve exponential equations. For any algebraic expressions, letter 1d446 NDT, and any positive real number letter 1d44f not equal to 1. Letter 1d44f, letter 1d446 equals letter 1d44f, letter 1d447 if, and only if letter 1d446 equals letter 1d447. How to? Given an exponential equation with the form letter 1d44f, letter 1d446 equals letter 1d44f, letter 1d447, where letter 1d446 and letter 1d447 are algebraic expressions with an unknown, solve for the unknown. Use the rules of exponents to simplify, if necessary, so that the resulting equation has the form letter 1d44f, letter 1d446 equals letter 1d44f, letter 1d447. Use the one-to-one property to set the exponents equal. Solve the resulting equation, letter 1d446 equals letter 1d447, for the unknown. Example 1. Solving an exponential equation with a common base. Solve 2 letter 1d465 minus 1 equals 22 letter 1d465 minus 4. Solution. 2 letter 1d465 minus 1 equals 22 letter 1d465 minus 4. Letter 1d465 minus 1 equals 2 letter 1d465 minus 4. Letter 1d465 equals 3. The common base is 2. By the one-to-one property, the exponents must be equal. Solve for x. Try it 1. Solve 52 letter 1d465 equals 53 letter 1d465 plus 2. Rewriting equations so all powers have the same base. Sometimes the common base for an exponential equation is not explicitly shown. In these cases, we simply rewrite the terms in the equation as powers with a common base and solve using the one-to-one property. For example, consider the equation 256 equals 4 letter 1d465 minus 5. We can rewrite both sides of this equation as a power of 2. Then we apply the rules of exponents, along with the one-to-one property, to solve for letter 1d465. 256 equals 4 letter 1d465 minus 528 equals 22 letter 1d465 minus 528 equals 22 letter 1d465 minus 108 equals 2 letter 1d465 minus 1018 equals 2 letter 1d465 letter 1d465 equals 9. Rewrite each side as a power with base 2. Use the one-to-one property of exponents. Apply the one-to-one property of exponents. Add 10 to both sides. Divide by 2. How to? Given an exponential equation with unlike bases, use the one-to-one property to solve it. Rewrite each side in the equation as a power with a common base. Use the rules of exponents to simplify, if necessary, so that the resulting equation has the form letter 1d44f, letter 1d446 equals letter 1d44f, letter 1d447. Use the one-to-one property to set the exponents equal. Solve the resulting equation, letter 1d446 equals letter 1d447, for the unknown. Example 2. Solving equations by rewriting them to have a common base. Solve 8 letter 1d465 plus 2 equals 16 letter 1d465 plus 1. Solution. 8 letter 1d465 plus 2 equals 16 letter 1d465 plus 1 23. Letter 1d465 plus 2 equals 24 letter 1d465 plus 123 letter 1d465 plus 6 equals 24 letter 1d465 plus 43 letter 1d465 plus 6 equals 4 letter 1d465 plus 4 letter 1d465 equals 2. Write 8 and 16 as powers of 2. To take a power, multiply exponents. Use the one-to-one property to set the exponents equal. Solve for x, try it 2. Solve 52, letter 1d465, equals 253, letter 1d465, plus 2. Example 3. Solving equations by rewriting roots with fractional exponents to have a common base. Solve 25, letter 1d465, equals 2 square. Solution. 25, letter 1d465, equals 2125, letter 1d465, equals 12, letter 1d465, equals 110, write the square root of 2 as a power of 2. Use the one-to-one property. Solve FOR, letter 1d465, try it 3. Solve 5, letter 1d465, equals 5 square. Q and A. Do all exponential equations have a solution? If not, how can we tell if there is a solution during the problem-solving process? No. Recall that the range of an exponential function is always positive. While solving the equation, we may obtain an expression that is undefined. Example 4. Solving an equation with positive and negative powers. Solve 3, letter 1d465, plus 1 equals minus 2. Solution. This equation has no solution. There is no real value of letter 1d465. That will make the equation a true statement because any power of a positive number is positive. Analysis. Figure 2 shows that the two graphs do not cross, so the left side is never equal to the right side. Thus the equation has no solution. Graph of 3, x plus 1 equals 2 and y equals 2. The graph notes that they do not cross. Figure 2. Try it 4. Solve 2, letter 1d465, equals minus 100. Solving exponential equations using logarithms. Sometimes the terms of an exponential equation cannot be rewritten with a common base. In these cases, we solve by taking the logarithm of each side. Recall, since log, letter 1d44e equals log, letter 1d44f, is equivalent to letter 1d44e equals letter 1d44f. We may apply logarithms with the same base on both sides of an exponential equation. How to? Given an exponential equation in which a common base cannot be found, solve for the unknown. Apply the logarithm of both sides of the equation. If one of the terms in the equation has base 10, use the common logarithm. If none of the terms in the equation has base 10, use the natural logarithm. Use the rules of logarithms to solve for the unknown. Example 5. Solving an equation containing powers of different bases. Solve 5, letter 1d465, plus 2 equals 4, letter 1d465. Solution. 5, letter 1d465, plus 2 equals 4, letter 1d465 ln, 5, letter 1d465, plus 2 equals ln 4, letter 1d465. Letter 1d465 plus 2 ln 5 equals letter 1d465 ln, 4, letter 1d465 ln 5, plus 2 ln 5 equals letter 1d465 ln, 4, letter 1d465 ln, 5 minus letter 1d465 ln 4 equals minus 2 ln 5 letter 1d4s. Is no easy way to get the powers to have the same base. Take ln of both sides. Use laws of logs. Use the distributive law. Get terms CONT, INING letter 1d465 on one side, terms WITHOUT letter 1d465 on the other. On the left-hand side, factor out a n letter 1d465. Use the laws of logs. Divide by the coefficient OF letter 1d465. Try it 5. Solve 2 letter 1d465 equals 3 letter 1d465 plus 1. Q&A. Is there any way to solve 2 letter 1d465 equals 3 letter 1d465? Yes, the solution is 0. Equations containing E. One common type of exponential equations are those with base letter 1d452. This constant occurs again and again in nature, in mathematics, in science, in engineering, and in finance. When we have an equation with a base letter 1d452, on either side, we can use the natural logarithm to solve it. How to? Given an equation of the form, solve for letter 1d461. Divide both sides of the equation by letter 1d434. Apply the natural logarithm of both sides of the equation. Divide both sides of the equation by letter 1d458. Example 6. Solve an equation of the form y equals ect. Solve 100 equals 20 letter 1d452 to t. Solution. 1005 ln 5 letter 1d461 equals 20 letter 1d452 to letter 1d461 equals letter 1d452 to letter 1d461 equals 2 letter 1d461 equals ln 52, divide by the coefficient of the power. Take ln of both sides. Use the fact that ln, letter 1d465, and letter 1d452, letter 1d465 are E-inverse functions. Divide by the coefficient of t. Analysis. Using laws of logs, we can also write this answer in the form ln. If we want a decimal approximation of the answer, we use a calculator. Try at 6. Solve 3 letter 1d4520. 5 letter 1d461 equals 11. Q and A. Does every equation of the form have a solution? No, there is a solution when letter 1d458 not equal to 0, and when letter 1d466 and letter 1d434 are either both 0 or neither 0, and they have the same sign. An example of an equation with this form that has no solution is 2 equals minus 3 letter 1d452 letter 1d461. Example 7. Solving an equation that can be simplified to the form y equals ect. Solve 4 letter 1d452 to letter 1d465 plus 5 equals 12. Solution. 4 e to letter 1d465 plus 5 equals 124 letter 1d452 to letter 1d465 equals 7 letter 1d452 to letter 1d465 equals 742 letter 1d465 equals ln. 74 letter 1d465 equals 12 ln 74 combine like terms. Divide by the coefficient of the power. Take ln of both sides, solve for x. Try at 7. Solve 3 plus letter 1d452 to letter 1d461 equals 7 letter 1d452 to t. Extraneous solutions. Sometimes the methods used to solve an equation introduce an extraneous solution, which is a solution that is correct algebraically, but does not satisfy the conditions of the original equation. One such situation arises in solving when the logarithm is taken on both sides of the equation. In such cases, remember that the argument of the logarithm must be positive. If the number we are evaluating in a logarithm function is negative, there is no output. Example 8. Solving exponential functions in quadratic form. Solve letter 1d452 to letter 1d465 minus letter 1d45 to letter 1d465 equals 56. Solution. E to letter 1d465 minus letter 1d45 to letter 1d465 letter 1d452. Letter 1d465 minus letter 1d45 to letter 1d465 minus 56. Letter 1d45 to letter 1d465 plus 7. Letter 1d45 to letter 1d465 minus 8 letter 1d45 to letter 1d465 plus 7 letter 1d45 to letter 1d465 letter 1d45 to letter 1d465 letter 1d465 equals 56 equals 0 equals 0 equals 0 or letter 1d. E letter 1d465 equals 8 equals 8 equals ln 8. Get one side of the equation equal to 0. Factor by the FOIL method. If a product is 0, then one factor must be 0. Isolate the exponentials. Reject the equation in which the power equals a negative number. Solve the equation in which the power equals a positive number. Analysis. When we plan to use factoring to solve a problem, we always get 0 on one side of the equation. Because 0 has the unique property that when a product is 0, one or both of the factors must be 0. We reject the equation letter 1d45 to letter 1d465 equals minus 7. Because a positive number never equals a negative number. The solution ln minus 7 is not a real number, and in the real number system, this solution is rejected as an extraneous solution. Try at 8. Solve letter 1d452 to letter 1d465 equals letter 1d45 to letter 1d465 plus 2. Q and A. Does every logarithmic equation have a solution? No. Keep in mind that we can only apply the logarithm to a positive number. Always check for extraneous solutions. Using the definition of a logarithm to solve logarithmic equations, we have already seen that every logarithmic equation, log letter 1d44f, letter 1d465, equals letter 1d466, is equivalent to the exponential equation. We can use this fact, along with the rules of logarithms, to solve logarithmic equations where the argument is an algebraic expression. For example, consider the equation log 2 plus log 2, 3 letter 1d465 minus 5 equals 3. To solve this equation, we can use rules of logarithms to rewrite the left side in compact form, and then apply the definition of logs to solve for letter 1d465. Log 2 2 plus log 2, 3 letter 1d465 minus 5 equals 3 log 2 2. 3 letter 1d465 minus 5 equals 3 log 2. 6 letter 1d465 minus 10 equals 323 equals 6 letter 1d465 minus 108 equals 6 letter 1d465 minus 1018 equals 6 letter 1d465 letter 1d465 equals 3. Apply the product rule of logarithms. Distribute, apply the definition of a logarithm. Calculate 23, add 10 to both sides, divide by 6, using the definition of a logarithm to solve logarithmic equations. For any algebraic expression, letter 1d446, and real numbers, letter 1d44f, and letter 1d450, where letter 1d44f0, letter 1d44f not equal to 1. Log letter 1d44f, letter 1d446 equals letter 1d450, if and only. Example 9. Using algebra to solve a logarithmic equation. Solve 2 ln letter 1d465 plus 3 equals 7. Solution. 2 ln letter 1d465 plus 3 equals 72 ln letter 1d465 equals 4 ln letter 1d465 equals 2 letter 1d465 equals letter 1d452 to subtract 3. Divide by 2, rewrite in exponential form, try at 9. Solve 6 plus ln letter 1d465 equals 10. Example 10. Using algebra before and after using the definition of the natural logarithm. Solve 2 ln 6 letter 1d465 equals 7. Solution. 2 ln 6 letter 1d465 equals 7 ln 6 letter 1d465 equals 726 letter 1d465 equals letter 1d452. 72 letter 1d465 equals 16 letter 1d452. 72 divide by 2. Use the definition of ln, divide by 6, try at 10. Solve 2 ln, letter 1d465 plus 1 equals 10. Example 11, using a graph to understand the solution to a logarithmic equation, solve ln letter 1d465 equals 3. Solution ln letter 1d465 equals 3 letter 1d465 equals letter 1d452 3. Use the definition of the natural logarithm. Figure 3 represents the graph of the equation. On the graph, the x-coordinate of the point at which the two graphs intersect is close to 20. In other words, letter 1d452 3 approximately 20. A calculator gives a better approximation. Letter 1d452 3 approximately 20. 855. Graph of two questions, y equals 3 and y equals ln x, which intersect at the point E3, 3, which is approximately 20. 855 3. Figure 3, the graphs of letter 1d466 equals ln letter 1d465 and letter 1d466 equals 3 cross at the point E33, which is approximately 20. 855 3. Try it 11. Use a graphing calculator to estimate the approximate solution to the logarithmic equation 2 letter 1d465 equals 1000 to 2 decimal places. Using the one-to-one property of logarithms to solve logarithmic equations, as with exponential equations, we can use the one-to-one property to solve logarithmic equations. The one-to-one property of logarithmic functions tells us that, for any real numbers letter 1d4650, letter 1d4460, letter 1d4470, and any positive real number b, where letter 1d44f not equal to 1. Log letter 1d44f, letter 1d446 equals log letter 1d44f, letter 1d447 if, and only if letter 1d446 equals letter 1d447. For example, if log 2, letter 1d465 minus 1 equals log 2, 8, then letter 1d465 minus 1 equals 8. So, if letter 1d465 minus 1 equals 8, then we can solve for x, and we get letter 1d465 equals 9. To check, we can substitute letter 1d465 equals 9 into the original equation. Log 2, 9 minus 1, equals log 2, 8 equals 3. In other words, when a logarithmic equation has the same base on each side, the arguments must be equal. This also applies when the arguments are algebraic expressions. Therefore, When given an equation with logs of the same base on each side, we can use rules of logarithms to rewrite each side as a single logarithm. Then we use the fact that logarithmic functions are one-to-one to set the arguments equal to one another and solve for the unknown. For example, consider the equation log 3 letter 1d465 minus 2 minus log 2 equals log letter 1d465 plus 4. To solve this equation, we can use the rules of logarithms to rewrite the left side as a single logarithm, and then apply the one-to-one property to solve for x. Log 3 letter 1d465 minus 2 minus log 2 equals log letter 1d465 plus 4 log 3 letter 1d465 minus 22 equals log letter 1d465 plus 4 3 letter 1d465 minus 22 equals letter 1d465 plus 43 letter 1d465 minus 2 equals 2 letter 1d465 plus 8 letter 1d465 equals 10. Apply the quotient rule of logarithms. Apply the one-to-one property of a logarithm. Multiply both sides of the equation by 2. Subtract 2 letter 1d465 and add 2. To check the result, substitute letter 1d465 equals 10 into log 3 letter 1d465 minus 2 minus log 2 equals log letter 1d465 plus 4. Log 3 10 minus 2 minus log 2 equals log 10 plus 4 log 28 minus log 2 equals log 14 log 282 equals log 14. The solution checks. Using the one-to-one property of logarithms to solve logarithmic equations for any algebraic expressions s and t and any positive real number b, where letter 1d44f not equal to 1. Log letter 1d44f, letter 1d446 equals log letter 1d44f, letter 1d447 if, and only if letter 1d446 equals letter 1d447. Note: when solving an equation involving logarithms, always check to see if the answer is correct or if it is an extraneous solution. How to given an equation containing logarithms, solve it using the one-to-one property. Use the rules of logarithms to combine like terms, if necessary, so that the resulting equation has the form log letter 1d44f, letter 1d446 equals log letter 1d44f, letter 1d447. Use the one-to-one property to set the arguments equal. Solve the resulting equation, letter 1d446 equals letter 1d447, for the unknown. Example 12, solving an equation using the one-to-one property of logarithms, solve ln. Letter 1d4652 equals ln, 2 letter 1d465 plus 3. Solution ln, letter 1d4652 equals ln 2 letter 1d465, plus 3 letter 1d4652 equals 2 letter 1d465, plus 3 letter 1d4652 minus 2 letter 1d465 minus 3 equals 0. Letter 1d465 minus 3. Letter 1d465 plus 1 equals 0. Letter 1d465 minus 3 equals 0. Or letter 1d465 plus 1 equals 0. Letter 1d465 equals 3 or letter 1d465 equals minus 1. Use the one-to-one property of the logarithm. Get 0 on one side before factoring. Factor using FOIL. If a product is 0, one of the factors must be 0. Solve for x analysis. There are two solutions, 3 or minus 1. The solution minus 1 is negative, but it checks when substituted into the original equation because the argument of the logarithm functions is still positive. Try at 12. Solve ln, letter 1d4652 equals ln1. Solving applied problems using exponential and logarithmic equations in previous sections, we learned the properties and rules for both exponential and logarithmic functions. We have seen that any exponential function can be written as a logarithmic function and vice versa. We have used exponents to solve logarithmic equations and logarithms to solve exponential equations. We are now ready to combine our skills to solve equations that model real-world situations, whether the unknown is in an exponent or in the argument of a logarithm. One such application is in science, in calculating the time it takes for half of the unstable material in a sample of a radioactive substance to decay, called its half-life. Table 1 lists the half-life for several of the more common radioactive substances. Substance, use half-life gallium-67, nuclear medicine 80 hours, cobalt-60 manufacturing 5. 3 years technetium-99 m nuclear medicine, 6 hours americium-241, construction 432 years, carbon-14 archaeological dating. 5,730 years, uranium-235, atomic power 703,800,000 years. Table 1. We can see how widely the half-lives for these substances vary. Knowing the half-life of a substance allows us to calculate the amount remaining after a specified time. We can use the formula for radioactive decay. Letter 1d434, letter 1d461, equals letter 1d4340, letter 1d452ln, 0. 5 letter 1d447, letter 1d461, letter 1d434. Letter 1d461 equals letter 1d434, 0, letter 1d452ln, 0. 5 letter 1d461, letter 1d447, letter 1d434. Letter 1d461 equals letter 1d434, 0, letter 1d452ln, 0. 5 letter 1d461, letter 1d447, letter 1d434. Letter 1d461 equals letter 1d434, 0. 12. Letter 1d461, letter 1d447, where A0 is the amount initially present T, is the half-life of the substance T, is the time period over which the substance is studied. Letter 1d434. Letter 1d461 is the amount of the substance present after time T. Example 13, using the formula for radioactive decay to find the quantity of a substance. How long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? Solution: letter 1d466 equals 1,000, letter 1d452ln, 0. 5,703, 800, 000, letter 1d461 900 equals 1,000, letter 1d452ln, 0. 5,703, 800, 000, letter 1d461 0. 9 equals letter 1d452ln, 0. 5,703, 800, 000, letter 1d461ln, 0. 9 equals ln, letter 1d452ln, 0. 5,703, 800, 000, letter 1d461, ln, 0. 9 equals ln, 0. 5,703, 800, 000, letter 1d461, letter 1d461 equals 703, 800, 000 times ln, 0. 9 ln, 0. 5 ye a rs, letter 1d461 approximately 106, 979, 777 years after 10% decays, 900 grams are left. Divide by 1,000. Take ln of both sides. Ln, letter 1d452, letter 1d440 equals letter 1d440, solve fort. Analysis: 10% of 1,000 grams is 100 grams. If 100 grams decay, the amount of uranium-235 remaining is 900 grams. Try it 13. How long will it take before 20% of our 1,000 gram sample of uranium-235 has decayed? Media access: these online resources for additional instruction and practice with exponential and logarithmic equations. Solving logarithmic equations, solving exponential equations with logarithm 6. 6th section, exercises. Verbal 1. How can an exponential equation be solved? 2. When does an extraneous solution occur? How can an extraneous solution be recognized? 3. When can the one-to-one property of logarithms be used to solve an equation? When can it not be used? Algebraic: for the following exercises, use like bases to solve the exponential equation. 4 minus 3, letter 1d463, minus 2 equals 4 minus letter 1d4635. 6443, letter 1d465 equals 166. 32, letter 1d465 plus 13, letter 1d465 equals 243. 72 minus 3, letter 1d45b. 14 equals 2, letter 1d45b plus 28. 625. 53, letter 1d465 plus 3 equals 125. 9. 363, letter 1d44f, 362, letter 1d44f equals 2162 minus letter 1d44f 10. 164 3 letter 1d45b 8 equals 26 for the following exercises. Use logarithms to solve. 11. 9 letter 1d465 minus 10 equals 112. 2 letter 1d452 6 letter 1d465 equals 1313. Letter 1d45 to letter 1d45f plus 10 minus 10 equals minus 4214. 2 109 letter 1d44e equals 2915. Minus 810 letter 1d45d plus 7 minus 7 equals minus 2416. 7 letter 1d452 3 letter 1d45b minus 5 plus 5 equals minus 8917. Letter 1d452 minus 3 letter 1d458 plus 6 equals 4418. Minus 5 letter 1d452 9 letter 1d465 minus 8 equals minus 6219. Minus 6 letter 1d452 9 letter 1d465 plus 8 plus 2 equals minus 7420. 2 letter 1d465 plus 1 equals 52 letter 1d465 minus 121. E to letter 1d465 minus letter 1d45 to letter 1d465 minus 132 equals 022. 7 letter 1d452, 8 letter 1d465 plus 8 minus 5 equals minus 9523. 10 letter 1d452, 8 letter 1d465 plus 3 plus 2 equals 824. 4 letter 1d452, 3 letter 1d465 plus 3 minus 7 equals 5325. 8 letter 1d452 minus 5 letter 1d465 minus 2 minus 4 equals minus 9026. 32 letter 1d465 plus 1 equals 7 letter 1d465 minus 227. E to letter 1d465 minus letter 1d45 to letter 1d465 minus 6 equals 028. 3 letter 1d452 3 minus 3 letter 1d465 plus 6 equals minus 31 for the following exercises. Use the definition of a logarithm to rewrite the equation as an exponential equation. 29. Log 1100 equals minus 230. Log 324, 18 equals 12 for the following exercises. Use the definition of a logarithm to solve the equation. 31. 5 log 7 letter 1d45b equals 1032. Minus 8 log 9 letter 1d465 equals 1633. 4 plus log 2, 9 letter 1d458 equals 234. 2 log 8 letter 1d45b plus 4 plus 6 equals 1035. 10 minus 4 ln 9 minus 8 letter 1d465 equals 6 for the following exercises. Use the one-to-one property of logarithms to solve. 36. ln 10 minus 3 letter 1d465 equals ln minus 4 letter 1d465, 37. Log 13, 5 letter 1d45b minus 2 equals log 13, 8 minus 5 letter 1d45b, 38. Log letter 1d465 plus 3 minus log letter 1d465 equals log 74, 39. ln minus 3 letter 1d465 equals ln letter 1d465 2 minus 6 letter 1d465, 40. Log 4, 6 minus letter 1d45a equals log 43 letter 1d45a, 41. ln letter 1d465 minus 2 minus ln letter 1d465 equals ln 54, 42. Log 9, 2 letter 1d45b 2 minus 14 letter 1d45b equals log 9 minus 45 plus letter 1d45b 2, 43. ln letter 1d465 2 minus 10 plus ln 9 equals ln 10 for the following exercises. Solve each equation for x44. Log letter 1d465 plus 12 equals log letter 1d465 plus log 12, 45. ln letter 1d465 plus ln letter 1d465 minus 3 equals ln 7 letter 1d465, 46. Log 2, 7 letter 1d465 plus 6 equals 347. ln 7 plus ln 2 minus 4 letter 1d465 2 equals ln 14, 48. Log 8 letter 1d465 plus 6 minus log 8 letter 1d465 equals log 8, 58, 49. ln 3 minus ln 3 minus 3 letter 1d465 equals ln 450. Log 3, 3 letter 1d465 minus log 3, 6 equals log 3. 77. Graphical for the following exercises, solve the equation for x if there is a solution. Then graph both sides of the equation and observe the point of intersection, if it exists, to verify the solution. 51. Log 9, letter 1d465, minus 5 equals minus 452. Log 3, letter 1d465, plus 3 equals 253. ln 3 letter 1d465 equals 254. ln letter 1d465 minus 5 equals 155. Log 4 plus log minus 5 letter 1d465 equals 256. Minus 7 plus log 3, 4 minus letter 1d465 equals minus 657. ln 4 letter 1d465 minus 10 minus 6 equals minus 558. Log 4 minus 2 letter 1d465 equals log minus 4 letter 1d465, 59. Log 11 minus 2 letter 1d465 2 minus 7 letter 1d465 equals log 11, letter 1d465 minus 2, 60. ln 2 letter 1d465 plus 9 equals ln minus 5 letter 1d465, 61. Log 9, 3 minus letter 1d465 equals log 9, 4 letter 1d465 minus 8, 62. Log letter 1d465 2 plus 13 equals log 7 letter 1d465 plus 3, 63. 3 log 2 10 minus log letter 1d465 minus 9 equals log 44, 64. ln letter 1d465 minus ln letter 1d465 plus 3 equals ln 6. For the following exercises, solve for the indicated value and graph the situation showing the solution point. 65. An account with an initial deposit of $6,500 earns 7.25% annual interest, compounded continuously. How much will the account be worth after 20 years? 66. The formula for measuring sound intensity in decibels D is defined by the equation letter 1d437 equals 10 log, letter 1d436 letter 1d436 0, where I is the intensity of the sound in watts per square meter, and letter 1d436 0 equals 10 minus 12, is the lowest level of sound that the average person can hear. How many decibels are emitted from a jet plane with a sound intensity of 8.102 watts per square meter? 67. The population of a small town is modeled by the equation letter 1d443 equals 1,650 letter 1d4520. 5t, where t is measured in years. In approximately how many years will the town's population reach 20,000? Technology for the following exercises, solve each equation by rewriting the exponential expression using the indicated logarithm. Then use a calculator to approximate the variable to 3 decimal places. 68, 1001, 03, letter 1d461 equals 5,000 using the common log. 69. Using the natural log 70, 3, 1. Using the common log 71. 34 letter 1d465 minus 5 equals 38 using the common log 72. 50 letter 1d452 minus 0. 12 letter 1d461 equals 10 using the natural log. For the following exercises, use a calculator to solve the equation. Unless indicated otherwise, round all answers to the nearest 10,000th. 73. 7 letter 1d452 3 letter 1d465 minus 5 plus 7. 9 equals 4774. ln 3 plus ln 4, 4x plus 6. 8 equals 275. Log minus 0. 7 letter 1d465 minus 9 equals 1 plus 5 log, 576. Atmospheric pressure P in pounds per square inch is represented by the formula letter 1d443 equals 14. 7 letter 1d452 minus 0. 21x, where x is the number of miles above sea level. To the nearest foot, how high is the peak of a mountain with an atmospheric pressure of 369 pounds per square inch? Hint: there are 5280 feet in a mile 77. The magnitude m of an earthquake is represented by the equation letter 1d440 equals 23 log letter 1d438 letter 1d4380, where E is the amount of energy released by the earthquake in joules and letter 1d4380 equals 104. 4 is the assigned minimal measure released by an earthquake. To the nearest hundredth, what would the magnitude be of an earthquake releasing 1? For 1013 joules of energy, extensions 78. Use the definition of a logarithm, along with the one-to-one property of logarithms, to prove that letter 1d44f, log letter 1d44f, letter 1d465 equals letter 1d465. 79. Recall the formula for continually compounding interest. Letter 1d466 equals letter 1d434, letter 1d452, letter 1d458, letter 1d461. Use the definition of a logarithm, along with properties of logarithms, to solve the formula for time t such that t is equal to a single logarithm. 80. Recall the compound interest formula letter 1d434 equals letter 1d44e. 1 plus letter 1d45f, letter 1d458, letter 1d458, letter 1d461. Use the definition of a logarithm, along with properties of logarithms, to solve the formula for time t 81. Newton's law of cooling states that the temperature T of an object at any time t can be described by the equation letter 1d447 equals letter 1d447, letter 1d460 plus letter 1d4470 minus letter 1d447, letter 1d460, letter 1d452 minus letter 1d458, letter 1d461, where letter 1d447, letter 1d460 is the temperature of the surrounding environment, T0 is the initial temperature of the object, and K is the cooling rate. Use the definition of a logarithm, along with properties of logarithms, to solve the formula for time t such that t is equal to a single logarithm. Learning objectives in this section, you will model exponential growth and decay, use Newton's law of cooling, use logistic growth models, choose an appropriate model for data, express an exponential model in base E inside a nuclear research reactor. Figure 1, a nuclear research reactor inside the Neely Nuclear Research Center on the Georgia Institute of Technology campus. Credit: Georgia Tech Research Institute. We have already explored some basic applications of exponential and logarithmic functions. In this section, we explore some important applications in more depth, including radioactive isotopes and Newton's law of cooling. Modeling exponential growth and decay in real-world applications, we need to model the behavior of a function. In mathematical modeling, we choose a familiar general function with properties that suggest that it will model the real-world phenomenon we wish to analyze. In the case of rapid growth, we may choose the exponential growth function. Letter 1d466 equals letter 1d4340, letter 1d452, letter 1d458, letter 1d461, where a0 is equal to the value at time 0, E is Euler's constant, and K is a positive constant that determines the rate percentage of growth. We may use the exponential growth function in applications involving doubling time, the time it takes for a quantity to double. Such phenomena as wildlife populations, financial investments, biological samples, and natural resources may exhibit growth based on a doubling time. In some applications, however, as we will see when we discuss the logistic equation, the logistic model sometimes fits the data better than the exponential model. On the other hand, if a quantity is falling rapidly towards zero without ever reaching zero, then we should probably choose the exponential decay model. Again, we have the form letter 1d466 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461, where a0 is the starting value, and E is Euler's constant. Now K is a negative constant that determines the rate of decay. We may use the exponential decay model when we are calculating half-life, or the time it takes for a substance to exponentially decay to half of its original quantity. We use half-life in applications involving radioactive isotopes. In our choice of a function to serve as a mathematical model, we often use data points gathered by careful observation and measurement to construct points on a graph and hope we can recognize the shape of the graph. Exponential growth and decay graphs have a distinctive shape, as we can see in Figure 2 and Figure 3. It is important to remember that, although parts of each of the two graphs seem to lie on the x-axis, they are really a tiny distance above the x-axis. Graph of y equals 2e 3x with the labeled points, -1 3, 2e, 0 2, and 1 3, 2e, and with the asymptote at y equals 0. Figure 2, a graph showing exponential growth. The equation is letter 1d466 equals 2 letter 1d452 3 letter 1d465. Graph of y equals 3e minus 2x with the labeled points -1 2, 3e, 0 3, and 1 2, 3e, and with the asymptote at y equals 0. Figure 3, a graph showing exponential decay. The equation is letter 1d466 equals 3 letter 1d452 minus 2 letter 1d465. Exponential growth and decay often involve very large or very small numbers. To describe these numbers, we often use orders of magnitude. The order of magnitude is the power of 10 when the number is expressed in scientific notation, with one digit to the left of the decimal. For example, the distance to the nearest star, Proxima Centauri, measured in kilometers, is 40,113,497,200,000 kilometers. Expressed in scientific notation, this is 4,01134,972 times 1013. So, we could describe this number as having order of magnitude 1013. Characteristics of the exponential function. Letter 1d466 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461, an exponential function with the form letter 1d466 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461, has the following characteristics. One-to-one function horizontal asymptote, letter 1d466 equals 0 domain, infinity range, 0 infinity x-intercept, none y-intercept, 0 a0, increasing if letter 1d4580, see Figure 4, decreasing if letter 1d4580, see Figure 4, two graphs of y equals a0, kt, with the asymptote at y equals 0. The first graph is of when k0 and with the labeled points 1k, a0e, 0 a0, and -1k, a0/e. The second graph is of when k0 and with the labeled points -1k, a0e, 0 a0, and 1k, a0/e. Figure 4, an exponential function, models exponential growth when letter 1d4580 and exponential decay when letter 1d4580. Example 1, graphing exponential growth, a population of bacteria doubles every hour. If the culture started with 10 bacteria, graph the population as a function of time. Solution: when an amount grows at a fixed percent per unit time, the growth is exponential. To find a0, we use the fact that a0 is the amount at time 0, so letter 1d4340 equals 10. To find k, use the fact that after 1 hour, letter 1d461 equals 1. The population doubles from 10 to 20. The formula is derived as follows: 20 equals 10 letter 1d45 letter 1d458, 12 equals letter 1d45 letter 1d458 ln, 2 equals letter 1d458. Divide by 10, take the natural logarithm, so letter 1d458 equals ln 2. Thus the equation we want to graph is letter 1d466 equals 10 letter 1d452. ln 2 letter 1d461 equals 10 letter 1d452 ln 2 letter 1d461 equals 10 2 letter 1d461. The graph is shown in Figure 5. A graph starting at 10 on the y-axis and rising rapidly to the right. Figure 5, the graph of letter 1d466 equals 10 letter 1d452, ln 2 letter 1d461 analysis, the population of bacteria after 10 hours is 10,240. We could describe this amount as being of the order of magnitude 104. The population of bacteria after 20 hours is 10,480,5,760, which is of the order of magnitude 107. So we could say that the population has increased by 3 orders of magnitude in 10 hours. Half-life, we now turn to exponential decay. One of the common terms associated with exponential decay, as stated above, is half-life, the length of time it takes an exponentially decaying quantity to decrease to half its original amount. Every radioactive isotope has a half-life, and the process describing the exponential decay of an isotope is called radioactive decay. To find the half-life of a function describing exponential decay, solve the following equation. 12 letter 1d434, 0 equals letter 1d434 letter 1d45c letter 1d452 letter 1d458 letter 1d461. We find that the half-life depends only on the constant k and not on the starting quantity a0. The formula is derived as follows. 12 letter 1d434, 0 equals letter 1d434 letter 1d45c letter 1d452 letter 1d458 letter 1d461. 12 equals letter 1d452 letter 1d458 letter 1d461 ln 12 equals letter 1d458 letter 1d461 minus ln 2 equals letter 1d458 letter 1d461 minus ln 2 letter 1d458 equals letter 1d461 divide by a0. Take the natural log, apply laws of logarithms, divide by letter 1d458. Since t, the time, is positive, k must, as expected, be negative. This gives us the half-life formula, letter 1d461 equals minus ln 2 letter 1d458. How to given the half-life? Find the decay rate. Write letter 1d434 equals letter 1d434 letter 1d45c letter 1d452 letter 1d458 letter 1d461. Replace a by 12a0 and replace t by the given half-life. Solve to find k. Express k as an exact value, do not round. Note, it is also possible to find the decay rate using letter 1d458 equals minus ln 2 letter 1d461. Example 2, finding the function that describes radioactive decay. The half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time, t. Solution. This formula is derived as follows. Letter 1d434 equals letter 1d434, 0, letter 1d452 letter 1d458 letter 1d461, 0. 5 letter 1d434, 0 equals letter 1d434, 0, letter 1d452 letter 1d458, 57,300. 5 equals letter 1d452, 5,730, letter 1d458 ln 0. 5 equals 5,730, letter 1d458 letter 1d458 equals ln 0. 5,730 letter 1d434 equals letter 1d434 0 letter 1d452 ln 0. 5,730 letter 1d461 the continuous growth formula. Substitute the half-life FOR letter 1d461 at ND0. 5 letter 1d4340 FOR letter 1d453 letter 1d461. Divide by a0. Take the natural log of both sides. Divide by the coefficient OF letter 1d458. Substitute FOR letter 1d45F IN the continuous growth formula. The function that describes this continuous decay is letter 1d453. Letter 1d461 equals letter 1d434 0 letter 1d452. ln 0. 5,730 letter 1d461. We observe that the coefficient of t, ln 0. 5,730 approximately minus 1. 2,097 times 10 minus 4 is negative, as expected in the case of exponential decay. Try at 1. The half-life of plutonium-244 is 80 million years. Find a function that gives the amount of plutonium-244 remaining as a function of time, measured in years. Radiocarbon dating. The formula for radioactive decay is important in radiocarbon dating, which is used to calculate the approximate date a plant or animal died. Radiocarbon dating was discovered in 1949 by Willard Libby, who won a Nobel Prize for his discovery. It compares the difference between the ratio of two isotopes of carbon in an organic artifact or fossil to the ratio of those two isotopes in the air. It is believed to be accurate to within about 1% error for plants or animals that died within the last 60,000 years. Carbon-14 is a radioactive isotope of carbon that has a half-life of 5,730 years. It occurs in small quantities in the carbon dioxide in the air we breathe. Most of the carbon on Earth is carbon-12, which has an atomic weight of 12 and is not radioactive. Scientists have determined the ratio of carbon-14 to carbon-12 in the air for the last 60,000 years, using tree rings and other organic samples of known dates, although the ratio has changed slightly over the centuries. As long as a plant or animal is alive, the ratio of the two isotopes of carbon in its body is close to the ratio in the atmosphere. When it dies, the carbon-14 in its body decays and is not replaced. By comparing the ratio of carbon-14 to carbon-12 in a decaying sample to the known ratio in the atmosphere, the date the plant or animal died can be approximated. Since the half-life of carbon-14 is 5,730 years, the formula for the amount of carbon-14 remaining after T years is letter 1d434, approximately letter 1d434, 0, letter 1d452. ln 0. 5,730. Letter 1d461, where A is the amount of carbon-14 remaining A0 is the amount of carbon-14 when the plant or animal began decaying. This formula is derived as follows. Letter 1d434 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461, 0. 5 letter 1d434, 0 equals letter 1d434, 0, letter 1d452, letter 1d458, 57,300. 5 equals letter 1d452, 5,730, letter 1d458, ln 0. 5 equals 5,730, letter 1d458, letter 1d458 equals ln 0. 5,730, letter 1d434 equals letter 1d434, 0, letter 1d452, ln 0. 5,730, letter 1d461, the continuous growth formula. Substitute the half-life FOR letter 1d461 at ND0. 5 letter 1d434, FOR letter 1d453, letter 1d461. Divide by A0. Take the natural log of both sides. Divide by the coefficient OF letter 1d458. Substitute FOR letter 1d458, IN the continuous growth formula. To find the age of an object, we solve this equation for t. Letter 1d461 equals ln, letter 1d434, letter 1d434, 0 minus 0. 121 out of necessity. We neglect here the many details that a scientist takes into consideration when doing carbon-14 dating, and we only look at the basic formula. The ratio of carbon-14 to carbon-12 in the atmosphere is approximately 0.1%. Let R be the ratio of carbon-14 to carbon-12 in the organic artifact or fossil to be dated, determined by a method called liquid scintillation. From the equation letter 1d434, approximately letter 1d434, 0, letter 1d452, minus 0. 121t, we know the ratio of the percentage of carbon-14 in the object we are dating to the initial amount of carbon-14 in the object when it was formed. Is letter 1d45f equals letter 1d434, letter 1d434, 0, approximately letter 1d452, minus 0. We solve this equation for t to get letter 1d461 equals ln, letter 1d45f, minus 0. 121, how to given the percentage of carbon-14 in an object, determine its age. Express the given percentage of carbon-14 as an equivalent decimal, k. Substitute for k in the equation letter 1d461 equals ln, letter 1d45f, minus 0. 121, and solve for the age t. Example 3, finding the age of a bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? Solution, we substitute 20% equals 0. 20 for R in the equation and solve for t. Letter 1d461 equals ln, letter 1d45f, minus 0. 0,00121 equals ln, 0. 20 minus 0. 0,00121 approximately 13,301. Use the general form of the equation. Substitute for R round to the nearest year. The bone fragment is about 13,301 years old. Analysis: the instruments that measure the percentage of carbon-14 are extremely sensitive, and, as we mentioned above, a scientist will need to do much more work than we did in order to be satisfied. Even so, carbon dating is only accurate to about 1%. So this age should be given as 13,301 years plus, or minus 1%, or 13,301 years plus, or minus 133 years. Triate-2 cesium has a half-life of about 30 years. If we begin with 200 mg of cesium-137, will it take more or less than 230 years until only 1 milligram remains? Calculating doubling time for decaying quantities, we determined how long it took for half of a substance to decay. For growing quantities, we might want to find out how long it takes for a quantity to double. As we mentioned above, the time it takes for a quantity to double is called the doubling time. Given the basic exponential growth equation, letter 1d434 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461. Doubling time can be found by solving for when the original quantity has doubled. That is, by solving 2 letter 1d434, 0 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461. The formula is derived as follows. 2 letter 1d434, 0 equals letter 1d434, 0, letter 1d452, letter 1d458, letter 1d461. 2 equals letter 1d452, letter 1d458, letter 1d461 ln. 2 equals letter 1d458, letter 1d461, letter 1d461 equals ln to k divide by a0. Take the natural logarithm. Divide by the coefficient oft, thus the doubling time is letter 1d461 equals ln to k. Example, for finding a function that describes exponential growth according to Moore's law. The doubling time for the number of transistors that can be put on a computer chip is approximately 2 years. Give a function that describes this behavior. Solution: the formula is derived as follows. Letter 1d461 equals ln to letter 1d458. 2 equals ln to letter 1d458, letter 1d458 equals ln. 22, letter 1d434 equals letter 1d434, 0, letter 1d452 ln. 22, letter 1d461, the doubling time formula. Use a doubling time of 2 years. Multiply by letter 1d458, a nd divide by 2. Substitut e letter 1d458, int o the continuous growth formula. The function is letter 1d434, 0, letter 1d452 ln, 22, letter 1d461. Triate-3 recent data suggests that, as of 2013, the rate of growth predicted by Moore's law no longer holds. Growth has slowed to a doubling time of approximately 3 years. Find the new function that takes that longer doubling time into account. Using Newton's law of cooling, exponential decay can also be applied to temperature. When a hot object is left in surrounding air that is at a lower temperature, the object's temperature will decrease exponentially, leveling off as it approaches the surrounding air temperature. On a graph of the temperature function, the leveling off will correspond to a horizontal asymptote at the temperature of the surrounding air. Unless the room temperature is 0, this will correspond to a vertical shift of the generic exponential decay function. This translation leads to Newton's law of cooling. The scientific formula for temperature as a function of time as an object's temperature is equalized with the ambient temperature, letter 1d447. Letter 1d461 equals letter 1d434, letter 1d452, letter 1d458, letter 1d461, plus letter 1d447, letter 1d460. This formula is derived as follows. Letter 1d447, letter 1d461 equals letter 1d434, letter 1d44f, letter 1d450, letter 1d461, plus letter 1d447, letter 1d460, letter 1d447, letter 1d461 equals letter 1d434, letter 1d452 ln. Letter 1d44f, letter 1d450, letter 1d461, plus letter 1d447, letter 1d460, letter 1d4 of logarithms, laws of logarithms, rename the constant c ln b calling it k. Newton's law of cooling the temperature of an object, T, in surrounding air with temperature letter 1d447, letter 1d460, will behave according to the formula letter 1d447. letter 1d461 equals letter 1d434, letter 1d452, letter 1d458, letter 1d461, plus letter 1d447, letter 1d460, where T is time A is the difference between the initial temperature of the object, and the surroundings K is a constant. The continuous rate of cooling of the object how to given a set of conditions. Apply Newton's law of cooling. Set letter 1d447, letter 1d460 equal to the y-coordinate of the horizontal asymptote, usually the ambient temperature. Substitute the given values into the continuous growth formula, letter 1d447. Letter 1d461 equals letter 1d434, letter 1d452, letter 1d458, letter 1d461, plus letter 1d447, letter 1d460 to find the parameters A and K. Substitute in the desired time to find the temperature or the desired temperature to find the time. Example 5, using Newton's law of cooling, a cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees F and is placed into a 35 degrees F refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees F. If we must wait until the cheesecake has cooled to 70 degrees F before we eat it, how long will we have to wait? Solution: because the surrounding air temperature in the refrigerator is 35 degrees, the cheesecake's temperature will decay exponentially toward 35. Following the equation, letter 1d447. Letter 1d461 equals letter 1d434, letter 1d452, letter 1d458, letter 1d461, plus 35, we know the initial temperature was 165. So letter 1d447, 0, equals 165. 165 equals letter 1d434, letter 1d452, letter 1d458, 0, plus 35 letter 1d434 equals 130. Substitute, 165. Solve for A. We were given another data point, letter 1d447, 10 equals 150, which we can use to solve for K. 150 equals 130 letter 1d452, letter 1d458, 10, plus 35,115 equals 130 letter 1d452, letter 1d458, 10,115,130 equals letter 1d452, 10 letter 1d458 ln. 115,130 equals 10 letter 1d458, letter 1d458 equals ln. 115,000. 123. Substitute 10, 150. Subtract 35. Divide by 130. Take the natural log of both sides. Divide by the coefficient OF letter 1d458. This gives us the equation for the cooling of the cheesecake. Letter 1d447, letter 1d461 equals 130 letter 1d4520. 123T plus 35. Now we can solve for the time it will take for the temperature to cool to 70 degrees. 70 equals 130 letter 1d452 minus 0. 0123 letter 1d461 plus 3535 equals 130 letter 1d452 minus 0. 0123 letter 1d461 35,130 equals letter 1d452 minus 0. 0123 letter 1d461 ln 35,130 equals minus 0. 0123 letter 1d461 letter 1d461 equals ln 35,130 minus 0. 0123 approximately 106. 68. Substitute in 70 for letter 1d447, letter 1d461. Subtract 35. Divide by 130. Take the natural log of both sides. Divide by the coefficient oft. It will take about 107 minutes, or 1 hour and 47 minutes, for the cheesecake to cool to 70 degrees F. Try it for a pitcher of water at 40 degrees Fahrenheit is placed into a 70-degree room. 1 hour later, the temperature has risen to 45 degrees. How long will it take for the temperature to rise to 60 degrees? Using logistic growth models, exponential growth cannot continue forever. Exponential models, while they may be useful in the short term, tend to fall apart the longer they continue. Consider an aspiring writer who writes a single line on day 1 and plans to double the number of lines she writes each day for a month. By the end of the month, she must write over 17 billion lines or 1/2 billion pages. It is impractical if not impossible, for anyone to write that much in such a short period of time. Eventually, an exponential model must begin to approach some limiting value, and then the growth is forced to slow. For this reason, it is often better to use a model with an upper bound instead of an exponential growth model, though the exponential growth model is still useful over a short term before approaching the limiting value. The logistic growth model is approximately exponential at first, but it has a reduced rate of growth as the output approaches the model's upper bound, called the carrying capacity. For constants a, b, and c, the logistic growth of a population over time t is represented by the model letter 1d453. Letter 1d461 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d461. The graph in figure 6 shows how the growth rate changes over time. The graph increases from left to right, but the growth rate only increases until it reaches its point of maximum growth rate, at which point the rate of increase decreases. Graph of ft equals c slash 1 plus a tx. The carrying capacity is the asymptote at y equals c. The initial value of population is 0, c slash 1 plus a. The point of maximum growth is ln a slash b c2. Figure 6. The logistic growth model is letter 1d453. Letter 1d461 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d461, where c1 plus a is the initial value, c is the carrying capacity, or limiting value b is a constant determined by the rate of growth. Example 6, using the logistic growth model, an influenza epidemic spreads through a population rapidly, at a rate that depends on two factors. The more people who have the flu, the more rapidly it spreads, and also the more uninfected people there are, the more rapidly it spreads. These two factors make the logistic model a good one to study the spread of communicable diseases. And, clearly, there is a maximum value for the number of people infected, the entire population. For example, at time letter 1d461 equals 0, there is one person in a community of 1,000 people who has the flu. So, in that community, at most 1,000 people can have the flu. Researchers find that for this particular strain of the flu, the logistic growth constant is letter 1d44f equals 0. 60-30. Estimate the number of people in this community who will have had this flu after 10 days. Predict how many people in this community will have had this flu after a long period of time has passed. Solution: we substitute the given data into the logistic growth model letter 1d453. Letter 1d461 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d461, because at most 0 people, the entire population of the community, can get the flu. We know the limiting value is letter 1d450 equals 1,000. To find a, we use the formula that the number of cases at time letter 1d461 equals 0 is letter 1d450, 1 plus letter 1d440 equals 1, from which it follows that letter 1d440 equals 999. This model predicts that, after 10 days, the number of people who have had the flu is letter 1d453. Letter 1d461 equals 10,001 plus 999 letter 1d452 minus 0. 6,030 letter 1d465 approximately 293. 8. Because the actual number must be a whole number, a person has either had the flu or not, we round to 294. In the long term, the number of people who will contract the flu is the limiting value. Letter 1d450 equals 1,000. Analysis: remember that, because we are dealing with a virus, we cannot predict with certainty the number of people infected. The model only approximates the number of people infected and will not give us exact or actual values. The graph in figure 7 gives a good picture of how this model fits the data. Graph of f(x) equals 1,000 slash 1 plus 999 e minus 0. 50-30x, with the y-axis labeled as cases and the x-axis labeled as days. There was 1 case on day 0, 20 on day 5, 294 on day 10, and 1,000 on day 21. Figure 7, the graph of letter 1d453, letter 1d461, equals 10,001 plus 999 letter 1 D452 minus 0. 6030x try it 5 using the model in example 6. Estimate the number of cases of flu on day 15. Choosing an appropriate model for data now that we have discussed various mathematical models, we need to learn how to choose the appropriate model for the raw data we have. Many factors influence the choice of a mathematical model, among which are experience, scientific laws, and patterns in the data itself. Not all data can be described by elementary functions. Sometimes, a function is chosen that approximates the data over a given interval. For instance, suppose data were gathered on the number of homes bought in the United States from the years 1960 to 2013. After plotting these data in a scatter plot, we notice that the shape of the data from the years 2000 to 2013 follow a logarithmic curve. We could restrict the interval from 2000 to 2010, apply regression analysis using a logarithmic model, and use it to predict the number of home buyers for the year 2015. Three kinds of functions that are often useful in mathematical models are linear functions, exponential functions, and logarithmic functions. If the data lies on a straight line, or seems to lie approximately along a straight line, a linear model may be best. If the data is nonlinear, we often consider an exponential or logarithmic model, though other models, such as quadratic models, may also be considered. In choosing between an exponential model and a logarithmic model, we look at the way the data curves. This is called the concavity. If we draw a line between two data points and all or most of the data between those 2 points lies above that line, we say the curve is concave down. We can think of it as a bowl that bends downward and therefore cannot hold water. If all or most of the data between those 2 points lies below the line, we say the curve is concave up. In this case, we can think of a bowl that bends upward and can therefore hold water. An exponential curve, whether rising or falling, whether representing growth or decay, is always concave up away from its horizontal asymptote. A logarithmic curve is always concave away from its vertical asymptote. In the case of positive data, which is the most common case, an exponential curve is always concave up, and a logarithmic curve always concave down. A logistic curve changes concavity. It starts out concave up and then changes to concave down beyond a certain point, called a point of inflection. After using the graph to help us choose a type of function to use as a model, we substitute points and solve to find the parameters. We reduce round-off error by choosing points as far apart as possible. Example 7. Choosing a mathematical model does a linear, exponential, logarithmic, or logistic model best fit the values listed in Table 1. Find the model and use a graph to check your choice. X1 2 3 4 5 6 7 8 9 Y0 1 386 2 197 2 773 3 219 3 584 3 892 4 159 4 394. Table 1 solution. First, plot the data on a graph as in Figure 8. For the purpose of graphing, round the data to 2 decimal places. Graph of the previous table's values. Figure 8 clearly, the points do not lie on a straight line, so we reject a linear model. If we draw a line between any two of the points, most or all of the points between those 2 points lie above the line, so the graph is concave down, suggesting a logarithmic model. We can try letter 1D466 equals letter 1D44ELN, letter 1D44F, letter 1D465. Plugging in the first point, 10, gives 0 equals letter 1D44ELN, letter 1D44F. We reject the case that letter 1D44E equals 0. If it were, all outputs would be 0, so we know ln, letter 1D44F, equals 0. Thus letter 1D44F equals 1 and letter 1D466 equals letter 1D44ELN, x. Next, we can use the point 94, 394, to solve for a. Letter 1D466 equals letter 1D44ELN, letter 1D4654. 394 equals letter 1D44ELN, 9 letter 1D44E equals 4. 394 ln 9, because letter 1D44E equals 4. 394 ln 9, approximately 2, an appropriate model for the data is letter 1D466 equals 2 ln letter 1D465. To check the accuracy of the model, we graph the function together with the given points as in Figure 9. Graph of previous tables values showing that it fits the function y equals 2 ln x with an asymptote at x equals 0. Figure 9, the graph of letter 1d466 equals 2 ln letter 1d465. We can conclude that the model is a good fit to the data. Compare Figure 9 to the graph of letter 1d466 equals ln letter 1d4652 shown in Figure 10. Graph of previous tables values showing that it fits the function y equals 2 ln x with an asymptote at x equals 0. Figure 10, the graph of letter 1d466 equals ln letter 1d4652, the graphs appear to be identical when letter 1d4650. A quick check confirms this conclusion. Letter 1d466 equals ln letter 1d4652 equals 2 ln letter 1d465 for letter 1d4650. However, if letter 1d4650, the graph of letter 1d466 equals ln letter 1d4652 includes an extra branch, as shown in Figure 11. This occurs because, while letter 1d466 equals 2 ln letter 1d465 cannot have negative values in the domain, as such values would force the argument to be negative, the function letter 1d466 equals ln letter 1d4652 can have negative domain values. Graph of y equals ln x2. Figure 11 try it 6. Does a linear, exponential, or logarithmic model best fit the data in Table 2? Find the model. x1 2 3 4 5 6 7 8 9 y3, 297 5, 437 8, 963 14, 778 24, 365 40, 172 66, 231 109, 196 180. 34 Table 2, expressing an exponential model in base e, while powers and logarithms of any base can be used in modeling. The two most common bases are 10 and e. In science and mathematics, the base e is often preferred. We can use laws of exponents and laws of logarithms to change any base to base e. How to given a model with the form letter 1d466 equals letter 1d44 letter 1d44f letter 1d465. Change it to the form letter 1d466 equals letter 1d434, 0, letter 1d452 letter 1d458 letter 1d465. Rewrite letter 1d466 equals letter 1d44 letter 1d44f letter 1d465 as letter 1d466 equals letter 1d44 letter 1d452 ln letter 1d44f letter 1d465. Use the power rule of logarithms to rewrite y as letter 1d466 equals letter 1d44 letter 1d452 letter 1d465 ln. Letter 1d44f equals letter 1d44 letter 1d452 ln letter 1d44f letter 1d465. Note that letter 1d44e equals letter 1d4340 and letter 1d458 equals ln letter 1d44f. In the equation, letter 1d466 equals letter 1d4340, letter 1d452 letter 1d458 letter 1d465. Example 8 changing to base e change, the function letter 1d466 equals 2, 5, 3. 1 letter 1d465 so that this same function is written in the form letter 1d466 equals letter 1d4340, letter 1d452 letter 1d458 letter 1d465. Solution: the formula is derived as follows: letter 1d466 equals 2, 5, 3. 1 letter 1d465 equals 2, 5 letter 1d452 ln 3. 1 letter 1d465 equals 2, 5 letter 1d452 letter 1d465 ln 3. 1 equals 2, 5 letter 1d452 ln 3. 1 letter 1d465 insert exponential and its inverse. Laws of logs. Commutative law of multiplication try it 7 change, the function letter 1d466 equals 3, 0. 5 letter 1d465 to 1 having e as the base. Media access, these online resources for additional instruction and practice with exponential and logarithmic models. Logarithm application, pH exponential model, age using half-life Newton's law of cooling exponential growth given doubling time exponential growth. find initial amount given doubling time 6. 7 section exercises verbal 1. With what kind of exponential model would half-life be associated? What role does half-life play in these models? 2. What is carbon dating? Why does it work? Give an example in which carbon dating would be useful. 3. With what kind of exponential model would doubling time be associated? What role does doubling time play in these models? 4. Define Newton's law of cooling. Then name at least 3 real-world situations where Newton's law of cooling would be applied. 5. What is an order of magnitude? Why are orders of magnitude useful? Give an example to explain. Numeric 6. The temperature of an object in degrees Fahrenheit after t minutes is represented by the equation letter 1d447, letter 1d461, equals 68 letter 1d452 minus 0, 174t plus 72. To the nearest degree, what is the temperature of the object after 1.5 hours? For the following exercises, use the logistic growth model letter 1d453, letter 1d465, equals 1501 plus 8 letter 1d452 minus 2 letter 1d465. 7. Find and interpret letter 1d453, 0, round to the nearest tenth. 8. Find and interpret letter 1d453, 4, round to the nearest tenth. 9. Find the carrying capacity. 10. Graph the model. 11. Determine whether the data from the table could best be represented as a function that is linear, exponential, or logarithmic. Then write a formula for a model that represents the data. X letter 1d453, letter 1d465, 20,69410, 833.0, 11122, 144.31, 728.42, 74.52, 488.12. Rewrite 68.0. 65. Letter 1d465 as an exponential equation with base e to 5 decimal places. Technology for the following exercises: enter the data from each table into a graphing calculator and graph the resulting scatter plots. Determine whether the data from the table could represent a function that is linear, exponential, or logarithmic. 13. X letter 1d453, letter 1d465, 1224. 79, 35, 296.46, 159.56, 828, 6, 7, 375, 7, 7, 838.88, 238.98, 592.10.8, 908.14. X letter 1d453, letter 1d465, 12422, 88.33, 456.44. 147.54, 977.65, 972.77, 166.88, 6, 9, 10, 32, 10, 12, 380.315. X letter 1d453, letter 1d465, 49, 429.59, 972.610, 415.710, 79.811, 115.911, 401.10.11, 657.11.11, 889.12.12, 101.13.12, 295.16. X letter 1d453, letter 1d465, 125.5, 75.225.8, 75.3, 56.12, 68.4214, 65, 65.18, 95.6, 75.22, 25.7, 25.23, 75.8, 6.27, 8.9, 25.29, 75.10, 5.33. 5. For the following exercises, use a graphing calculator and this scenario. The population of a fish farm in T years is modeled by the equation letter 1d443, letter 1d461 equals 10,001 plus 9 letter 1d452 minus 0. 6t17. Graph the function. 18. What is the initial population of fish? 19. To the nearest tenth, what is the doubling time for the fish population? 20. To the nearest whole number, what will the fish population be after 2 years? 21. To the nearest tenth, how long will it take for the population to reach 900? 22. What is the carrying capacity for the fish population? Justify your answer using the graph of p extensions 23. A substance has a half-life of 245 minutes. If the initial amount of the substance was 132. 8 grams, how many half-lives will have passed before the substance decays to 83 grams? What is the total time of decay? 24. The formula for an increasing population is given by letter 1d443. Letter 1d461 equals letter 1d4430, letter 1d45 letter 1d45f, letter 1d461, where p0 is the initial population and letter 1d45f 0. Derive a general formula for the time t it takes for the population to increase by a factor of m25. Recall the formula for calculating the magnitude of an earthquake. Letter 1d440 equals 23 log letter 1d446 letter 1d4460. Show each step for solving this equation algebraically for the seismic moment S26. What is the y-intercept of the logistic growth model letter 1d466 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d45f letter 1d465. Show the steps for calculation. What does this point tell us about the population? 27. Prove that letter 1d44f letter 1d465 equals letter 1d452 letter 1d465 ln letter 1d44f for positive letter 1d44f not equal to 1. Real-world applications for the following exercises use this scenario. A doctor prescribes 125 milligrams of a therapeutic drug that decays by about 30% each hour. 28. To the nearest hour, what is the half-life of the drug? 29. Write an exponential model representing the amount of the drug remaining in the patient's system after t hours. Then use the formula to find the amount of the drug that would remain in the patient's system after 3 hours. Round to the nearest milligram. 30. Using the model found in the previous exercise, find letter 1d453, 10, and interpret the result. Round to the nearest hundredth. For the following exercises, use this scenario. A tumor is injected with 0.5 grams of iodine, which has a decay rate of 115% per day. 31. To the nearest day, how long will it take for half of the iodine to decay? 32. Write an exponential model representing the amount of iodine remaining in the tumor after t days. Then use the formula to find the amount of iodine that would remain in the tumor after 60 days. Round to the nearest tenth of a gram. 33. A scientist begins with 250 grams of a radioactive substance. After 250 minutes, the sample has decayed to 32 grams. Rounding to 5 decimal places, write an exponential equation representing this situation. To the nearest minute, what is the half-life of this substance? 34. The half-life of radium-226 is 1590 years. What is the annual decay rate? Express the decimal result to 4 decimal places and the percentage to 2 decimal places. 35. The half-life of erbium-165 is 10 hours. What is the hourly decay rate? Express the decimal result to 4 decimal places and the percentage to 2 decimal places. 36. A wooden artifact from an archaeological dig contains 60% of the carbon-14 that is present in living trees. To the nearest year, about how many years old is the artifact? The half-life of carbon-14 is 5730 years. 37. A research student is working with a culture of bacteria that doubles in size every 20 minutes. The initial population count was 1350 bacteria. Rounding to 5 decimal places, write an exponential equation representing this situation. To the nearest whole number, what is the population size after 3 hours? For the following exercises, use this scenario. A biologist recorded a count of 360 bacteria present in a culture after 5 minutes and 1,000 bacteria present after 20 minutes. 38. To the nearest whole number, what was the initial population in the culture? 39. Rounding to 6 decimal places, write an exponential equation representing this situation. To the nearest minute, how long did it take the population to double? For the following exercises, use this scenario. A pot of warm soup with an internal temperature of 100 degrees Fahrenheit was taken off the stove to cool in a 69 degrees F room. After 15 minutes, the internal temperature of the soup was 95 degrees F40. Use Newton's law of cooling to write a formula that models this situation. 41. To the nearest minute, how long will it take the soup to cool to 80 degrees F? 42. To the nearest degree, what will the temperature be after 2.5 hours? For the following exercises, use this scenario. A turkey is taken out of the oven with an internal temperature of 165 degrees F and is allowed to cool in a 75 degrees F room. After half an hour, the internal temperature of the turkey is 145 degrees F. 43. Write a formula that models this situation. 44. To the nearest degree, what will the temperature be after 50 minutes? 45. To the nearest minute, how long will it take the turkey to cool to 110 degrees F? For the following exercises, find the value of the number shown on each logarithmic scale. Round all answers to the nearest thousandth. 46. Number line to show log x is between -1 and 0.47. Number line to show log x is between 1 and 248. Plot each set of approximate values of intensity of sounds on a logarithmic scale. Whisper. 10 minus 10, letter 1d44, letter 1d45a, 2, vacuum. 10 minus 4, letter 1d44, letter 1d45a, 2, jet. 102, letter 1d44, letter 1d45a, 249. Recall the formula for calculating the magnitude of an earthquake. Letter 1d440 equals 23 log letter 1d446, letter 1d4460. One earthquake has magnitude 3. 9 on the MMS scale. If a second earthquake has 750 times as much energy as the first, find the magnitude of the second quake. Round to the nearest hundredth. For the following exercises, use this scenario. The equation letter 1d441, letter 1d461 equals 5001 plus 49 letter 1d452 minus 0. 7t models the number of people in a town who have heard a rumor after t days. 50. How many people started the rumor? 51. To the nearest whole number, how many people will have heard the rumor after 3 days? 52. As t increases without bound, what value does letter 1d441, letter 1d461 approach? Interpret your answer. For the following exercise, choose the correct answer choice. 53. A doctor injects a patient with 13 milligrams of radioactive dye that decays exponentially. After 12 minutes, there are 75 milligrams of dye remaining in the patient's system. Which is an appropriate model for this situation? A. Letter 1d453, letter 1d461 equals 13, 0, 0805. Letter 1d461, B. Letter 1d453. Letter 1d461 equals 13, letter 1d4520. 9195 TC, letter 1d453. Letter 1d461 equals 13, letter 1d452 minus 0. 839t D, letter 1d453, letter 1d461 equals 4. 751 plus 13, letter 1d452 minus 0. 80, 3925t. Learning objectives in this section, you will build an exponential model from data, build a logarithmic model from data, build a logistic model from data. In previous sections of this chapter, we were either given a function explicitly to graph or evaluate, or we were given a set of points that were guaranteed to lie on the curve. Then we used algebra to find the equation that fit the points exactly. In this section, we use a modeling technique called regression analysis to find a curve that models data collected from real-world observations. With regression analysis, we don't expect all the points to lie perfectly on the curve. The idea is to find a model that best fits the data. Then we use the model to make predictions about future events. Do not be confused by the word model. In mathematics, we often use the terms function, equation, and model interchangeably, even though they each have their own formal definition. The term model is typically used to indicate that the equation or function approximates a real-world situation. We will concentrate on 3 types of regression models in this section: exponential, logarithmic, and logistic. Having already worked with each of these functions gives us an advantage. Knowing their formal definitions, the behavior of their graphs, and some of their real-world applications gives us the opportunity to deepen our understanding. As each regression model is presented, key features and definitions of its associated function are included for review. Take a moment to rethink each of these functions, reflect on the work we've done so far, and then explore the ways regression is used to model real-world phenomena. Building an exponential model from data, as we've learned, there are a multitude of situations that can be modeled by exponential functions, such as investment growth, radioactive decay, atmospheric pressure changes, and temperatures of a cooling object. What do these phenomena have in common? For one thing, all the models either increase or decrease as time moves forward. But that's not the whole story. It's the way data increase or decrease that helps us determine whether it is best modeled by an exponential equation. Knowing the behavior of exponential functions in general allows us to recognize when to use exponential regression. So let's review exponential growth and decay. Recall that exponential functions have the form letter 1 d466 equals letter 1 d44 letter 1 d44f letter 1 d465, or letter 1 d466 equals letter 1 d434, 0, letter 1 d452 letter 1 d458 letter 1 d465. When performing regression analysis, we use the form most commonly used on graphing utilities. Letter 1 d466 equals letter 1 d44 letter 1 d44f letter 1 d465. Take a moment to reflect on the characteristics. We've already learned about the exponential function letter 1 d466 equals letter 1 d44 letter 1 d44f letter 1 d465. Assume letter 1 d44 is 0. B must be greater than 0 and not equal to 1. The initial value of the model is letter 1 d466 equals letter 1 d44. If letter 1 d44f1, the function models exponential growth. As x increases, the outputs of the model increase slowly at first, but then increase more and more rapidly, without bound. If 0, letter 1 d44f1, the function models exponential decay. As x increases, the outputs for the model decrease rapidly at first and then level off to become asymptotic to the x-axis. In other words, the outputs never become equal to or less than 0. As part of the results, your calculator will display a number known as the correlation coefficient, labeled by the variable r or r2. You may have to change the calculator settings for these to be shown. The values are an indication of the goodness of fit of the regression equation to the data. We more commonly use the value of r2 instead of r, but the closer either value is to 1, the better the regression equation approximates the data. Exponential regression is used to model situations in which growth begins slowly and then accelerates rapidly without bound, or where decay begins rapidly and then slows down to get closer and closer to 0. We use the command expreg on a graphing utility to fit an exponential function to a set of data points. This returns an equation of the form letter 1 d466 equals letter 1 d44 letter 1 d44f letter 1 d465. Note that b must be non-negative. When letter 1 d44f1, we have an exponential growth model. When 0, letter 1 d44f1, we have an exponential decay model. How to, given a set of data, perform exponential regression using a graphing utility. Use the Stat then Edit menu to enter given data. Clear any existing data from the lists. List the input values in the L1 column. List the output values in the L2 column. Graph and observe a scatter plot of the data using the SDATPLOT feature. Use Zoom 9 to adjust axes to fit the data. Verify the data follow an exponential pattern. Find the equation that models the data. Select expreg from the Stat then CALC menu. Use the values returned for A and B to record the model letter 1 d466 equals letter 1 d44 letter 1 d44f letter 1 d465. Graph the model in the same window as the scatter plot to verify it is a good fit for the data. Example 1, using exponential regression to fit a model to data in 2007, a university study was published investigating the crash risk of alcohol-impaired driving. Data from 2,871 crashes were used to measure the association of a person's blood alcohol level, BAC, with the risk of being in an accident. Table 1 shows results from the study 9. The relative risk is a measure of how many times more likely a person is to crash. So, for example, a person with a BAC of 0.9 is 354 times as likely to crash as a person who has not been drinking alcohol. BAC 00, 1030, 50, 70, 9 relative risk of crashing 11, 31, 61, 38.2, 93. 54 BAC 0, 11 0, 13 0, 15 0, 17 0, 19 0, 21 relative risk of crashing 6, 41 12, 622, 139, 565, 3299. 78 Table 1, let X represent the BAC level, and let Y represent the corresponding relative risk. Use exponential regression to fit a model to these data. After 6 drinks, a person weighing 160 pounds will have a BAC of about 0.16. How many times more likely is a person with this weight to crash if they drive after having a 6-pack of beer? Round to the nearest hundredth. Try it. 1 Table 2 shows a recent graduate's credit card balance each month after graduation. Month 1 2 3 4 5 6 7 8 debt, $620 761, 88 899, 80 1039, 93 1270, 63 15 89, 4 18 51, 31 21 54. 92 Table 2, A. Use exponential regression to fit a model to these data. B. If spending continues at this rate, what will the graduate's credit card debt be 1 year after graduating? Q&A. Is it reasonable to assume that an exponential regression model will represent a situation indefinitely? No, remember that models are formed by real-world data gathered for regression. It is usually reasonable to make estimates within the interval of original observation, interpolation. However, when a model is used to make predictions, it is important to use reasoning skills to determine whether the model makes sense for inputs far beyond the original observation interval, extrapolation. Building a logarithmic model from data. Just as with exponential functions, there are many real-world applications for logarithmic functions. Intensity of sound, pH levels of solutions, yields of chemical reactions, production of goods, and growth of infants. As with exponential models, data modeled by logarithmic functions are either always increasing or always decreasing as time moves forward. Again, it is the way they increase or decrease that helps us determine whether a logarithmic model is best. Recall that logarithmic functions increase or decrease rapidly at first, but then steadily slow as time moves on. By reflecting on the characteristics we've already learned about this function, we can better analyze real-world situations that reflect this type of growth or decay. When performing logarithmic regression analysis, we use the form of the logarithmic function most commonly used on graphing utilities. Letter 1D466 equals letter 1D44E plus letter 1D44FLN, letter 1D465. For this function, all input values, x, must be greater than 0. The point 1a is on the graph of the model. If letter 1D44F0, the model is increasing. Growth increases rapidly at first and then steadily slows over time. If letter 1D44F0, the model is decreasing. Decay occurs rapidly at first and then steadily slows over time. Logarithmic regression is used to model situations where growth or decay accelerates rapidly at first and then slows over time. We use the command lnreg on a graphing utility to fit a logarithmic function to a set of data points. This returns an equation of the form letter 1D466 equals letter 1D44E plus letter 1D44FLN, letter 1D465. Note that all input values, x, must be non-negative. When letter 1D44F0, the model is increasing. When letter 1D44F0, the model is decreasing. How to, given a set of data, perform logarithmic regression using a graphing utility. Use the Stat then Edit menu to enter given data. Clear any existing data from the lists. List the input values in the L1 column. List the output values in the L2 column. Graph and observe a scatter plot of the data using the STATPLOT feature. Use Zoom 9 to adjust axes to fit the data. Verify the data follow a logarithmic pattern. Find the equation that models the data. Select lnreg from the Stat then CALC menu. Use the values returned for A and B to record the model. Letter 1D466 equals letter 1D44E plus letter 1D44FLN, letter 1D465. Graph the model in the same window as the scatterplot to verify it is a good fit for the data. Example 2, using logarithmic regression to fit a model to data. Due to advances in medicine and higher standards of living, life expectancy has been increasing in most developed countries since the beginning of the 20th century. Table 3 shows the average life expectancies, in years, of Americans from 1900 to 1010. Year 1900, 1910, 1920, 1930, 1940, 1950 life expectancy. Years 47, 350, 054, 159, 762, 968. 2-year 1960, 1970, 1980, 1990, 2000, 2010 life expectancy. Years 69, 770, 873, 775, 476, 878. 7 Table 3, A. Let X represent time in decades starting with letter 1D465 equals 1 for the year 1900, letter 1D465 equals 2 for the year 1910, and so on. Let Y represent the corresponding life expectancy. Use logarithmic regression to fit a model to these data. B. Use the model to predict the average American life expectancy for the year 2030. Solution, using the Stat, then Edit menu on a graphing utility. List the years using values 112 in L1 and the corresponding life expectancy in L2. Then use the SDATPLOT feature to verify that the scatterplot follows a logarithmic pattern as shown in Figure 3. Graph of a scattered plot. Figure 3, use the lnreg command from the Stat, then CALC menu to obtain the logarithmic model. Letter 1D466 equals 42. 52,722,583 plus 13. 85,752,327 ln, letter 1D465. Next, graph the model in the same window as the scatterplot to verify it is a good fit as shown in Figure 4. Graph of a scattered plot with an estimation line. Figure 4b, to predict the life expectancy of an American in the year 2030, substitute letter 1D465 equals 14 for the in the model and solve for Y. Letter 1D466 equals 42. 52,722,583 plus 13. 85,752,327 ln, letter 1D465, equals 42. 52,722,583 plus 13. 85,752,327 ln, 14, approximately 79. 1. Use the regression model found in Part A. Substitute 14 for x round to the nearest tenth. If life expectancy continues to increase at this pace, the average life expectancy of an American will be 79. 1 by the year 2030. Try it. 2 sales of a video game released in the year 2000 took off at first, but then steadily slowed as time moved on. Table 4 shows the number of games sold, in thousands, from the years 2000-2010. Year 2000, 2001, 2002, 2003, 2004, 2005. Number sold thousands. 142, 149, 154, 155. 159, 161 year 2006, 2007, 2008, 2009, 2010. Number sold thousands. 163, 164, 164, 166. 167 Table 4. A. Let X represent time in years, starting with letter 1D465, equals 1 for the year 2000. Let Y represent the number of games sold in thousands. Use logarithmic regression to fit a model to these data. B. If games continue to sell at this rate, how many games will sell in 2015? Round to the nearest thousand. Building a logistic model from data like exponential and logarithmic growth, logistic growth increases over time. One of the most notable differences with logistic growth models is that, at a certain point, growth steadily slows, and the function approaches an upper bound or limiting value. Because of this, logistic regression is best for modeling phenomena where there are limits in expansion, such as availability of living space or nutrients. It is worth pointing out that logistic functions actually model resource-limited exponential growth. There are many examples of this type of growth in real-world situations, including population growth and spread of disease, rumors, and even stains in fabric. When performing logistic regression analysis, we use the form most commonly used on graphing utilities. Letter 1D466 equals letter 1D450, 1 plus letter 1D44 letter 1D452 minus letter 1D44F letter 1D465. Recall that C1 plus A is the initial value of the model. When letter 1D44F0, the model increases rapidly at first until it reaches its point of maximum growth rate, ln, letter 1D44E letter 1D44F, letter 1D4502. At that point, growth steadily slows, and the function becomes asymptotic to the upper bound letter 1D466 equals letter 1D450. C is the limiting value, sometimes called the carrying capacity, of the model. Logistic regression is used to model situations where growth accelerates rapidly at first and then steadily slows to an upper limit. We use the command logistic on a graphing utility to fit a logistic function to a set of data points. This returns an equation of the form letter 1D466 equals letter 1D450, 1 plus letter 1D44 letter 1D452 minus letter 1D44F letter 1D465. Note that the initial value of the model is C1 plus A. Output values for the model grow closer and closer to letter 1D466 equals letter 1D450 as time increases. How to, given a set of data, perform logistic regression using a graphing utility. Use the Stat then Edit menu to enter given data. Clear any existing data from the lists. List the input values in the L1 column. List the output values in the L2 column. Graph and observe a scatter plot of the data using the SDATPLOT feature. Use Zoom 9 to adjust axes to fit the data. Verify the data follow a logistic pattern. Find the equation that models the data. Select Logistic from the Stat then CALC menu. Use the values returned for A, B, and C to record the model. Letter 1D466 equals letter 1D450, 1 plus letter 1D44 letter 1D452 minus letter 1D44F letter 1D465. Graph the model in the same window as the scatter plot to verify it is a good fit for the data. Example 3, using logistic regression to fit a model to data mobile telephone service, has increased rapidly in America since the mid-1990s. Today, almost all residents have cellular service. Table 5 shows the percentage of Americans with cellular service between the years 1995 and 2012-11. Year Americans with cellular service, percent, year Americans with cellular service, percent, 1995-12. 69 2004 62, 852 1996 16, 35 2005 68, 63 1997 20, 29 2006 76, 64 1998 25, 8 2007 82, 47 1999 30, 81 2008 85, 68 2038, 75 2009 89, 14 2001 45, 2010 91, 86 2002 49, 16 2011 95, 28 2003 55, 15 2012 98, 17 Table 5a, let x represent time in years, starting with letter 1D465 equals 0 for the year 1995. Let y represent the corresponding percentage of residents with cellular service. Use logistic regression to fit a model to these data. B. Use the model to calculate the percentage of Americans with cell service in the year 2013. Round to the nearest tenth of a percent. C. Discuss the value returned for the upper limit. C. What does this tell you about the model? What would the limiting value be if the model were exact? Try it 3. Table 6 shows the population in thousands of harbor seals in the Wadden Sea over the years 1997 to 2012. Year seal population, thousands. Year seal population, thousands, 1997 3. 493, 2005 590 1998, 282, 2006 21. 955 1999 6. 357 2007 22. 862 2009. 201 2008 23. 869 2001 11. 224 2009 24. 243 2002 12. 964 2010 24. 344 2003 16. 226 2011 24. 919 2004 18 137 2012 25. 108. Table 6. A. Let x represent time in years, starting with letter 1d465 equals 0 for the year 1997. Let y represent the number of seals in thousands. Use logistic regression to fit a model to these data. B. Use the model to predict the seal population for the year 2020. C. To the nearest whole number, what is the limiting value of this model? Media access this online resource for additional instruction and practice with exponential function models. Exponential regression on a calculator 6-8 section, exercises verbal 1. What situations are best modeled by a logistic equation? Give an example and state a case for why the example is a good fit. 2. What is a carrying capacity? What kind of model has a carrying capacity built into its formula? Why does this make sense? 3. What is regression analysis? Describe the process of performing regression analysis on a graphing utility. 4. What might a scatterplot of data points look like if it were best described by a logarithmic model? 5. What does the y-intercept on the graph of a logistic equation correspond to for a population modeled by that equation? Graphical for the following exercises, match the given function of best fit with the appropriate scatterplot in Figure 7 through Figure 11. Answer using the letter beneath the matching graph. Graph of a scattered plot. Figure 7 graph of a scattered plot. Figure 8 graph of a scattered plot. Figure 9 graph of a scattered plot. Figure 10 graph of a scattered plot. Figure 11 6. Letter 1d466 equals 10. 209 letter 1d452 minus 0. 294 x 7. Letter 1d466 equals 5. 598 minus 1. 912 ln, letter 1d465, 8. Letter 1d466 equals 2, 104, 1. 479, letter 1d465, 9. Letter 1d466 equals 4. 607 plus 2. 733 ln, letter 1d465, 10. Letter 1d466 equals 14. 51 plus 2. 79 letter 1d452 minus 0. 812 x numeric 11. To the nearest whole number, what is the initial value of a population modeled by the logistic equation plus 6? 995 letter 1d452 minus 0. 68t, what is the carrying capacity? 12. Rewrite the exponential model letter 1d434, letter 1d461 equals 1550, 1. 085, letter 1d465 as an equivalent model with base. Express the exponent to 4 significant digits. 13. A logarithmic model is given by the equation letter 210e, letter 1d45d equals 67. 682 minus 5. 792 ln, letter 1d45d. To the nearest hundredth, for what value of p does letter 210e, letter 1d45d equals 62? 14. A logistic model is given by the equation letter 1d443, letter 1d461, equals 901 plus 5 letter 1d452 minus 0. 42t to the nearest hundredth, for what value of t does letter 1d443, letter 1d461 equals 45? 15. What is the y-intercept on the graph of the logistic model given in the previous exercise? Technology for the following exercises, use this scenario. The population P of a koi pond over X months is modeled by the function letter 1d443, letter 1d465, equals 680, 1 plus 16 letter 1d452 minus 0. 28x16. Graph the population model to show the population over a span of 3 years. 17. What was the initial population of koi? 18. How many koi will the pond have after 1.5 years? 19. How many months will it take before there are 20 koi in the pond? 20. Use the intersect feature to approximate the number of months it will take before the population of the pond reaches half its carrying capacity. For the following exercises, use this scenario. The population P of an endangered species habitat for wolves is modeled by the function letter 1d443, letter 1d465, equals 5,580, 1 plus 54. 8 letter 1d452 minus 0. 462x, where x is given in years. 21. Graph the population model to show the population over a span of 10 years. 22. What was the initial population of wolves transported to the habitat? 23. How many wolves will the habitat have after 3 years? 24. How many years will it take before there are 100 wolves in the habitat? 25. Use the intersect feature to approximate the number of years it will take before the population of the habitat reaches half its carrying capacity. For the following exercises, refer to Table 7. X 1, 2, 3, 4, 5, 6, F. X 11, 25, 14, 95, 23, 10, 32, 94, 46, 50, 63, 61, Table 7, 26. Use a graphing calculator to create a scatter diagram of the data. 27. Use the regression feature to find an exponential function that best fits the data in the table. 28. Write the exponential function as an exponential equation with base e29. Graph the exponential equation on the scatter diagram. 30. Use the intersect feature to find the value of x for which letter 1d453, letter 1d465 equals 4,000. For the following exercises, refer to Table 8. X 1, 2, 3, 4, 5, 6, F. X 555, 380, 307, 210, 158, 122, Table 831. Use a graphing calculator to create a scatter diagram of the data. 32. Use the regression feature to find an exponential function that best fits the data in the table. 33. Write the exponential function as an exponential equation with base e34. Graph the exponential equation on the scatter diagram. 35. Use the intersect feature to find the value of x for which letter 1d453, letter 1d465 equals 250. For the following exercises, refer to Table 9. X 1, 2, 3, 4, 5, 6, F, X 516, 373778, 18, 6 Table 936. Use a graphing calculator to create a scatter diagram of the data. 37. Use the Logarithm option of the regression feature to find a logarithmic function of the form letter 1d466 equals letter 1d44e plus letter 1d44fln, letter 1d465, that best fits the data in the table. 38. Use the logarithmic function to find the value of the function when letter 1d465 equals 10. 39. Graph the logarithmic equation on the scatter diagram. 40. Use the intersect feature to find the value of x for which letter 1d453, letter 1d465 equals 7. For the following exercises, refer to Table 10. X 1, 2, 3, 4, 5, 6, 7, 8, F, X 7, 5, 6, 5, 2, 4, 3, 3, 9, 3, 4, 3, 1, 2, 9 Table 1041. Use a graphing calculator to create a scatter diagram of the data. 42. Use the Logarithm option of the regression feature to find a logarithmic function of the form letter 1d466 equals letter 1d44e plus letter 1d44fln, letter 1d465, that best fits the data in the table. 43. Use the logarithmic function to find the value of the function when letter 1d465 equals 10. 44. Graph the logarithmic equation on the scatter diagram. 45. Use the intersect feature to find the value of x for which letter 1d453, letter 1d465 equals 8. For the following exercises, refer to Table 11. X 1 2 3 4 5 6 7 8 9 10 F X 8 7 12 3 15 4 18 5 20 7 22 5 23 3 24 24 6 24 8 Table 11 46. Use a graphing calculator to create a scatter diagram of the data. 47. Use the logistic regression option to find a logistic growth model of the form letter 1d466 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d465 that best fits the data in the table. 48. Graph the logistic equation on the scatter diagram. 49. To the nearest whole number, what is the predicted carrying capacity of the model? 50. Use the intersect feature to find the value of x for which the model reaches half its carrying capacity. For the following exercises, refer to Table 12. X0 2 4 5 7 8 10 11 15 17 letter 1d453, letter 1d465, 12 28, 652, 870, 399, 9 112, 5 125, 8 127, 9 135, 1 135, 9 Table 1251. Use a graphing calculator to create a scatter diagram of the data. 52. Use the logistic regression option to find a logistic growth model of the form letter 1d466 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d465 that best fits the data in the table. 53. Graph the logistic equation on the scatter diagram. 54. To the nearest whole number, what is the predicted carrying capacity of the model? 55. Use the intersect feature to find the value of x for which the model reaches half its carrying capacity. Extensions 56. Recall that the general form of a logistic equation for a population is given by letter 1d443. Letter 1d461 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d461, such that the initial population at time letter 1d461 equals 0 is letter 1d443. 0 equals letter 1d4430. Show algebraically that letter 1d450 minus letter 1d443. Letter 1d461 letter 1d443. Letter 1d461 equals letter 1d450 minus letter 1d443, 0, letter 1d443, 0, letter 1d452, minus letter 1d44f letter 1d461. 57. Use a graphing utility to find an exponential regression formula letter 1d453, letter 1d465, and a logarithmic regression formula letter 1d454, letter 1d465 for the points 1, 51, 5, and 8, 58, 5. Round all numbers to 6 decimal places. Graph the points and both formulas along with the line letter 1d466 equals letter 1d465 on the same axis. Make a conjecture about the relationship of the regression formulas. 58. Verify the conjecture made in the previous exercise. Round all numbers to 6 decimal places when necessary. 59. Find the inverse function letter 1d453 minus 1, letter 1d465. For the logistic function letter 1d453. Letter 1d465 equals letter 1d450, 1 plus letter 1d44 letter 1d452 minus letter 1d44f letter 1d465. Show all steps. 60. Use the result from the previous exercise to graph the logistic model letter 1d443, letter 1d461, equals 201 plus 4 letter 1d452 minus 0. 5t along with its inverse on the same axis. What are the intercepts and asymptotes of each function?